the director of the Department of Earth Sciences, Dr. Pedro Pina. So I'll give the floor to our first speaker, Dr. Nuno Mendoza.
Good morning, everyone. Thank you, Vasco, for the invitation to be here with you. Thank you for choosing Coimbra to meet here, to understand not only share your knowledge between each other, but also to understand what Coimbra University has to offer in a very sustainable way for the future. The last 6 months we have been, although we have more than 150 years of data on climatic data within the university libraries and old archives, the last 6 months we have been shifting the way that we are proposing to translate this capacity to the market. We choose to operate under the brand of UC Space Hub, initiative that joins every kind of researcher or research center within the university that is connected with space or directly or indirectly related to space. And this allows us to understand, at least at the rectory point, and the faculty, of course, to understand what are the needs of the researchers and how can we better approach the solving of the funding problem, the political problem of, or even the capacity to transfer the knowledge in a more efficient way. And for us, it's very important for you to understand, even during this conference, that we are here to help each other and be able to make sure that we are more able to translate knowledge and technology to the market in a more efficient way. Furthermore, in the last, and we are launching now in June 29, with the City Hall and the vast majority of companies, the Coimbra Supernova, which is a regional cluster focused on economic development, based not only on the scientific knowledge of the university, but also in the entrepreneurship and in the spin-offs and startups that arose from the Instituto Pedro Nunes, which is and the ASABIC that is incubated there for the last 10 years. So Coimbra ecosystem is not only composed of scientific knowledge within the university, but also from the innovation point of view, from the business development point of view, and we are aiming to share with you in the next couple of days this knowledge, so we probably identify other synergies that could arise from the IPC conference. So again, I hope you have a great 3 days of work in Coimbra. Hopefully you have some time to visit also our library. At least it's the minimum that we can offer to you guys, but I'm pretty sure you will have the best time in the next couple of days. So thank you and have a nice day.
Thank you very much. I'd like to welcome now Dr. Edmundo Monteiro, Dean of the Faculty of Science.
Good morning, everybody. It's a pleasure to welcome you and to be in the opening session of this conference, International Precipitation Conference. So the topic is very important for the faculty. Our faculty, we have 11 departments, and this topic is touched by several of our departments and research centers. And it is very important for Coimbra because, as you might know, in Coimbra it rains a lot, so we had lots of rain this year. This year it was very heavy rain and we had flooding. All this impact relates, so we had the downtown was underwater and the river from here to the fields, the Mondego fields, are still full of sand, and there was a ditch that was a channel that was broken, so we had strong impact of heavy weather this year, and it has and we have it's a big debate how to install mechanisms to build a new dam up river or not. to how to control this, how to make this, because the Mondego fields from here to the sea, they are very important for rice plantation, and the economic impact of this heavy weather that we had this year was a high impact. So our Faculty of Science and Technology, we have 11 departments, and the topic is covered by the Earth Science Department that is also in this building. So in this building, it's the direction of the faculty and the Earth Science Department. We share the building. Then Pedro will talk a bit about the activities of the Earth Science Department in this field, but there are many. But we have other departments like the Computer Science Department, we call it Informatics. We have projects related to space weather or prediction of debris in the space. It's not directly related, but is in this field with AI and machine learning. And the topics I saw, weather radars, they are covered by the electrical engineering department. That is I'm originally from this electrical engineering department, so several of the topics that I saw in the paper related to using this kind of technologies to predict and to measure the impacts of the weather. So we have also the civil engineering department that deals with the hydraulics and all this impact of the structures that are built along the river and that were obstructed by trees and this was the reason that also the impact was also severe of this flood that we had. We have also in the life science department, so they have several, they are quite strong in ecology, and they have a strong group in ecology, and so they study all the water-related aspects from the small streams. They have one research group studying these small streams of water, and then everything from the river until the sea. So the topic is very important. I know that we have remotely more than 100 people attending, so pity that you are not in Coimbra, but next time you can visit us. You that are here, enjoy the city, enjoy we will have good weather this week, it seems. No rain forecast. Yesterday there was a bit, but no rain for the rest of the week. So good weather and a nice city environment, so cultural environment. All the nightlife is quite intense here. Enjoy the city, enjoy the university, and welcome. Thank you.
Well, now, and I apologize to Pedro Pina, because I don't think he was expecting to say a few words, but thank you so much, and thank you for all the help of the Department of Earth Sciences. Please.
Okay, thank you, Vasco. I'll be very brief. Okay, just to welcome you here at Coimbra, at the Earth Science Department, the Faculty of Sciences, also the University of Coimbra. It is a pleasure for the Earth Science Department to welcome you, to have you here in these conferences. Also, I would like to start also thank Vasco for adding this conference, which is also it's very good, which is to be chairing an international conference like IPC15 is very. It's very good for us. Okay. Also, it's very good also to us to see a researcher from a new generation being involved in this kind of activities. Okay. Well, just to mention. Okay, Earth Science Department here at the Faculty of Science and Technology from UC. It's added or is built in geology, but not only in geology. So Earth Science, we try at the department to focus on all the subjects related to geology, using the most recent techniques, the most recent technologies, to give answers to be to even our day problems. Just to finish, just to say, just to finish and to welcome you to have, which is important now is the next days. I would like to wish you a very good conference with very fruitful discussions. And once again, to finish, we are very pleased to be in this conference. Okay, thank you very much and welcome to Coimbra.
Well, now, because this is IPC15, it means there were many IPCs before. And I'd like to welcome to the stage Dr. Effie Fofola Giorgio for a historical perspective, how we got here. Thank you so much.
So good morning, everybody. So Vasco asked me to say a few words about the history of the IPCs. And this is an honor, but also reveals that probably I'm one of the oldest, if not the oldest in the room, which is another privilege. So how do I advance here? No. And then I hit.
Yes, just the arrows.
Okay. So the first conference, the first precipitation conference was in 1986. So we're celebrating today the 40th anniversary of the IPCs. So it started in 1986 in Caracas, Venezuela. Many of you, I hope, you know the name Ignacio Rodriguez Iturbe, who started these conferences. And when I organized the IPC12 in 2019, I asked Ignacio to be there. He could not. Unfortunately, he passed away a few years ago. But he gave a remote presentation, and it was very interesting to see the comments. At that time, 1986, I had finished my postdoc, and I was starting my first assistant professor position. And Ignacio said that 1986, he asked American Geophysical Union, can we have a conference? And Fred Spielhaus, at that time, the executive director of AGU, said, sure, and we'll give you $10,000. So we were 25 of us in Caracas, Venezuela, and Ignacio mentioned in his presentation that we didn't even use all the money. He had to return $5K back to AGU. These were the times. So we stayed all together in the dormitories. I remember one night we didn't even go to sleep. We were discussing the whole night, different times. So the next one, 1988, in Cambridge, Massachusetts, Rafael Bras organized that. College Station with Jerry North and Juan Valdez. And probably not all the names resonate with the younger people in the room. 1993, Vite Krajewski at the University of Iowa in Iowa City. 1995, I organized it in Greece, in the island of Crete. 98, it was in Hawaii, and Ronnie Avisar organized it. 2001, in Maine, Anna Barros and Elta here. Then we took it to Vancouver, and Chris Kumero was involved, and Alila. 2007, Son Lovejoy and Danielle Serger took it to Paris, France. 2010, it was here, Coimbra. So we're celebrating not only 40 years, but twice that was done in Coimbra. 2013 was in the Netherlands, Wageningen, and then, if you notice, the conference happened every 2 years at the beginning, 3 years after that. And then 2013, it kind of stalled. So I remember meeting Remco in the airport on my way to EGU Vienna, and I said, what happened to the IPC? He said, oh, it fell apart. I said, I'm going to do it. I'm going to just continue the tradition. So 2019, I organized it in Irvine, South California. Then Pierre organized it in Oklahoma. It was an excellent conference. And here we're back in Coimbra. So twice, University of Coimbra, and we are very thankful for bringing us back here. So as you can see on the map, half of the conferences were outside the US and half inside. And we have really develop an international community that is expanding. Now, just to put things into perspective, it's not only the dates, but it's the relationship we build, and 40 years, what does it mean? I don't know, but here are 1986, I don't have any pictures. We were not taking pictures, we didn't have phones. But in 1995, someone took these pictures that I found. This is me, and that's my two-year-old son, who, everybody laughs there, because as I was talking, he was coming and pulling my skirt and says, "Mom, enough talking, let's go and play." And, later, of course, 30 years later, this kid. Now, another picture. Some of you might recognize Rafael Bras. He has not changed much 30 years later. And then you cannot see behind, but is Vijay Gupta. I hope some of you know Ed Wemar. Then was Kostas Georgakakos, Vita Krajewski here, and Edward Zavatsky. All these are names that basically developed theories, and especially stochastic theories. At that time, the 25 people that we were in Caracas, Venezuela, were a few hydrologists, meteorologists, and mathematicians, because it was the time of basically developing mathematical and stochastic theories of hydrology, of precipitation and hydrology. And there you see here a little girl, that was my daughter, 5-year-old, who apparently had a conversation with Vijay Gupta, I don't know about what. But yes, she has grown too, and she is herself a faculty pursuing earth sciences, carbon cycling. So time flies, but what is important to note is that this relationship that we form, they're much more than professional. They're also personal, and friendships are developed. And I hope that many of you, the younger people, will walk away from this conference with personal connections to people for the rest of their lives. So I put together a perspective myself of the 40 years of precipitation research. Now, the decade of 1980, 1990, there was a lot of theory of scaling. How do I go from the small scale to the larger scale? The larger scale, at that time, the models were very, coarse scale. Stochastic point process models, emergent physical statistical descriptions, and a lot of nonlinearity and predictability. Now, I put there because it's interesting to note that, at least in the US, the Global Change Research Act of 1990 was passed as a law, okay, requiring research in global warming and related issues, and also the mandate by Congress that every 4 years there will be a report on the consequences of climate change, 40 years ago. The USG CRP, the first IPCC, and then we go to the next decade. A lot of work now, we started having a lot more data, 3-dimensional, 4-dimensional rainfall organization, storm dynamics, subgrid scale modeling, because we had the 40-kilometer at most resolution, and we said, okay, how do I downscale? Microphysics, cloud resolving models, flood forecasting. I was part of the National Academy study for the National Weather Service modernization, new computers that are keeping up with the age. The next RAD, TRIM was launched in 1997, the Tropical Rainfall Measuring Mission, and the IPC2. We go to 2000, 2010, probabilistic QPE and quantitative precipitation forecasting. A lot of research on model verification metrics, that is, how do I know if the model is doing well, multi-scale statistics, and so forth, and fully coupled atmosphere models, remote sensing of precipitation, because we started having some data from TRIM, and so forth. Some of you are familiar with the WRF, the Water Research and Forecasting Model that was developed at that time at NCAR, research to operations, operations to research. The first National Climate Assessment Report for the US, IPCC3, IPCC4. So you can see there was a lot of activity in these decades on precipitation and climate change. We go to the decade of 2010, 2020. We had a lot more observations from multi-satellite platforms. We started worrying about extremes, water cycle at the global scale and regional scale and so forth, and started worrying more about non-stationarities. We started having longer records and observing some signs of climate change. So GPM was launched in 2014. We had in the US 3 national climate assessment reports, the second, third, and the fourth, IPCC5, and also the first decadal survey of observation from space, 2017. And we passed to the current decade. We're halfway through that. We have seen the AI, machine learning, deep learning revolution. That is basically something that in 2010, 2020 was not there. Data-driven model for weather, climate, for precipitation retrieval, for data simulation, and sample models for uncertainty quantification and high-impact weather. In fact, the National Academy of Studies I was part of redefined the standards for the design of high-hazard dams, the so-called probable maximum precipitation, because of non-stationarities and climate change. So IPCC6, ECMWF released the ERA, the reanalysis products, the fifth climate assessment in 2023. And I put a question mark there because we are in the US in different times. In case you don't know, the sixth national climate assessment was canceled. Reports have been removed from the federal websites. And we're going through some tough periods for the research, and especially for whatever has to do with the future of environmental sciences and climate change. But the international precipitation science will persist and thrive. And we are very thankful that you brought us here, and the University of Coimbra hosting us, and Vasco for doing all the work to have us here. And I look forward to 3 days, not only of exchanging research ideas, but also, again, building relationships that will stay for us for 40 years, as they have stayed with me when I started my career, and I still, have the friendships that were developed at that conference. So thank you, Vasco.
Well, thank you so much. This was a great way to start. I'd like to, first of all, say it's a great pleasure to have you here in Coimbra and to officially open the 15th International Precipitation Conference. It is truly special to have you here in person and online in the heart of Portugal. And for what I believe will be a very exciting 3 days of science, discussion, and community building. Before we begin, I'd like to ask for a moment of silence in the memory of Dr. Paul Kucera, whose work and commitment to precipitation science, international collaboration, and capacity building had a deep impact on many people in this community. His generosity, scientific leadership, and dedication to making precipitation data useful for society will remain part of the legacy in this field. So please, let's observe a minute of silence in his memory. Thank you. So IPC15 is, as Effie was describing so well, it's also part of a journey that continued strongly after IPC14. A lot of emails I sent you throughout the months asking you for presentations, asking you for abstracts, all sort of things. And I do apologize for all the emails that remain unanswered or delayed. or any other problem you had during this process. IPC14 was excellently hosted by Pierre Kierstetter and his team in Norman, Oklahoma, and many of us left Norman with new ideas, new collaborations, and a renewed sense that this community has an important role to play. It is very exciting to now continue that journey and legacy here in Coimbra. Over the last months, it has been a privilege to see the IPC15 program come together. We have contributions from 4 continents across different scientific traditions, operational contexts, and application needs. That is it's not just a number, it is a sign of how vibrant, diverse, and dynamic this community really is. And perhaps this dynamism also points to something larger. Maybe IPC should, in time, become the International Precipitation Society. Not as a section of a larger union, not as a national association, but as a truly international forum that would allow for dialogue across regions to happen in a more continuous, structured, and ambitious way. We have strong connections. We have an excellent set of institutions represented, both public and private, networks, missions, agencies, universities, and operational services. But we also have the opportunity to forge lasting connections across them, to create a space where precipitation science, data, applications, policy, and capacity building can meet regularly, openly, and globally. I believe this is within reach of this community, and perhaps by IPC16, this will be a challenge we have already begun to fulfill. In that same spirit, I am also very happy to announce that the revenues from IPC15 will be used to create a precipitation science travel fund for students and early career scientists. This is a small but important step towards making participation in this community more accessible, more inclusive, and more sustainable. The future of precipitation science will depend not only on missions, models, algorithms, and data, but also on whether we are able to support the next generation of scientists who will carry this work forward. Of course, IPC15 would not have been possible without the work, generosity, and commitment of many people, especially during a period that has not been free of uncertainty and challenges. I would like to sincerely thank all those who contributed to making this conference possible. In particular, I want to thank Dr. Effie Fofola Giorgio, Dr. Christian Kumaro, Dr. Pierre Kierstetter, Dr. Joe Turk, for their leadership, guidance, and continued investment in the future of IPC. I would also like to acknowledge the organizers of the pre-conference workshops, Dr. Daniel Waters and Dr. Shruti Upadhyaya, for helping us start this meeting with an important focus on training, methods, and community capacity. My special thanks go to all session conveners who helped shape the scientific core of the conference, and in particular, I'd like to thank Dr. Sarah Ringerud, Dr. Luca Broca, Dr. Jessica Sutton, and Dr. Chris Funk for their work and commitment. To our keynote speakers, Dr. Bart Kriegs, Dr. Gabriel Moldovan, my sincere thanks as well. We are very fortunate to have you with us, and we look forward to your contributions. And Dr. Viviana Maggione, I'm sorry. We have a science-packed 3 days ahead of us. We all hear about observations. We will hear about observations, algorithms, models, uncertainty, ground validation, extremes, applications, policy, private sector engagement, and the future of precipitation science. And it will be intense, but I hope it will be useful, open, and energizing. I would also like to thank you, Senor Armand, who will be helping us with all the IT things. His help is absolutely critical to make sure we have our remote attendees able to join us from all over the world. Practical note, we'll do our very best to stay on time, and for that we kindly ask all speakers, to both in-person and remote, to keep within their allocated time. This is essential so that we can protect the full program, allow space for discussion, and respect everyone's contributions. Finally, I want to thank you all for being here. Conferences like this are built by the people who show up, present, listen, question, challenge, and collaborate. IPC15 is yours as much as it is ours. I wish you an excellent conference, fruitful discussions, new collaborations, and a very happy stay in Coimbra, the heart of Portugal. Thank you. With this, we start our program with our first keynote speaker, Dr. Effie Fofola Georgiou. Thank you.
Thank you, everybody. As I said, the decade of 2020 to 30 is driven a lot by data-driven approaches, and this is what I decided to speak today about, which is work in my group by my former postdoc, Ranzi Lee and Clement Guillotin. So a video diffusion model for high spatiotemporal fidelity, satellite-based precipitation fields, and of course, uncertainty quantification is important. So the key points before I start the talk is AI has revolutionized weather prediction. We know that. The global satellite precipitation products, many of us have worked, and there is room for improvement. We're improving constantly, but there is still room because we have, many of us, quantified some issues that we try to address. Building our path strategically towards data-driven methods, and I mean it, not just put the data in a pile and steer it, and here comes out the output, but strategically see what is needed for the problem we try to solve is important. I will present our new results on the video diffusion model because we care about why video, space, and time coherence. I'll show you, we have developed a lot of metrics to evaluate the products and some takeaway points and what's next. So now we've all seen the revolution of AI for weather. We follow the news, ForecastNet by NVIDIA. They released in January 2026 at the MS meeting their Earth-2 family of products. We've seen the Google DeepMind, the GenCast, and so forth, Pango Weather. We've seen the ECMWF, their AI forecasting systems, NOAA, the AI global forecasting system, and so forth. Now, all these advances are great for weather prediction, but there is a difference between AI for weather and AI for remote sensing. AI for weather is basically emulate the physics, so I can get faster predictions. So it's saving on the computations for forecasting and producing large ensembles. And at the bottom there, you can see, for example, that GenCast from Google DeepMind produces global 15-day ensemble forecast at 0.25 resolution in basically 8 minutes. And not only one, but several ensembles because they're done in parallel. That's a big plus. Now, AI for remote sensing is a different problem. It's an inverse problem, it's under constraint, underdetermined, and we have to use as much information to constrain the problem. It's not prediction. This constrain what? The mapping of the indirect and diverse observations, which are the multi-scale references, sensor differences, different sampling, and so forth, to the target variable of interest. So it's a different problem. And the question is, are we taking full advantage of AI and the increasing volume of satellite data to improve global products? Are we so much kind of investing on that as much as the weather has invested? But of course, the weather investments and so forth have been done for weather prediction by companies like NVIDIA. Is NVIDIA going to get into that? I hope so, and I've been talking to them. But it requires different innovation and disciplinary knowledge than weather prediction. So the next generation of global satellite precipitation products, they need to resolve the fine space-time structure of the evolving storms at sub-hourly, probably sub-kilometer resolution, because these are important for hydrologic application, for hazard prediction, for security, decision support, and so forth. And while significant advances have been made in improving the spatial fidelity of satellite products, including, and we'll hear a lot, and we've heard already a lot of machine learning models, little or no progress has been made in the fine-scale space-time handshaking of the precipitation products. So what we've been developing is a video diffusion model that will produce dynamically consistent products and also ensemble members. So I'll go a little, like when I said strategically building on the machine learning, I mean it. And in previous presentations, I had, like 2018, I had a slide that I showed like, oh, what is machine learning? And it's like a pile. And what about, pile of data? What about, and then there was a question, what about if the output is not good? Well, you put more data and stir more the pile. That's one thing, but it's not all. There is theory behind the AI models, and strategically, we have to use the best. So we have shown, and I have some papers there, which are all some of your co-authors there, that we did elaborate analysis of the iMerge final compared to the MRMS, and we showed that through wavelet spectral analysis and localized transforms and so forth, and I don't see my sensor, that through a spatial coherence, which basically looks at what wavelength or what scales are captured well in the model compared to the ground truth, the large scales are captured well. And these large scales are more than 100 kilometers, more than 3 hours. But the small scales, they look energy. The products do not capture this well. And these are important features that we want to preserve. So we started on a path, in the last, 6 years or so, to introduce more information. And we said, well, can we introduce non-local information in the brightness temperature to provide more constraints to the problem? And yes, we build on that. We call it Beyond the Pixel. And it was a lot of work that was done in my group. And then, when we started using machine learning model, and this is a multi-scale, fully connected neural network that we developed a few years ago, we also went beyond the pixel in terms of the cost function to use root mean square error is not right, because I don't care about pixel to pixel, but I care about the coherence. So we introduced novel loss functions there that were unforced to preserve the wavelet spectrum and therefore the consistency across scales. Then we built more into, okay, well, we still have biases. Do these biases depend on the life cycle of the storms? So we use both the Lagrangian, following the storm, cloud tracking, and the Eulerian approach, staying in the ground and follow the sequence of precipitation time series. And we documented that, yes, the biases are more at the beginning of the storm and less in the middle and also at the end of the storm. And also, and you can see some papers there, the one that, the new event-based error model that is evaluate how well do I capture the beginning of the storm? Do I capture the maximum well? Do I capture the end of the storm? Do I finish too early, too late, and so forth? And we also try to explain with environmental variables whether these biases are basically related to some way to the environmental variables like CAPE and so forth. And all of this, led us to build a generative diffusion model that was in space only to produce ensemble forecasts, ensemble, retrievals, which worked very well, but nothing yet was done on the space-time kind of structure. That was basically the spatial structure, and we improved a lot. So the goal, in my mind, is to produce high-fidelity satellite products. You see this graph. In the horizontal axis is the spatiotemporal coverage from low to high. The vertical axis is the relative quality, again, from low to high. And we have the radar sitting on the top, very, high quality, but very low spatiotemporal coverage. We have the reanalysis product sitting at the other end that is almost global coverage, but very low quality. The satellite products stand somewhere in between, and we have to push this envelope upwards towards, eventually, in some years from now, high-fidelity precipitation estimates from space of high global coverage and high fidelity. So basically bringing resolution, accuracy, and coverage together. So now many of you know what the diffusion models are, and this have seen a lot of use lately. They were basically started much earlier than what we're aware of, based on equilibrium thermodynamics. And later, the famous papers by Ho et al. I have here cited more than 40,000 times, and later Song et al., again, very important. But what they do is basically contaminate your image with noise, and then they learn how to reverse this noise by learning these gradients of the log probability density function, the so-called score functions. And they've been very successful because also once you have contaminated your image and you got it basically to noise, you can sample from that space and invert backward and create as many ensemble members as you want, basically for free. So we used this model a few years ago, published 2025, last year, with colleagues from computer sciences and experts. So our input was microwave radiances at time t and infrared images 30 minutes before and 30 minutes after, like in a stack of images, trying to see whether IR can provide some temporal information that will improve retrieval. And the output was an ensemble of accumulated precipitation, in our case, 1 hour, before the instantaneous microwave pass, before and after. And the ensemble generation, of course, was the ensemble mean, the a posteriori Bayesian, and the ensemble spread. So we demonstrated the efficiency here. You see, for example, in the left, 4 examples of members of the ensemble set. You see the ensemble mean at the top, and I don't know here if, but the ensemble mean, of course, is smoothed out, does not have the extremes that the ensemble members have. And here to the right is the MRMS product. Visually, you can see resembles and a good performance. And of course, we beat the hell out of quantitative metrics. And here you see the dispersion of the ensemble. Another example here, and you can get the point that basically these are ensembles generated from the learning that I said before, from microwave and infrared images. Lots of metrics that we developed. For example, you see the probability distribution here. You see MRMS always as the ground truth. You see GPROF where it stands here. You see the ensemble member. Of course, it does not have, you can see the sensor. Oh, the sensor. Oh, the mouse is not showing there, okay? The red line is the ensemble member, which does not have, of course, it has squeezed all the variability. But then here you have the difference, we call it the diffusion-based precipitation retrieval, that is the blue line, actually the green line, very close to MRMS. And this is the ensemble, the probability distribution of all the ensemble members, not the ensemble mean. And then you see this Fourier spectra, again, reduced variability by GPROF. The ensemble mean, of course, reduced variability, but the ensemble members taken together very close to MRMS. We also wanted to see whether the ensemble member can be used, it's not obvious, but can be used for uncertainty quantification. And we saw in simple words that if I were to hide the ground truth among the ensemble members, you won't be able statistically to distinguish it. That is, this is the spectral coherence. MRMS versus the the ensemble mean is one of the samples between any ensemble member and the ensemble mean. So this is a test that is needed to make sure that I can use the ensemble for uncertainty quantification. But then we get into, this is just a static image. Then we are familiar, and this is from a paper 2021, where basically shows that something that we know, there is a lack of coherency. CMORPH tries to do a job there, but I have a lot of loss of persistence and so forth between the microwave overpasses. And you can see here, for example, the maximum rain rate that dips down between the exact microwave retrieval. So we have to work on that aspect, and this brings us to the space-time, basically, needs. So if I use, as we used before, the special diffusion model, I don't do it consistently in time, and as you will see later, it flickers. It does not know the previous time and so forth, but we need to introduce and constrain the model with that continuity. So the video diffusion model does that, and you can see here we put as input a data cube, I call it 10 hours of 30 minutes, that is 20 temporal frames that are given as input. We have a special extent here that was trained over the southeastern US, so it's a big area. We use 37 variables, environmental variables from ERA 5 also to help the learning. And we create 32 ensemble members, which are 10 hours at 30 minutes, 10-kilometer resolution. The loss function, again, is not root mean square error, but we use, many of you are familiar, the Wasserstein distance, which is an optimal mass transport that is much more demanding. And we trained a 3-year training period, and that takes 4 days. Needless to say that my postdoc Renzi spent a whole year basically working on that training and so forth, et cetera. The 4 days is what it takes, but to really decide the hyperparameters and so forth, it was a lot of time. I don't go through the architecture, but it's a diffusion, a UNet, and then the probabilistic residual refiner. The environmental variables, I will not list all of them here. I mean, I will not read them, but it involves topography from ERA 5 land, dynamics, thermodynamics, moisture, and cloud properties. And we trained it in the southeastern US for 3 years and 1 year for testing. The metrics we use are very rigorous, from space-time spectral analysis to really event statistics, and also the track the 3D structure, and I'll show you that. Visual comparison, you see here, one of the storms, MRMS, you're able to see that. This is what IMERT shows. You see that, they basically is much larger area, and the extremes are not captured well, and so forth. This is an output from the high-fidelity model that we proposed, but this is just visual comparison. The standard things, probability density function, the video diffusion model is on top of MRMS. We use the spectra. Now, what do you see there? IMERT, as expected, has reduced variabilities at small spatial scales. To the right is the small scales. That is, as I said before, we had seen that. Less than 150 kilometers, it has reduced variability. I also compare here with the image diffusion, I call it, which is, the isolated spatial, but not tracked in time with the video diffusion. And the image diffusion does okay in the spatial spectra, and the video diffusion does the best. This was the spatial spectra. In temporal, you see that IMERT, again, lacks variability at very small, less than 3 hour or so period. Very interesting to see the orange line is the image diffusion. So you see it has even more variability in the temporal small scales. Why? Because of the flickering effect. One image does not remember the previous one, and I'll show later, where the video diffusion does the best. Storm orientation, I saw here the MRMS, this is the northeast, northwest kind of orientation, and you see in the horizontal line the kilometer, which is the scale at which I'm evaluating the product. The red line means a lot of energy, power spectra, and you see MRMS has a lot of variability up to 20 kilometer scales and before, and smaller. IMERT does not capture this variability, and the video diffusion model, if you see the most left and the most right, MRMS and the video diffusion model are almost identical. Storm propagation, again, the speed, you see here the westward versus eastward propagation, And again, the same. Red means that I captured the orientation and the speed of propagation. I merge looks, lacking scale at small, does not propagate the small features, and the video diffusion model is, again, identical to MRMS. This is an interesting plot that I walk through the lines. So let's see the storm features. If I evaluate, so I evaluate MRMS, which is black, I merge is the blue, the image diffusion is the red, and then the video diffusion is the green, the last one, actually blue. So now, what do I see at the very large scales? 500 to 1,000 kilometers. They're all doing well, very large features. They're all captured the same. And what we see in the circle there is the speed of this propagation speed of these large features and the orientation. As we go to smaller scales, 200 to 500 kilometers, you see that the I-merge starts deviating from the ground truth. It has less speed, and the orientation is not captured very well. Let's go to smaller features even. 50 to 200 kilometers. Again, I-merge has much more reduced. It does not propagate the small features and also has lost the orientation. And you see there the orange arrow is very small because this is the special diffusion model only, so it does not know what happened the previous time or the time afterwards. Finally, we get to the very small features, and you see that both the special only diffusion and I-merge do not propagate the small features. They don't have the temporal information for the small features, where the diffusion model has been trained to learn this propagation. Now, event-based evaluation, a lot of metrics, the count of events, depth, duration, mean intensity, the peak to the mean intensity, peak timing, evaluate very short duration events, that is contribution of the less than 1.5 hours and more than 5 millimeters per hour events, and the intermittency, the dry spell to wet spell. And here are the statistics. I don't know if you can see the colors well, but you see I've marked the ones that are missed by I-merge. For example, I-merge overestimates the count of events, and we've seen that before. It breaks some events and so forth, and has more, identifies more as separate events, underestimates the storm duration, the average intensity, and underestimates the short extremes. The image diffusion improves in a bit in the short extremes, but the video diffusion performs the best. And this is because it falls. This is a normalized axis in that plot. So basically, you cannot distinguish too much the MRMS with the video diffusion model, where you see the, what line is that? The I-merge, the blue, that, as I said, overestimates the count and so forth. Let's move to then the 2D, system-based evaluation, the morphology and the spatial organization. Not time yet, but morphology. Several metrics again, the scale, the linear length of the system in kilometers, orientation, we fit an ellipse and we have the major axis relative to the north as the orientation, aspect ratio, the major to minor axis of the system, regularity is basically rugosity of the shape of the system, asymmetry, the geometric centroid versus the intensity centroid displacement, just to see where the peak is basically located within the 2D system. Concentration, the limited, this is almost what I hope you're familiar with, the Gini coefficient, the limited pixels contributing mostly to the total amount within the storm area. Radial decay, if I sit at the core and I see how fast it decays the intensity from the core to the edge of the storm, and core area, the fraction of convective core area, more than 5 millimeters per hour to the total area. And again, you see here the summary. The I-merge, and I have marked them in red, underestimates the core area. It underestimates the radial decay That is, it does not fall as fast as it is. It just keeps the intensity from the center to the outlet, not as fast decaying, and the concentration. The image difference improved on those, but not as much, and you see the shortcomings here, underestimation and so forth. And the video diffusion has the best performance. Let's move to the next thing, that is track the storms, again, at all scales. Metrics, a lot of metrics. The lifetime, the temporal persistence, track length. This is the Eulerian distance translation from the centroid over the lifetime. Straightness, the trajectory distance, the Eulerian distance versus the track length, that is as the storm moves around versus the straight line. The speed, the direction, the turning rate, how it turns, the small scale features especially, this is important. The difference in the area, frame-to-frame change of the area, and the frame-to-frame change in the maximum intensity. You see, again, where the eye merge kind of, again, does not have, as I said before, between the overpasses, it has limitations, overestimates the area growth and the speed, and underestimates the maximum intensity change from frame to frame. The image that is not aware of the temporal persistence does not capture the spatiotemporal organization. So as we building more on the metrics, you see the space-time evolution at all features there. And the video diffusion model was trained to perform better, and it does. And this was, of course, all the statistics was the out of sample, trained for 1 year and tested in 1 year. If I look at the precipitation tracks, this is one storm, and you see, so the storm is tracked and followed from the center of the storm. You don't see my cursor there, but it's okay. So you see that I merge is off. The black line is MRMS. I merge is off. It does not track the system. The diffusion model, both the image diffusion and the video diffusion do very well. And it's interesting to see the flickering, what I call, of the image diffusion, because again, it just goes like that. It does not keep the trajectory consistent and straight. Another big storm, this was the Hurricane Helene. It's interesting to see that again, iMerge does not capture it. The video diffusion has some bias. This is to the right, much more consistent and not flickering trajectory, but it has a bias, which I will not spend time, but I know where it's coming from. It has overestimated some of the extremes and has pulled the center of mass to the right, and these are things to work on. Now, we trained in southeast corner, but then, of course, if we're interested for global products, is how does it do? If you train it in one area, how does it do in another? And this is a lot of work. This is just the beginning to show you that in the Northwest, trained in the Southeast and transferred to the Northwest with what we ended up using a quantile matching only, it has underestimated the short extremes. Actually overestimated. So some work that we have to do there, and this is a project for the next year for us. So what's next? Transfer studies to other regions, not used in the training. That's important towards a reliable global product. How much do the environmental variables? We had 32, 37 of them. How, do I need all of them? So we have already started doing ablation studies that you exclude some and you see, how does it do? In fact, we've even tried to exclude iMerge altogether and see how the environmental variables would help me learn, trained with MRMS, and it's doing okay, but why not include iMerge? New advances, it could be used. The area of diffusion model is increasing a lot. Non-Gaussian noise schedule, so you can reduce the computational time and preserve the very extremes. That's something we will try. And produce hyper-resolution products. Now we produce 10 kilometers, but it's not difficult to do a hyper-resolution and produce 4 kilometers instead. The other thing is handle multimodal sparse inputs. For example, when we went to northwest, we don't have MRMS with high quality index in all pixels, and we had to deal with that. And this is something that I think in the future we have to learn how to benefit from opportunistic data that are not really gridded and available at all the grid points and so forth. And along these lines, I wanted to present some, just to make you aware, some recent work we did, which is fusion, the fusion models of observations that are not necessarily gridded in the same grid. This is basically sparse grids that they learn from fine scale, and they extrapolate this knowledge to grids for which fine scale products are not available. Another thing that is relevant, and I hope in the next years we incorporate that, this is a work of Clement Guillotot. So many times we have sparse data or limited data, and we try to detect a signal of interest, whatever that is. It could be a trend over time. It could be here, for example, seasonal signal from limited observations. And we have pixelized data. So here I show you a map when I have hourly observations at every single, and here we use a hair product or Chorus 404. So in every pixel, you basically try to identify your signal. Fit here a sinusoidal that will capture, here I show the phase of the seasonal cycle. So, of course, your data are hourly and you capture it well. Let me then sample this with a satellite that instead of capturing every hour, it captures every 100 hours or so. What do I see? This image. Because it's not able from this sparse signal or limited data to identify the seasonal cycle, so there's a lot of noise. Separating the noise from the signal or internal variability is something that is not trivial. Many times we see maps of trends, that here I have a positive trend of precipitation, but next pixel, 4 kilometers away, I have a negative trend. That's not possible. There is coherence in this signal. So the trick here that we use is basically take advantage of the spatial information, that there is spatial coherence in the signal and spatial coherence in the internal variability, and the two are orthogonal. So we use a Wiener spatial filter to basically adjust for the spatial coherence and extract the signal from the temporal data. So, long story short, sometimes we average the data, especially to increase the signal to noise ratio, but how do I know what average area to use? So we learned this from the spatial signature of the signal and the noise. And this is what you get. It's much more coherent if we apply that. The filtering, the spatial filtering is not uniform, but it depends on the region of interest and so forth. And I hope that even this information can be used within the machine learning models for the future. So takeaway points, a lot of innovations in AI that have not been yet used to their full extent for the inverse problem of remote sensing. Uncertainty quantification is important, and generative diffusion models are the way to go, and they're very fitting for that problem. Fidelity in the space-time organization, again, is important. I cannot do one frame at a time. I have to keep the space-time coherence, and therefore I believe the video diffusion model offers opportunities here and is just beginning to be used. In regions with patches of low-quality truth, for example, even MRMS, orographic regions, coastal regions, etc., we have to be more inventive. Probably masked video diffusion models or what's called in-painting and so forth could be used and offer opportunities. It's not completely irrelevant, the big issue of sensor-to-sensor translation, not for the L3 product, even for L1. And some ideas there can be developed within machine learning, of course, transferability. And the other thing is that the same as in weather prediction, industry jumped in a big way. Of course, there is much more there. They're going to make money out of basically apps for weather, but academia, NASA, and industry partnerships should be explored for the next generation of space-time, high-fidelity global products. And I hope this happens. We see the 2030 to 2040 era that somebody else, probably not me, will put in the IPC history, will be something that basically we take full advantage of all the data that is out there, from all the sensors, opportunistic data, and so forth, to their full extent. So thank you. We take questions?
Thank you so much. Are there any questions?
Yeah.
Yes, thanks, Abby, for that really amazing talk. I just wondered how the future modeling might work in kind of a real-time setting. Say that we're looking at an evolving student and we do that from now passing
Yeah, so you said that when I said it takes 4 days to be trained, once you've trained it, it's fast. So it could be used for real time. Now, it's not the same as weather. Our need is not the same as weather, but the 3-hour or near real time, yes, this is not a problem. The problem is the training. And the ensemble, the same as in weather, comes for free.
Thank you for the very nice talk. So you fine-tuned or you trained your model or MS, right?
So I trained the model?
You trained the model on the MRMS dataset, or you used it for...
Yeah, MRMS is the ground truth.
Yeah, so I wonder, have you tested if it also improves iMerge over other domains, such as Europe, tropics, etc., or you only focused on producing data over the USA? If that makes sense.
So if I understand, so this is the next challenge, transferability and generalizability of the model. That is, I saw just a beginning of here we trained it in the southeast. How does it do in the northwest without retraining it? And we had the challenge there, that's why I didn't show spectra. I cannot even do a spectrum because in the northwest, for example, we excluded the grid points at which MRMS had low quality. So we had to use variograms and so forth. But it did not perform too bad. We had to do just quantile to quantile mapping, which is, just a post-processing. But if I go to other areas, coastal areas, orographic areas, etc., that is a lot of work. The transferability is not trivial. But if we are talking about a global product, that will be the next challenge. And I hope that, not only there will be theoretical and more fundamental advances that we can take advantage of, because image-to-image transferability is easier, but the video transferability is a little more tricky. So we'll have to put a lot of time and thought into that. Yeah. Yeah. Yeah.
Thank you, Effie, for this very nice presentation. So you have pushed forward with the estimation. Okay, thank you. All right. You have pushed forward with the estimation of precip. You have also done a lot of development on how to validate those precipitation products. Well, I have many questions, but one I will ask is, overall, how many predictors do you have in your model, and have you performed an analysis to figure out which predictor contributes to what? For example, one of the metrics you have for evaluating the product is area. What product, what predictor contributes the most to the good performance of retrieving the correct area of precipitation? Have you performed this kind of analysis?
So you mean, okay, we have all of these evaluation metrics. Now, you said what environmental variable contributes most?
Environmental variables or IR or whatever predictor you are using, yes.
Yeah, so I have a hidden slide here, probably, or I removed to reduce the size, with what I mentioned, the ablation studies. It's very interesting to see. I remove moisture content, or remove microphysics, I remove this, and I have all the metrics. And some of them go up, some of them go down. That is, I lose accuracy. But yes, we've done this, and more work to do. When I remove microphysical parameters, what do I see deteriorating in my performance? If that were because eventually, you know, it comes for free to use as many variables as you want, but if you don't need them, and also not only, can we learn what environmental variables contribute mostly to all these metrics? So I don't know if I have or we have the time, but I can show you this eliminating, you know, strategically variable by variable and see what is the effect of that on the performance.
So how many variables do you have right now as input?
How much, what?
How many variables?
37. It's a lot.
Yes, it is a lot.
It is a lot. And some of them you can see that you don't need. Now someone can ask, oh, could it be that they hurt instead of helping? I don't think so. And it's interesting to see that if you see some of the microphysical parameters where you miss, for example, is at the beginning of the storm, in the event statistics, you start deteriorating a little, because we've shown before with the event-based analysis, some of the microphysical environmental variables are critical to capture the beginning of the storm and so forth. So it is a lot. We included them, but some of them can easily be removed without deterioration.
Effie, thanks. I want to follow up on that a little bit philosophically.
Yeah.
If you have a single variable that you're trying to validate, you end up with a single best method. Now that you have 7 or 8 different metrics, you could easily end up with 7 or 8 different schemes that each optimize one of those. From a user perspective, you know, I always get asked, you know, what's the best rainfall product? I say, well, it could be one of 8 depending on exactly what you want.
Yeah,
is that where we're going?
I see your point, Chris. Now, the thing is, in developing a product, first you have to evaluate it for a lot of things. And, you know, if we had the storm tracking and we visually see that, all these metrics that I was talking about, that is the orientation of that, how does it change, the area, how does it increase, the maximum, how does it, all of these are important, and that's why we did, this is like, you know, much more than one wants in validation. But I think this is the beginning. Now, if you wanted to say, well, I want to focus on this only, you could use a subset of these properties. But I think even for me to see the flickering of the storm, it goes like that when I do spatial diffusion, that in the previous paper we had spatial diffusion, it does great. But if I do it instantaneously and I look at the small cells, they just flicker, they move around. This is important, and we have to consider that. So all this, they are kind of excessive, but it's better to be excessive than not question how well my product does in all scales and dynamics of the scales. It's morphodynamics and morphology and morphodynamics at all scales. So I don't know if I answered the question, but one can use a subset of these variables. But I hope we all agree that as I look at the system to propagate, I want to see all the features where they are. And in the cyclone there that we had, the hurricane Helene, that we had a bias. That we have to evaluate more, but it comes from the center of mass, which the center of mass from the prediction or whatever is the weighted according to intensities. So it probably positioned in extreme, a little, in a different location, and that weights the center of mass in that location. But overall, all the other metrics tells me that I've done well overall of the structure. And we saw I-merge, it does not capture that. So this is the beginning. The paper, actually, we've not even submitted yet. We'll submit soon, but this is a lot of work that we aim to address this problem, spatiotemporal resolution and coherency, and a lot of metrics that hopefully we're going to publish in a package too, so they're available for other people to use and evaluate products.
Thank you very much. This was a great way to start the conference. I would invite you to continue the questions and the conversation during the coffee break. The coffee break is right outside. Just have to go straight ahead and turn left.
Oh, it's the Huffman Ringer one there, yeah. Perfect. All right. First, I want to really thank Vasco and the other organizers for helping George and I get this PMM-based session together, since we were unable to have a science team meeting the last couple of years and for the foreseeable future. So I'm excited to hear about everyone's GPM and PMM-based science. So the first talk of this session is actually George Huffman's talk. He is very sorry that he was not able to participate in the meeting, but I am happy to present this for him. And I'm going to start a timer for myself so I don't go over. This presentation is a report from a recent workshop. Basically, a few years ago, when I became the deputy project scientist for GPM, I started thinking about the future and sitting in on all the algorithm team meetings and realizing how closely correlated these global products that I was learning were being used globally by all kinds of different applications, not just for science, but by the insurance industry, by the military, by global health officials. I was really interested in how we're going to keep these products going when we reach the end of the GPM era. So I thought this is something that we should really get a bunch of experts together in a room to sit and talk about, right? So we created this workshop. We had it in March of 2026 at the University of Maryland College Park, and you can see all of the steering committee members listed there. Many of you are in the room today. We had 48 people in person to talk and 31 online. Basically, the steering committee narrowed things down to 6 general topics that we felt really needed good discussion by the precipitation community. And this was a very discussion-based workshop. So for each of these topics, we had a quick 10-minute introductory presentation, and then most of the workshop was in small breakout groups, just having a conversation. We're currently synthesizing all the results into a white paper, and it's from that white paper that these sort of general themes are coming from. So our first topic was applications, and we really talked a lot about the future of these global precipitation products having an application-driven approach, where we're really addressing the needs of the users. So some of the important topics that came up in our discussions were latency, and the idea that operational forecasting and disaster management have very different latency requirements than for things like science. And current latencies are often insufficient for some of these needs. We talked a lot about uncertainty as well, and the fact that users require tiered uncertainties. One uncertainty does not fit all. Expert users like things like PDFs and spatially correlated error structures, whereas others just want a flag that says, should I use this or not? But of course, all of these across the spectrum should be traceable to quantitative metrics of some kind. We talked about fitness for purpose in these precipitation products. Users need specific information that tells them what the best product is for their particular needs. And they have lots of different filters that are not just a general uncertainty. And the question was raised, do we need satellite products? Is that the best thing for users to use? And we felt that yes, satellite observations provide unique model-independent values, particularly in the less surface-observed areas. And this is a plot that sort of demonstrates part of the latency issue. So these are inputs to the iMerge product. And you can see they're coming in on various timescales. And it's up to 6 hours till we have 100% of all of these observations ready to go. The second topic was merged products in general. We talked a lot about the sources of things going into these products, that there's huge value to as many surface-based observations that we can get for validation as well as the analysis. We talked, of course, a lot about incoming commercial data and the fact that there's a lot of effort that needs to go into integrating these. And the workshop participants really felt that there's an ongoing need for agency sensors as a backbone of high-quality data. A hierarchy of these merged products, we want to have a long-term homogeneous climate record, but then separately we need a best available high-resolution algorithm as well. Merging strategy, there's a lot of interest in researching different merging schemes, And in particular, we talked about merging at level 1, so in TB space rather than level 2, where we're merging the actual precipitation estimates. And just that however we do this, we need to be able to trace errors and data back to their original sources. Enhanced content, we talked about additional products with other latencies, but minimizing confusion in the suite of products that we produce. And that, as we move into the next generation, we can move beyond things like precipitation rate and give other information as well. And then a big theme was that we need to talk about how we divide these responsibilities between the agency and commercial sectors moving forward. Machine learning was the next topic. Obviously a big topic, and there was a lot of great discussion about this. We talked about the idea of having an intercomparison project for all of these new machine learning algorithms that are coming out, to look at the robustness of the approaches, look at comparisons over a range of regimes, and perhaps using the IPWG SAT-RAIN database as a benchmark data set. And this could lead to things like hybrid approaches. There was general agreement that generative AI would be a suitable approach to represent retrieval uncertainties, which Effie talked about this morning. We also talked about the fact that machine learning requires, it's very data hungry. It needs large amounts of high quality reference data, so we need to continue making these observations. And as we start looking at the end of the life of the GPM Core Observatory, we need to talk more about how we're gonna do that. And also about how quickly new sensors, and in particular some of these shorter-lived small sats, can be brought in. The machine learning schemes typically run more quickly, but of course it's the training where things get a little trickier. The fourth topic was calibration and reference standards. We talked about calibration strategies that are going to have to be a little more dynamic and adaptable in the current era, given that we now have this heterogeneous constellation of short-lived satellites coming in and out. We need to talk about how we're going to calibrate these small sats and commercial constellations fast enough to make them useful for most of their lifespan. And then, in addition to those, we need to continue to have some sort of backbone, high-quality, well-calibrated sensor. We felt that that was really a non-negotiable to have a consistent constellation global product. We're going to have the upcoming JAXA PMM radar. At the moment, there's not a great plan to have coincident radiometer data flying with that, but we really wanted to push on that that's a valuable asset moving forward. We felt having something in inclined orbit is really important to sample the diurnal cycle and act as that calibrator. And while machine learning can accelerate calibration, the workshop participants felt it shouldn't replace physics-based active calibration. And then we talked about things like, a government NIST traceable warm load to also standardize the TB calibrations across all of this dynamic constellation of instruments. The fifth topic, constellation and sampling strategies. And just to sort of give you a sense, the figure on the right there shows the equator crossing times of the current constellation, so you can kind of see how they're spaced out. And then the map on the left is just a snapshot of a typical half-hour coverage by the current constellation from iMerge. So you can see where you're getting information content from passive microwave sensors, and everything in the in-between gaps is filled in with a combination of morphed passive microwave and current hour infrared from GEO. So the workshop participants emphasized that future constellations should be designed based on observation interval rather than specific orbits. So, Tomorrow.io, for example, has this combination of some inclined and some polar orbiters to give them full coverage. Observing short-lived extreme events and storms require, hourly or so observation intervals, and also to adequately resolve the diurnal cycle. Passive microwave sensors give us the high information content, but of course we really need that higher temporal resolution geodata at the same time. And as we're shifting to multi-channel geo algorithms, this gives us even more information content to use there. International and commercial collaborations are, of course, extremely important as we talk about the constellation. And the final topic was validation. The workshop participants felt that validation needs to move beyond statistical metrics to sort of look at validation as a function of applications. So this is going to require performance within applications and looking at different metrics in that context. Expanding the global footprint, people talked about the danger of chasing accuracy only in places like the US, where we tend to calibrate everything too because we have a lot of data there. But of course, that doesn't tell us about the full global variability. And sustained long-term ground observation networks are often more beneficial for algorithm development and level 2 validation than these sort of short-term snapshot field campaigns. So some final comments. Across the workshop, these are the things that came up most often. You know, extremes, extremes, extremes. We're hearing that all the time in every context. Also orographic precipitation, phase, everything you see listed there. Just a note, you know, every month we get a new forecast based on the solar cycle of how long the GPM core satellite is going to last. And the current projections have us starting to slowly drift down in 2031 and the end of the mission in 2034. So that's it. I can take questions, even though this, I'll be George, if you want to ask any George-based questions. And if not, we can move on to, I think Lisa is the next speaker. Oh, somebody has a question? Yeah, go for it, Pierre.
Thank you. Thank you for this summary of the NASA workshop that happened in March. That's very nice to have that overview of the requirements for future precipitation products. Well, there are several aspects here. I think we will discuss during this conference, but I see a very nice connection with FE's previous presentation where FE provided, you know, a whole new suite of metrics to target characteristics of precipitation systems that we wanted to retrieve, and that addresses directly one of your requirements here. So any comment on that?
Absolutely. I think it's very complementary. So, you know, a lot of the things that the workshop participants were discussing are happening, and that's why it's important that we, like I said, get together in a room and talk about the best ways to do these things. So yeah, the recipe is there. Anybody else? All right, take it away, Lisa.
Try to time myself. Okay, good morning, everyone. Before we start digging into the core of the science of the GPM mission, I wanted to bring some fun and just introduce this project that I've been leading for about 4 years now, about the GPM mission and how to bridge the scientific data into the classroom, so for teachers and educators. Vasco and Andrea Portier helped me with this, helping with slides and a little bit thinking about how to develop the program. This is the team this year. There's a lot of names. So those are mostly the teachers that were involved from different schools. I'm going to talk about the Italian side of things because I was in charge of that one. Vasco developed something for Portugal as well, so you can ask him about that part of stuff. This program started as a spin-off of the original GPM mentorship program that Andrea and Vasco developed 5 years ago, I believe now. Since 2023, we dedicated a part of this program to teachers and educators. We want to provide resources to teachers to pass the scientific knowledge of the Earth's water cycle, weather, and climate to their students from a water resource perspective. So there's a GPM expert. In Italy, that expert will be me. In other countries, for example, Vasco, etc. And we just teach the teachers how to use the data and how to transmit this knowledge to their students. Just a little bit of the evolution of the program. I started with 9 schools, 9 teachers in 2022-23 school year, and now I have about 28. They go from preschool to high school, about the same amount, I would say, a little bit less on primary school, but every grade is very happy to participate in this. It was a little bit challenging at the beginning to understand how to put the content in all these different levels, but we succeeded and everybody's happy about that. So the structure of this program is in 2 parts. The first part is 3 online lectures. I gave them information about the water cycle, meteo and climate, and the GPM mission. And then in the second part, the teachers use this information to put together a project with their students. And here I have some examples of these projects. This is an example taken from the precipitation education website of the GPM mission. Precipitation towers, they take monthly precipitation climatology in a specific location around the world. They do histograms with towers, and they transfer it to an actual plot on paper. So they learn how to plot data. And then this is a high school, and they deployed rain gauges in the backyard of the school. This is a agriculture-based high school, so they learn how to be agricultural people. They measure daily precipitation accumulation. They put the data in spreadsheets. They use also the data from local stations, and on the left bottom you see the weather service person explaining to the kids how to use how the weather station is built and how to use it, and then they plot all the data they collect. The same school does also chemistry, so they studied the effects of acid rain, and also in the two posters there is the English as a second language type of lectures. Oops. Then other schools did use our slides to explain how the GPM mission and satellite work, and then while they were doing this, they built a little satellite model on paper. They do also activities on Earth Day. They do Earth Day celebration. This is an example in 2024, and this year I had the opportunity to actually visit them on Earth Day, and I gave a presentation. Some of you might recognize my snow plots up there. So I bothered them with my snow stuff also. And you see a picture of the teachers. They are always very, very happy to be involved in this kind of programs. This is another example. They do comparisons, long-term comparisons on different months to see if there's any trend on precipitation. They can't find any, actually, but they can find trends on phase. And this one was a new experience for me as well. The Italian teacher helped the students to put together a podcast episode. So they put together all the questions, and I got to record this podcast episode during my visit in April. Oops. And this is a kindergarten school. They collect water in their backyard. They see the plants, and they understand the importance of water for growth of their little seeds. And they understand how of a precious resource water is, and how it should be used responsibly. And here, another ton of examples. On the top right video is a coding class in preschool. They went through the water cycle with a little robot that they had to code to actually get through it. So that was pretty fun. And I visit schools when I have the opportunity. The students learn how to present their projects. I present some stuff from my side about their project or the topics they want covered. And usually questions are countless. They span from how satellite works to how to become an astronaut. Of course, I can answer some questions, not all of them, but it's a fun thing. So just to summarize the importance of this program, this provides the content about the current important topics, such as the water cycle, climate change, and bridge the science and shows the real world impact of it. There's a lot of excitement and curiosity, and from my point of view, since I'm a woman in science, I highlight the women in STEM, and I present myself in a role of a woman in science. And then it demonstrates the value of NASA data, not just for us scientists, but also, for little kids. Contribution to more GPM resources, supporting education community, because I didn't say that, but most of the material is in English, and that can be a barrier for countries that don't have English as primary language. So the goal is to put together material that can be used, for example, in Italian or Portuguese or other languages. And we want to understand the needs across the K-12 space. And bottom line, it's so much fun. When I go visit, I have so much fun. And that's all. There's just some pictures from the last visits. Everybody's pretty happy, and I was too. Thank you. Curiosity more than questions. This one, Viviana.
I'm just curious to know how expandable this is. If I want to do it in France, can we help?
Nicola. Yeah, just repeating, I don't know if online they heard that, but I'm just curious to know how expandable this project is and whether you're interested in expanding it to other countries, even more schools in Italy or even in the US, because I feel like we could do it there too.
We can definitely expand it. We have the deck, the slide decks, is 3 lessons, so each country should just translate them in their own language, and that's the bulk of the work. And then the projects, really, I don't make the projects. I meet with the teachers, I give examples, and then they develop it based on their requirements for their school year, what they need to do in their program, and then what kind of students they have, stuff like that.
And I'll just add to that, this is a great example of what can be done internationally and nationally. On the part of just even resources, I cannot get credit, but before she retired, Dorian Janning, she made a tremendous amount of resources that are still online. So if those, for the K through 12 audience especially, feel free, Andrea Portier, to reach out, because that is part of my job, to build those resources. So like Lisa said, we have the slide deck that she has. We have tons of other resources that could cater to audiences, with the exception of translating it into a language that would work.
All right, so that's a question for an idea for the broader community here, but it seems, so Lisa, a question. This is hybrid? Is it online? Is it in person? How does it work?
It is kind of hybrid. The lectures are online only, because I'm, of course, in the US. I can't just go there and meet all the teachers. So the lectures are online, and I usually do them around November time. So sort of the first part of the school year is 3 weeks, once a week. And then I record them, so if any teacher has meetings or stuff, they can, catch up. And then starting January, usually, I give them time, January to July. It can be a 1-hour lesson. It can be a 6 months program or project. It doesn't really matter. What matters is the student touch this. Okay. The student hear about, satellites that record precipitation.
Okay. So the science advice, sorry, Vasco, how we called again the Science Advisory Committee of IPC? That's Effie, Chris. Anyway, so we are concerned about the future of IPC. And I see that the pre-conference workshops that we organize online are something we are thinking of that can continue in the future and maybe can expand the involvement of the precipitation science community global-wise. This initiative that you are presenting, Lisa, could also be another prong more on the education side of things. So just food for thought, but this is something that we could consider as a community as we are evolving, and we need to think about the future.
Yeah, if you speak a language that is not just English, contact me and we can coordinate on this. Thank you.
And if I may answer Pierre as well, I think if IPC had a national representative in different countries who could make this connection between the experts and the local community, I think that would take us a long way.
All right, thanks, Lisa. I am not sure how to make this PDF into show mode. I'd like to introduce Nicholas, who's going to talk to us about quantile regression in rain retrieval.
You don't think, I don't know. It's Windows, I don't know anything about Windows.
Here.
Thank you. Good morning, everyone. So I will talk a little bit about quantile regression in rain retrieval. This is the consequences of a talk we had with Pierre-Emmanuel about 20 years ago. After working for a long time on Bayesian retrievals, in 2020 I started to work with deep learning for rain retrieval. So I will briefly explain what we did with the rain retrieval using deep learning. This is an algorithm called DRAIN for deep learning rain. The algorithm as it is right now works only for GPM core. And it uses collocation of the DPR product for the rain as a target and the brightness temperatures from GMI, namely the 89 and the 37 gigahertz as an input. Purposely, we did not use any auxiliary data. We really kind of use only the brightness temperature for from GMI, with the idea that there is a lot of information in the brightness temperatures, and auxiliary data could always be a little risky. I'm not going to go too much into the implementation of the algorithm, but what's important is we chose as a loss function a quantile loss function. So basically, the quantile loss function will retrieve not only one rain rate per pixel, but it will retrieve the cumulative density function of rain rate in the pixel. Basically, if you take quantile 50, it's the median, and you should have statistically as many rain rates, real rain rates under your quantile and as many over. And there is no a priori information on the shape of this CDF. The algorithm itself is a very simple algorithm. It's an architecture of a network that's very classical. It's just a UNet. I'm not going to go too much into the details. You use the brightness temperatures as input. You train to retrieve the rain from DPR. And once the training is done, you use the network for inference, and you get the rain in the whole swath of the GMI. This is an example of a retrieval. There is indeed Yes. So this is a drain. It's the median. Oops. It's the 50th quantile. This is the DPR. This is the DPR. This is GPROF. We have differences. We think we're better than GPROF, but I'll show you why in a minute. Sorry, Chris. This is another example of something that's usually a little harder to retrieve. It's kind of more stratiform precipitation over France, and we compared also, we validated with the Météo France mosaic. But this is not the interesting part. I think it's what's interesting is how we try to exploit the quantiles. First thing first, the algorithm gives pretty good results, but in reality, if the quantile loss function really helped train the network, the training is not perfect. And this is a quantile coverage histogram. So basically, you take your training database, you retrieve rain on your training database, and you look at where the real or the DPR rain rate falls into the quantile. And you get this kind of histogram. If the training was perfect, all the blue bars here should be at 1% because we have 99 beans of interval. And what you see is that it's not true. There is definitely a lack of occurrence here and an over-occurrence on the other side of the spectrum. And here, slightly above 100 is actually all the occurrences where the retrieved rain rate, or rather the DPR rain rate, was above the 99th percentile. And you see that there's a fair amount of occurrence, about 4%, meaning that we tend to still underestimate the rain, and particularly the extremes. If you look at histogram, a 2D histogram, you have the DPR here as a reference, you have the GPROF here. Same thing here for the quantile 50, the median of drain and DPR. And this is the difference in 5 degrees box between DPR and GPROF and DPR and our median, the drain median. You can see that the difference, namely the difference between GPROF and drain, is that because we don't distinguish between land and ocean, we have a much more consistent error structure, while GPROF has a really different structure between land and ocean because it's basically two different algorithms. But still, we have a strong underestimation. But because we are using quantiles, we can explore alternate estimators based on the quantiles. So for instance, we can do the average of all the quantiles, which is because of the distribution of rain, which will be kind of higher than the Q50. And indeed, you reduce the bias. It's still a little underestimating, globally underestimating, but it's a little bit better. You can also, with the coverage histogram, you can look for the effective median of your distribution. And we figured that it was around quantile 70. So if you use the quantile 70 as the optimal estimator, you can see that you're getting closer to the XY axis. There's still a little bit of underestimation, but your error map or your bias map is kind of much more balanced. Last estimator that we tried to build was histogram adjusted. So we know that the CDF of the retrieved CDF is the orange one here, and the blue CDF is the CDF from the DPR. And so you can kind of correct by some sort of histogram adjustment your best estimator. And this is what you see here. You see that now we're kind of well balanced between the on each side of the XY axis. Unfortunately, this occurs at the cost of a lot of spreading. And your global map is much more balanced. And as I said at the beginning, I'm going to skip that. As I said at the beginning, the idea in the using quantile, besides improving the training of the network, was also to try to see if we could use the quantiles as a kind of proxy for the error on the retrieved rain. To do that, we tried to, because we have a distribution, it's kind of hard to compare distribution with a single value, so we used the CRPS. CRPS is a measure, as illustrated here. CRPS is a measure of how distant you are from a single value. Ideally, if your distribution is really kind of narrow and has a very precise peak, the pink area here will tend to be close to 0. And the more this area increases, the more uncertain somewhat is your retrieval. And the CRPSS, which is the continuous ranked probability skill score, which is something that is used a lot by model people, is trying to measure if you do better than the climatology, basically. Oops. You compute the distribution of rain from the DPR in like grid boxes, and you compute the your CRPS from the output of drain, and this little skill score kind of gives you a sense of how good are your quantiles, your retrieve quantiles. And on this, you can add a threshold. So basically, how much a certain amount of rain your skill score can be computed. And we see that if we take everything, basically, I mean, we just put a threshold above 0.1 millimeter per hour, the score is negative. That means we're not doing better than the climatology. So it would be better if we take everything. It would be better to just use an average rain rate. But as soon, obviously, as expected, as soon as you start getting into the higher rain rates and you kind of increase your threshold, the quantile kind of become more reliable, your retrieval becomes more interesting and better than the climatology. However, if you go to the really high rain rates, they become really rare, they're hard to train, they're hard to learn by the network, and your performances will kind of degrade. That's about it. Just a few concluding messages. I think I agree with Effie. I think the machine learning is an absolute breakthrough for all the stuff that we're doing here regarding satellite and rain retrieval. And this is due to the fact that we switch from pixel by pixel retrieval to image retrieval. And so we really kind of, the machine learning will really take into account the spatial structure of the input and the output. And that's something that we felt for many years contained a lot of information. The spatial structure of rain is very specific. It has a lot of information, and machine learning really kind of allows to connect the two things. For the moment, at least, the quantile retrieval, besides improving the training, they're not very conclusive for uncertainty assessment, and that's a bit of a disappointment. One of the difficulties with the machine learning is that we can easily train a network for GPM core, but for the other satellite, it's a little bit more complicated. We're working on domain adaptation using flow matching or diffusion model, generative model, basically. That seems promising, but it's not done yet. And we're also developing the same kind of algorithm for IR, but the transfer function is weaker, so we're probably going to go toward hybrid model, which will mix generative and deterministic models. And that's about it. Questions? Sorry, I thought it was a 15-minute presentation. I had to squish it in 10.
So maybe it's not super relevant, but because with DPR you already filter a lot of snowfall that doesn't detect, but if you don't use any auxiliary data, are you sure it's rain, or do you mean precipitation with rain? Or did you do any analysis on what the phase is?
Okay. So we do not distinguish between solid precipitation and liquid precipitation. One thing that we saw is that when we do supervised training, so basically we match the DPR and the brightness temperature, the network is able to extract features from the brightness temperature images that are robust enough to be able to retrieve snowfall. If we do unsupervised, like classification over the brightness temperature, then we cannot distinguish between snow on the ground and snowfall. But when we run drain, even at higher latitude, we didn't include a flag for snow or liquid precip, or solid or liquid precip. We could, but it works 99% of the time, 90% of the time. Okay. All right.
Thank you so much. We'll move on to Ali. I can figure this out here. Nope. I'm failing. I don't know what any of these words are. Sorry, I'm PC illiterate.
Good morning, everybody. So this story starts when I had one of our students that asked me to come say, can I have an internship with you? And her name is Amalie Resbok. And Amalie was my intern for the summer of 2024. And you can see the picture. Amalie graduated a year after, and she's currently a master's student at the Virginia Tech University. And I would like to acknowledge our other co-authors, David Wolf, our principal investigator, Chip Helms, the person that I stop by in his office every day, ask questions, and our group of folks who was hands-on on the data or the field, Jason Pippett, Alexei Chivot, and Mike Bronlid. And also our colleagues from the University of Connecticut is Diego Serrai and Brian Flipiak. So the classical motivation for our study, we are in the precipitation conference, and we know that it's one of the two components of the water cycle and global climate and fundamentally important in our daily life. Now in this talk, I'm going to focus that we are going to try to evaluate rainfall events of two publicly available and heavily used precipitation products. And both are operated by NOAA, the stage 4, and we heard a lot already this morning, MRMS, and I'm sure gonna hear more. And you can see that two images in the bottom, I just pulled from one of the private weather site, and again, they were looking at the 6-hour and 24-hour totals from those two products. Just a little bit brief information about these two products. The MRMS is primarily a gauge-adjusted radar product at 1 kilometer spatial and 2-minute temporal resolution. And from our perspective, it's very important because it is indeed used as a ground validation product for GPM level 2 and level 3 precipitation estimates. In that sense, we are evaluating our validation product per se. And stage 4 is a mosaic of the multi-sensor precip estimate, which generated by the river forecast centers. It's an hourly product at 4-kilometer resolution. It benefits from the radar, gauge, satellite, as well as MRMS. I have a long story with that, but I don't have the time to explain about more stage 4. The uniqueness of this study, what the novel about it, is this. So starting 2024, we have been assembling Pierce platforms. And this, you see the picture on the right. This platform has dual tipping bucket gauge and parsable distrometer. I want to emphasize the distrometer because that brings the novelty to the study. And this instrumentation package is, we've been putting together, and it's basically a solar panel and the cell phone modem across the United States for the GPM-funded institutes and minority institutions. The parsable here is critical because it, measures the size and fall velocity and rainfall and reflectivity drive products, but is also a present weather sensor, allows us to separate the frozen precipitation from the liquid precipitation, which is we are focusing in this study. If you look at the literature, you will find a large number of studies that in the stage 4 or MRMS evaluations, but they did not have a distrometer, which much better way you can define the event. You don't necessarily gonna rely your so-called daily totals, monthly totals. We know rain does not stop midnight. Rain does not start at the end of the month. That is critical to define in terms of the event. And so phase identification, we rely, of course, in the parsable. Event duration, we rely on the parsable, as well as the maximum rate, precipitation rate. The gauges are great for the event totals. So this is our map where our stations are located. In this talk, I'm gonna look at the 3 sites on the west and 3 sites on the east of the United States. And there are multiple sites in our eastern shores. So before we move in to evaluate those products, you must look at your own product, how good you are. So I'm just showing you from the 2 sites. In the top row, you are gonna see 3 images where you see that each point is an event rain total, parsable versus tipping bucket A, parsable distrometer tipping bucket B, and parsable versus tipping bucket A versus tipping bucket B. And that's your kind of your anchor. That's your basic. The bottom shows one of our interesting sites. We were in the Chesapeake Bay Bridge Tunnel. I mean, literally, you are in the Atlantic Ocean. And you could see that my parsable distrometer were underestimated, the precipitation in each of the events. You can clearly see that. This, you must show this before you use this site as the truth. This is critical for the research. So my next slide is looking at the 6 sites. X-axis are the tipping bucket gauges, and Y-axis are the MRMS. How we are doing across the country at different climate, at different elevation, coastal region, inland region, all around. An interesting point here, I'm going to rely on my normalized mean absolute error. So one of the things is this is the 1 year of data, and thanks to Pierre who provides us the GV MRMS data and how they look like for a given site. The question is going to ask us MRMS versus stage 4. Which one I should use? So my next plot is going to be the stage 4. So if you look at here, between the 2, and if you look at your normalized mean absolute error, 3 out of 6 sites, MRMS doing better. 2 of the sites, they were about the same. That was a 1 site, stage 4 was doing better. And we figured out that that particular site had some rain events. The radar data was not high quality. They had a differential reflectivity were extremely low, was creating very high rain rates. And that was the site that actually happened some other site under the same radar. These are the locations where they did not have a gauge for a good adjustment on that. As I said, that uniqueness of the study having the parsable. So I'm approaching from what I call it, farmer's approach. Farmers does not need to know how this product has been created. farmers need to know which one they are going to use. Farmers doesn't have a rain gauge. They are going to rely a precipitation program. So what you see here, the top row is the MRMS and bottom row is the stage 4. For 3 sites, we are looking for a little bit in depth because we have the parcel. So you have seen 3 colors in each plot. Those colors represents in terms of the rain totals less than 5 millimeter. Rain totals were 5 to 10, and rain totals were more than 10 millimeters. So we are defining like a subdividing our database per se. Typically, in this case, for instance, we find out that the events has a higher accumulations had a better performance. Now, next one, we look at the conditional rain rate. When it's raining, it's a light rain, moderate or heavy rain. How it's been performing? Farmers would like to know that in this case. And typically, the events has the less rain rate, the lighter rains, did not do well. You had higher normalized mean absolute error. The same thing also we looked at in terms of the event maximum rain rate. So we are looking at the one event in 1 minute, whatever the maximum rain rate. Less than 10 millimeter per hour, 10 to 50, or above 50 millimeter per hour. Again, events that had less than 10 millimeter per hour had a higher normalized mean absolute error. And finally, we looked at the duration. Events has less than 2 hours, events between the 2 to 5 hours, events longer than 5 hours. The longer events has less error that we find out. So this is the basically essence of the story that we are giving to you today. This was feasible because we had this dystrometer attached to our package. So my conclusion slide gonna come in here. Overall, MRMS performed better than stage 4, but suffered from erroneous radar data as we spoke. The second one, that we find out that events higher accumulation and longer duration had a lower normalized mean absolute error. Now, as a next step, we have ongoing studies. Number 1, we are trying to evaluating using again our grant-based data for iMerge and its friendly competitor, GSMAP, our Japanese colleagues' product. We are also evaluating the reanalysis products, ERA 5 and MERA 2, under the same event totals. And the picture on the left is my intern just started 2 weeks ago. Alex Zainski came from my alma mater, University of Illinois, and my former advisor wrote to me email saying that Alex is brilliant. So we just started 3rd week. I had so many interns and the students I work with. Actually, one of my former intern who started with me has been, again, told by the advisor, brilliant, worked with Chris Kumarov, having had PhD with him, Joe Munchak. So he was we'll see what Alex is gonna bring to the picture on this. So Alex is gonna work on evaluating the regional and the global products, like he's going to evaluate the HER, NAM, GFS work, whatever he can do. We are in the week number 3 out of 10 weeks program. We'll find out. I'll let you later how he's going to perform. Thanks so much. I also have the poster for the discussions that we might have about more broader about this research.
We're a little over time, but one quick question for Ali. Chris?
Oh, Chris wants to ask a question.
Thank you. So, working a lot with data, I always look at data. Can you tell me how a Parseval radiometer can see 30 millimeters of rain that fell between 2 and 5 hours, and MRMS sees no rain? That happened in Prairie View, Texas.
Yes.
Your plot.
Yeah, so definitely, as I said, everything here, all my event definitions based on the parcel. That's the thing. And we do know, based on how many minutes it's rained, how the MRMS perform in that window. So if you are interested about the 2 to 5 hours rain or less than 2 hours rain, we just subdivided the different regions because to enough sample.
I know. Your plot had a case where the Parsival saw 30 millimeters of rain and MRMS saw nothing. I'm asking whether that's real.
A good question. You know, it could be real, based on what I have seen sometimes. That depends where you are also looking at this. And
Prairie View, Texas.
This is our, okay, that site we did not have a major issue so far. The major issue, as I told you, with MRMS is the bad radar data in the absence of gauges. That's what we figured out. Apparently, for some reason, stage 4 forecasters were able to overcome because there is a personal influence right there. That's why I said, how come the stage 4 did not doing bad? They are also looking at the same thing. But stage 4 has a forecaster apparently overcame that issue. They figured it out, this radar data is bad. MRMS is more automatic, like one for all country, and got that.
Okay, thanks. I'll talk to Pierre.
Okay. Okay, thank you.
Special representativeness.
Okay.
All right, thanks, Ali. And now we will finish up the session by finding out what's going on over at WeatherStream. If I can get this to work. I'm useless at this. You should just come up every time.
All right. Hello, everyone. I'm Michael Marquez. I'm VP of Engineering at WeatherStream. This talk is just going to be a little bit of an overview of the status of our GEMS 2 Amethyst satellite that just launched, and a little bit about our company and what we're looking to do in the near future. So, a little overview of WeatherStream. It started as Orbital Microsystems out of the Center for Environmental Technology Lab at the University of Colorado Boulder. We launched our first passive microwave radiometer. It was purely a 118 gigahertz temperature sounder in 2019. You can see there that microwave images of Typhoon Hagibis off the coast of Japan. Then we got a contract for the Air Force Commercial Weather Data pilot project to build the GEMS 2, which is the one that just launched here in late March. And we're currently working on commissioning that. That's a picture of that satellite just above the 2023 mark. And we have a few different sort of sensors in development. None of them really close to launching right now, but I'll just give them mentions. GEMS Pearl is a precipitation imager style instrument. It's a conical scanner, similar to Cover channel set. GEMS CZ is the design we did for SIMBA, so it's sort of an ATMS-like follow-on backbone sensor design. And GEMS Cubic was developed for the AOS project for the Atmospheric Observing System to study liquid water path. Right now, the one that's going to launch in 2027 is another one of the GEMS 2s. That's GEMS 2 Barrel, and that's in the middle of production, expected to launch in the middle of next year. So a little more about GEMS 2 Amethyst. It launched end of March on Transporter 16. We're power positive. We've deployed the solar panels. We have a ground system with two-way communications at 5 different ground sites. I think that's important because of the latency aspect. We expect to be able to get, with these 5 ground sites, average sub-hour latency. About 70% of our data will be on the ground within an hour. And we're considering adding some more stations in the southern pole to bring that all the way up to 90+% sub-hour latency. And so here's some more details about the GIMS-2 payload. It is a combined 118, 183 gigahertz radiometer. The 118 provides the temperature sounding data, and the 183 provides humidity sounding. You can see our resolutions are 22 kilometers for temperature sounding per pixel and 16 kilometers for the G-band humidity sounding. It's got a 1 hertz scan rate with a 2,200 kilometer swath width. Consumes about 15 watts of power. It launched on a 6U CubeSat built by GOM Space. Our ground systems are utilizing KSAT. So our target is sub 1 hour latency for 95% plus of our data. There's just a few spots over the ocean it's hard to get any ground sites for. A little bit about the channel set. For the temperature sounding, we do have some very high sounding channels up in the upper stratosphere. That was a desire for the Navy, I think for icing condition at high altitude. On the left, you can see our channel set responses with a zoomed in. That's a symmetric logarithmic plot. So the channels towards the edges are quite wide, whereas the channels towards the middle are very narrow. So for example, the outermost channel is a 10 gigahertz wide channel, has a very low NEDT, whereas the narrow band channels in the middle are high atmospheric sounding, but have relatively high NEDTs given the narrow bandwidth. The 183 doesn't quite go as high, but we do have some good surface contributions, and we measure in the troposphere for the humidity soundings. So a little bit about the noise performance. This plot shows the channels for the 118 on the left, so that's the temperature sounding from the wideband surface channels on the left to the narrowband high altitude channels on the right. And then the channels 16 through 24 are the humidity sounding channels. The key thing here, I think, to look at is we have basically 3 plots: the theoretical based on the TSYS bandwidth and integration time, and then our actual measured standard deviations for a short time scale as well as a long time scale. So for the 118, you can see it matches very well for the short time scale, but the standard deviations over a long time scale are slightly elevated for the wideband channels. So that's indicative of a small amount of striping noise on those channels, but otherwise they're performing quite well. The G-band, on the other hand, you can see there's a separation basically across the channels. There's a little bit of an excess white noise on those channels, so their NEDT performance is a little bit degraded. That was an issue to do with the receiver design in the system, and we expect that to be fixed for GIMS-2 barrel. We've also added some additional capabilities in terms of the striping noise removal to the GIMS-2 barrel. So we're very excited for that next payload to launch to see those improvements. So this is the first light from the GIMS-2 Amethyst. You can see here this is uncalibrated data. We're still in the cal-val procedure, but I thought it'd be fun to look at. You can see some structure in the 118 data. The 183 has some sensitivity to the S-band radio. So we're planning to mostly leave the automatic beacons off to minimize where the data is contaminated. But that's what that bright sort of maroon stripe there is during a TNTC pass. So there's some issues with self-RFI, if you will. Yes. This is just a block diagram of our ground processing. So the L1B data we're planning to have freely available for evaluation and scientific research. Our pipeline here, you can see data comes in from KSAT. We process it from our level 0 all the way up to L1C. In addition, we currently generate pseudo data based on the ERA5 reanalysis using CRTM, and then we compare those to look at basically biases relative to the numerical weather predictions. And then we also have retrievals. We're implementing mirrors. We need to do tuning on that once we have some more in-orbit data, but we have mirrors running in our processing pipeline to produce retrievals for humidity and temperature, as well as precipitation. And we are also basically accelerating that by training a machine learning model to accomplish the same task. Oh yeah, one other thing. So we are delivering this data as part of the Air Force CWDP contract, and we are looking forward to the noted NOAA data buy coming up to sell this data. So So yeah, just an overview of our CalVal efforts. So we have the observed minus background with the ERA5 and the pseudo data. We're looking to do some studies against radiosondes to see, against in situ data, how well we're doing. And we are planning to do double difference against the ATMS and other backbone sensors such as MWS. So for our 2 retrievals, we do have mirrors. It does need some tuning. So there's an example of using pseudo data. So we generated pseudo data based on the sensor CRTM coefficients and then ran it back through mirrors to see if we got the same result as was expected, given we generated the brightness temperatures from the Area 5, and that's working well. So we'll have to see how well it actually works in practice. And then we do have a machine learning retrieval single pixel that does the same thing, a bit accelerated since it doesn't have to run CRTM. And we're doing temperature and humidity using MSE loss, and we also have precipitation classification and rate retrievals. And then, so a little bit about the future. So one of the projects we had as part of the SIMBA development was to make a hyperspectral V-band radiometer. That's some of the plots we got with that on the left, upward looking, so you can see the V-band spectral complex there. There's some issues with standing waves. You can see in the upper right, I don't know if you, where it's not quite as bright orange there. There's some standing wave structure. It matches pretty spot on below about 55.5 gigahertz though. So we're hoping to put that into GIMS 3. So basically the 118, 183 plus the V-band for looking through heavier precipitation close to the ground. And then on the right here that is a deployable 1.5 meter antenna that we're working on developing with some of our partners. So that is for a Cover-like instrument. So that 1.5 meter dish actually folds up into almost a 1U sort of size cube structure and deploys. And we're hoping to do ocean surface wind vector, tropical cyclone imagery, temperature sounding and humidity sounding with that instrument when it becomes available. All right, so yeah, if anyone have questions?
Questions? Looks like Lisa has a question.
So I noticed there were other stripes on the 183 beside the self-RFI. What were those?
Yeah, that's all the S-band radio. So it beacons every 30 seconds right now. That's its default behavior. So every time you see a stripe, that just means 30 seconds went by and it sent an auto beacon with telemetry data.
Okay.
So we're going to probably end up not using the S-band on auto beacon, and that would clean up pretty much the entire swath there.
Okay, thanks.
Anything else? All right, thank you. Next up, we have lunch. Please be back here at 1:30. Do you have any instructions for us for lunch? Same room.
Same room.
Okay. All right. Thank you all so much. We'll see you at 1:30.
discuss precipitation and other matters. We'll resume our program with our second keynote talk of the day, this time by Dr. Christian Kumaro. Thank you so much.
Okay. Oops. All right, my job is to put you to sleep after lunch. So I was asked to do this, and we're going to talk about global precipitation, the way forward. But this is, the disclaimer is this is just my opinion. You can have a different one. But so I wanted to start out with sort of saying in global precipitation, what are we really trying to do? One of them, and you'll see a lot of it this week, is we're trying to sort of look at high-resolution products. They're used in a fair number of applications. They tend to be, every 30 minutes, 10 kilometers, etc. So that product, those products are quite, created a lot by our community, and so we're going to look at those in a little bit more detail. We're also, in the satellite community, have to do a lot with climate change. The modeling community wants very much to, for us to give them the answer as to how is precipitation changing, where and why, and we'll look at that a little bit. And then we'll, I thought the third point I would talk about is sort of the high resolution products we need for impending disasters. Radars have proven very, very useful for that, but not the whole world doesn't have radars. Effie talked a lot about the high resolution products already, so if we run out of time, then we'll skip that. But let me start out with a little bit of history here, right? Just because this is IPC, and way back, when I was a young boy, we were talking about global rainfall products. And there was a break in the community. There was a part of the community that did infrared rainfall estimation. And passive microwave sensors had just been launched. And so the younger people were largely drawn towards the passive microwave. And of course, we were much smarter than the old guys, so we were much better. And back in the early 1990s, we had this big competition about rainfall products, where we compared the passive microwave in the infrared to local radars. This was done in Australia. In the top plot here on the right was sort of the correlation and bias of the passive microwaves. You see the whole group there in the dark on top, and the infrared was below that. Passive microwaves were clearly better at identifying rain than the infrared. But then when we did monthly accumulations of rain, that's the plot below that, you can see that whatever advantage the passive microwave had is now gone. And that's because of the sampling. The passive microwave had to be in low Earth orbit until the latter part of this year, when the Chinese launched the first geostationary microwave. The passive microwave in low Earth orbit just didn't capture enough of the precipitation. So that then essentially set the whole industry in motion. And this was one of the products, one of the infrared products. And I'm going to show you 3 products because I want to make a case with them. So this was an infrared product. This is a number of years. It's a 5-year mean, so there's not really sampling differences between things anymore. 5-year mean of a infrared product that was prevalent at the time. And like we all did then, and like we all do today, below is sort of the validation against some rain gauge data from atolls in that region. Okay, so this is only for ocean. The land is blacked out. And so the validation is from some atolls that nobody thought affected the precipitation at all. And so you see here's the infrared that validates reasonably well. There was also a passive microwave, but an MSU using the temperature sounding channels, which is a 54 gigahertz that were fairly insensitive, the one that's furthest away from the oxygen. And so you can see it too compared to rain gauges in the atolls. It too had pretty good correlations. Everything was wonderful. SSMI had just been launched. This is the map of the SSMI. It too validated against rain gauges. It too looked really good. And everything was great until you put the three of them next to each other. And you sort of look at that image of all three that each validated quite well. And you say, this doesn't look at all like each other. Right? So what's going on here? Right? And the problem is that none of the three actually measure precipitation. Right? Infrared measures cloud top temperature. And then there's an algorithm that says colder clouds are probably raining harder. And depending on how you make your algorithm, that's you get that. And so where you see the infrared making most of the rain is in fact where you see most tall, cold clouds in the world. You know, the West Pacific warm pool has a ton of really cold cirrus in it. The middle panel was the MSU. And the MSU was a 54 gigahertz microwave that sort of said the warmer the temperatures get, you know, then the more rain there is. And in those early days, they forgot that ice in the cloud would actually make the temperature colder again. And so where the warmest, you know, infrared, where the coldest clouds are, there's actually relatively little precip in the middle panel because temperatures were depressed again. The biggest rainfall in the middle panel is actually in the central Pacific, where the clouds are quite shallow and have very little ice, so the emission temperature was highest, and that's where they put all their rain. The bottom panel is the SSMI, and that was sort of had the low and the higher frequencies, and that sort of is a difference between the two, and to this day, what we think is sort of probably the right answer. But I wanted to show this to say that satellites don't actually measure rain. Satellites measure radiances at a frequency, and we interpret that as rain. And if the clouds don't do what we ask of them, but do their own thing, then we're going to make a mistake. And this, as an algorithm developer, I want to say, when we make a mistake, it's not our mistake, it's the clouds that are doing something that they shouldn't be doing. Okay? So don't blame us, blame the clouds. Okay? Anyway, this is, you know, after the SSMI, we had TRIM. And in TRIM, I think because of this experience of having different sensors give very different rainfall, we made sure that we had a rainfall product from the radar, a rainfall product from the radiometer, a rainfall product from radars and radiometers. And these are the three. And while they're not identical, you can sort of see that by the time we get to TRIM, we had made an awful lot of progress in that it now looks like, you know, one another. But they're still not identical because there's still assumptions made in each algorithm, and the clouds are still not, you know, working with us, sometimes working against us. But this is, you know, what then all led. We had the passive microwave, we had TRIM, we still had the infrared to fill in, and this is then what everybody started making. This is just a product that, you know, iMerge that, you know, I have easy access to, so you get to see the 30-minute, 10-kilometer loop from iMerge, and it has 0 mistakes in it. It's perfect. There are other products that are made relatively similarly. They're all infrared with passive microwave, and then merged in some capacity to get the best out of both worlds. Okay, so that's where we are today. See if I can get this to run. Oh yeah, it doesn't want to run, but that's okay. Though it wants me to click each time. But this is, you know, our competition. If we make global 10-kilometer, 30-minute rain maps, this would, oh, it is animating, sorry, okay. This is, I pulled up from AccuWeather, which is a US company that provides radar service. I pulled up the Kampala radar. And this is the Kampala radar. and it's a little bit blocky, but that's my fault, not the AccuWeather's. If you go to the web page, it's a nice animation. And if I Googled AI about the Kampala, radar, and it says that major weather services such as Meteo Blue and AccuWeather provide live radar coverage, for Kampala, Uganda. Which is great, but when you Google the weather radar in Kampala, Uganda, there is none. Okay? There's actually no radar here. There is a small radar at the airport that tracks incoming aircraft, but it doesn't make any weather imagery. Okay? So whatever this is, it's not a radar. Okay? I suspect it's Meteosat, IR, with some AI, possibly some model. Whatever it is, it's not what's being advertised, but you can get this weather radar. Actually, if you go home and Google any city anywhere in the world, weather radar, AccuWeather gives you a radar map. Okay? And it's 5 minute, 2 kilometer. Okay? And it's perfectly accurate. Okay? By the way, the big rain blob on the northwest corner of the image, I measured it's just 700 kilometers from Kampala, which is a very typical radar range, that you can make very useful images. I think if you compute the curvature of the Earth, that system, the radar is about 35 kilometers above the Earth's surface. But anyway, that doesn't stop this radar. Okay. So, so this happens in Colorado as well. My weather app sometimes, because it sort of transitions to model, makes rainfall systems over where I live that don't exist. So I've learned to always, the left panel is the weather app, the right panel. I often go to NOAA, right? Weather radar. And the right panel is NOAA. In this particular case, they look quite good. Right? And so why do I go to NOAA? The graphics are not as good. It's fuzzy, it's hard to get to, it's not on my phone, but when I need the truth, I go to NOAA. Okay? And so my first, when it comes to these high-resolution products, I think the world is starting to make these high-resolution, you pick how many kilometers, you pick how many minutes. It doesn't take very much effort to make an app that shows you the radar, whether there is a radar or not a radar. Right? And so my feeling is that if we want to compete, we have to sort of get serious about the applications, and the global precip community, has to start becoming the reference standard that people can go to. Even if they use the app, when they don't trust the app, they have some reason to not believe the app, there has to be a product that they can go to and say, this is sort of true. And that means we have to have some uncertainty associated with it. We have to let users know whether we actually believe that product ourselves or not, right? Right now, when I showed you the iMerge, it's a uniform product everywhere. If you ask Sarah or you ask George Huffman, do you believe that everywhere? They would say, well, not exactly. There are places we believe more than others. Right? That's not conveyed anywhere. Right? So I would say uncertainty, except uncertainty is a misused word, and nobody actually knows how to use uncertainties. Or some people do, but very few people. At least we have to provide a confidence in these products that is in some way quantitative that people can use. Right? So I think there's nothing wrong with improving our global products, improving the space-time resolution, but I think it's absolutely essential that we start putting some confidence, error bars, metrics on these things, so that everybody else who's using these radar products where there are no radars at least has something some reference that they can use. Okay? So that's sort of my first point. My second objective, that I listed before is the climate change, right? Everybody wants satellites because climate change is global, it's not regional, right? right? I mean, it manifests regionally, but we like to know what rain is doing globally. And, this is, sort of a map of, what the observations are saying versus what, the global models are saying for different seasons. And you can see there are some differences. GPCP, the observations are on the left for 4 months, and then the MIPS is on the bottom left. So that's and by the way, this is a millimeters per day per decade change. And if you can't see it, it goes from 0 to 0.5 millimeter per decade. So when it's a MIP, when you give it the sea surface temperature, you can see that the observations and the models are relatively in agreement. But even there's some big differences, right? So if you go high latitude oceans, top left-hand panel, GPCP, high latitude southern oceans, GPCP has quite an increase of precipitation with climate, whereas the MIP, even with a given SST, has a decrease of precipitation, right? So we really want to know, do we trust these changes in precipitation, or don't we trust them? The CMIP, when you don't give it SST, there you can see are still quite different from the observations. And you can probably say that, the pure climate models probably still have a lot to learn, from the observations. But when we give it the SST, they're similar enough where we need to start thinking about, do we trust those things? Okay. So obviously over land, we have gauges, and we can trust those. So this is the Global Historical Climate Network, GHCN. This is where the gauges are. They're not very well distributed. They're not everywhere. This is GPCC, which is the German climate center. They have more gauges, so they're well distributed. But surely gauges are gauges, and as we heard in the last talk, validation data is always true. But when you look at global climate products, right, and the top panel there is the different colors are a whole bunch of global climate products, or at least high resolution products. And you can see they're sort of in two groups. And that's because the rain gauges, the CPC, the Climate Prediction Center, are the triangles in the lower panel. And GPCC are the circles that are above the line. That's because on the global climate scale, the two gauge products don't agree with each other. And then you can see how the climate products, or the weather products in this case, the satellite products, keyed in on one or the other of the rain gauges that they used for calibration. And so the satellite products disagree because the gauges disagree. Okay? So this time we don't blame the clouds, we blame the gauge people. Okay? There's always somebody to blame. Okay? It's my story. It's never my fault. Okay. Anyway, so it's even worse when you get to extremes. Okay. When it comes to extreme rainfall, you see the gauges are either near the zero, right below the zero line, or well above all the satellite products. Right? So there, the satellites are keying on the mean. They don't key in on extremes, but you can see the gauges themselves disagree violently as to what extreme rainfall looks like. Okay? So gauges have their own issues, right, for climate products. We use MRMS, which is a gauge-corrected radar product. Guess what? It also has its own problems, but Pierre Kerstetter has been doing that for the community, and so it's Pierre's problem now. Okay. And this is sort of an example of it. We were looking at our latest version of the product. And there are two things you can see here. So the top panel is our latest satellite product. The top panel is the satellite product compared to the training data, which is actually a satellite product itself, okay? It's actually the satellite products that's in the second line. So in the second line, when the satellite product that we use for training is compared to the satellite product that we use for training, it actually agrees with itself, great. But then if you look through 4 years of iMerge, you see a couple of different things. One of them is that the colors, which is the bias, is changing regionally, right? So the first 2 years, you sort of see the left hand, the Western US is more red. Certainly the central north is more blue. The southeast, is more red, right? So ignore anything that goes over the oceans, but you sort of see a general pattern of colors that repeats itself the first 2 years. And then the right hand, the eastern US repeats itself the next 2 years again, but the western US doesn't. It flips colors. So this is actually one, Pierre, I don't know if you remember, we were calling you, is that MRMS changed something. At the end of the day, yes, it did change something very subtle, how it weighted gauges in the radar in the mountains, but that was enough to sort of change the biases there itself. But that's not the story. The story here is really that even though it's unbiased for the entire country, there are still regional biases there. And that's still because the satellite doesn't see all the details in the clouds. And as the clouds change from one region to another, we introduce small biases. That's over land. This is another region over land where now we're comparing against the satellite baseline. And you can see, for instance, here that over Central Africa, which is rainforest, we tend to overestimate. Over Amazonia, which is rainforest, we tend to underestimate. And we've been scratching our heads for the last 15 years. What's so different about the two rainforests? Well, the clouds are much taller in Africa. They have much more lightning, not that lightning, but as an indicator of much more ice than the same clouds in Amazon. So there are differences, and that's apparently spilling into. So that's over land where we have some truth. Over ocean, we don't have any, so what we've been doing is seeing if we can close the water cycle. Very simply, if you take evaporation minus precipitation, diverge the water vapor, that has to close, okay? That has to be 0. So if you look at the box in the bottom, we're taking that 20 by 20 degree box only over ocean, so where the box goes over land, ignore it. And the top line is the closure of the water budget. So here's quite a bit of land, so you can sort of ignore that a bit. But once the box gets over to the ocean, pure ocean, you can see that there's quite a bit of non-closure, but it's also not constant in time, right? It's not the same error, which is for me to say that if someone compares to some validation data and gives me the root mean squared error in the bias, it's not a very useful quantity to address diagrams like this, where over the Atlantic, things are beautifully closed. And this success, by the way, is due to my credit. Okay? And so the Indian Ocean, once we get past Africa, you'll see now too, the Western Indian Ocean is quite good. It's very close to balanced. But then as we get to the Eastern Indian Ocean, you start seeing these big departures, right? So once again, for the climate purposes, right, it's not the random error in the bias. It's these time-varying biases that are affecting. I can't swear it's precipitation. Okay? Could be one of the other fields. But just to look at the Central Pacific, this is just a frozen spot in the Central Pacific where the black line is the lack of closure before. And the 3 lines on top, or the green line, is the amount of rain that comes from shallow precipitation. And the blue line is the amount of rain that comes from a deep organized convection. And you can see that every time the deep organized convection goes up and shallow goes down, closure gets pretty good. And why do they do that? They do that because of ENSO. Every time there's an ENSO, deep organized convection goes up, shallow goes down, closure becomes good. Okay? So this is, my way of giving sort of the second, perceived way forward. We have to start getting better at not just doing random and systematic errors, but starting to look at errors as regime dependent and what do they depend on. Effie started talking about that, okay? That it's, you have to start looking at the environment in which the errors occur so that we can at least, at some point sort of start with some confidence talk about global climate errors, even in places where we don't have validation, just based on the weather regime that this precip is occurring. But we have to start putting what we see into context, because otherwise it just, it's just errors that seem to happen without rhyme or reason. Okay? And we have to figure out that rhyme or reason for climate. The third objective was, what Effie was talking about a lot, and that's sort of the high resolution, instantaneous high resolution, forecasts or even nowcasts that we need to give, right? And, this is, where the Japanese do really well. They're the only global product, high resolution, in time and space that actually goes up to real time. Right? If you look at iMerge, it comes out 4 hours late. Okay? The Japanese model, I made this image at 2 a.m. UTC. I don't live in Portugal, so I wasn't really up at 2 in the morning. Okay? So this is the afternoon for me. But you can, if the image was made from 20 to 2059, so it means the image is 5 hours old. And that would be the same for iMerge, right? So all the satellite products right now are 5 hours old, which I would argue is not particularly good, okay? For the application of what's happening now, right? But the GSMAP, unlike iMerge, also has a real time, which happens to be a forecast, right? So this is a 5 hour nowcast from the last image. So I could get what the thing is likely to look at 02 UTC. It just happens to be, actually this is an 8 hour forecast. So again, it's not a real time image, but it's the only one available from satellite, okay? So I give them tremendous credit for going out there. But I will say it's an 8 hour forecast. And it also, like iMerge, has no indication of what I should strongly believe and what might actually not be true. Okay? So that goes back to, and then this is my favorite image from Effie and Clement. This goes back, she showed this too, she didn't show this figure, but I just showed you earlier a 10-kilometer, 30-minute image loop from iMerge. Okay? This is the resolution, the effective resolution of iMerge, okay? It's not 10 kilometers, okay? It's actually closer to Brown, which is 80 to 120 kilometers is the effective real resolution, right? And everybody always tells me that they use 2-kilometer IR data, so therefore their resolution is surely 2 kilometers. No, it's actually more like 100 kilometers, right? So over ocean, the resolution is better. The footprints of the sensors are actually larger, the useful ones over ocean than they are over land, but there's more information content, right? So this is actually more an information content map than it is the resolution of the sensor map, right? So we need to deal with high resolution data as well, right? And that doesn't mean just use 2-kilometer IR. It means doing what Effie's doing, both, started to do, we're doing it too, is starting to look at spatial correlations, temporal correlations, and squeezing the high resolution information out of that data and not simply taking pixels and saying this pixel had 2-kilometer resolution. So my third one is we really need to decrease the latency, increase the spatial resolution. You know, it's easier said than done, but I think we do know that between spatial and temporal resolution, there is more information in the satellite data we're using. AI is useful for extracting it. We have to start doing it. But then we also have to, here too, start looking at uncertainties and errors, right? And the biggest issue is that errors, you know, everybody reports RMS and biases, but that's not, again, not the real error we need. Correlation of errors is incredibly important, especially when you get to high resolution. You know, if it's the same uncertain high rainfall system that's kind of moving along, then that uncertainty doesn't get reduced by 1 over the square root of the observations, right? So we need to know the correlation of the errors. And just as a pet peeve of mine, if you don't know what the resolution of the data is that the user needs, it's incredibly hard to report that. Because we love to report all our satellite data for pixel locations in uncertainty, but how do I convey what the spatial and temporal correlation is? So that if the user wants to aggregate into weekly or 3 days or monthly or annual, that they know what to do with the spatial correlation or the temporal correlations. Okay. So my last slide is this. I'm done. It really just came back. It says that validation is incredibly important, but it's not RMS and bias, okay? It's we got to take that next step. What does it depend on? What are the atmospheric variables? Clouds do not know where they are or what time it is, okay? They only sense the environment. And so that ought to be enough to figure out what the uncertainties are, okay? I also want to say that uncertainties themselves are misused often, and we need to think about it as a community. And I know they're misused because we were told 1,000,000 times that we had to add uncertainties to our rainfall product, which we did until one day something went wrong, and for a year we didn't produce uncertainties. Nobody told us, okay? Which tells me exactly how many users of that uncertainty there were. Okay? So people always say they need uncertainties. I don't think they really need them. I think they need something somewhat different. I think normal users need confidence. Should I trust this, yes or no? Yes, maybe, or no, right? And the science community, I think, needs something completely different. But we have to work on that. And just comparing it to some ground truth is not enough. So that's it. So if it does this again, push the cable towards. I think using everything that's available, right? I think too long we've been saying, use this frequency for this and that for that. I think machine learning in general says, stupid, okay? Just use everything there is. Let the machine figure out what's useless, okay? Machines are pretty good at figuring out what you don't need, okay? So let's not overthink this going forward. I think AI fixes it for you.
Yeah, so nice talk. When you talk about environment dependence or environment-based analysis of uncertainty, how we should define environment that describes the situation that we want to
I specifically didn't.
Yeah, I mean, any suggestion how to start?
So this is only mine, right? So obviously temperature and humidity structure and convergence, right, is typically all that clouds sense. Having said that, you cannot go too fine scale. So if you go at an individual cloud, every individual cloud is different from every other individual cloud, right? But still sort of on the 2-3 day domain when the weather doesn't change much, right? The clouds sort of tend to repeat themselves. So my feeling is it's somewhere in the 2 to 3 day, 100, 200 kilometer scale, temperature, humidity, convergence. But yeah, right? I mean, convergence forces that, right? But that's my guess, right? I will admit that I've been working on this for a little bit. It's been quite frustrating because I haven't gotten the clean result I've been wanting to get yet. So if you can do it better, it doesn't take a lot. Yeah, Ali.
Okay, so I have a couple of things. You showed earlier about the MRMS from 2018 to 2022, and for five years. And I think you were asking about what changed with MRMS. 2020, they moved from the dual pole. That was the change. It looks like your graphs were changing 2020. That's where the time that they started using dual pole variables for the radar estimate. That might be your reasoning behind that, the change in the MRMS. You also mentioned about the GPCC and CPC gauges. They don't agree each other, which is interesting because from the perspective that iMerge use GPCC on a monthly base versus GSMAP uses CPC on a daily base. Right. And if you look at their final products, the GSMAP is about 20% better with respect to iMerge. And they claim that because they are using daily, not monthly adjustment. Well, that's their bottom line from the Japanese end on that.
Like I say, so it just depends on which one you use. But,
Yeah.
So from the MRMS, like I say, the change in MRMS, it doesn't worry me as much as the fact that, we had those regional biases, and they're still due to the weather systems that we have, right? I mean, we'd love the validation data to be true. That'll never be the case, but we have to deal with that, right?
And I think my final question about, in one of your early diagrams, you mentioned about something with 10 to 20%.
Right, between gauge data sets.
But at which temporal scale, at what spatial scale?
Global monthly.
Monthly and what's the spatial?
Global.
Okay, thank you.
Okay. Last question.
All right, these are more just comments, so I'll see what you think. For the weather radar comment, I'm curious, just in general, AccuWeather actively uses iMerge in their operational systems, and also Media Blue, I do know they access GPM data. I'm just saying that as I'm curious to know how that maybe folds in if it's not actual weather radar. So that's a comment. That's in one comment. And then also I just want to go back to your last point on the uncertainty. I think just for accountability, defining it as this community, it helps so much, it makes it so much easier to relay information of how community of experts think when talking to folks, even if they're experts in their field like insurance, finance, and all these folks that want to leverage the data. So I just want to echo, and I think that's super important to be able to translate this technical information to something and to also help them define what does uncertainty mean to them.
And I would like to challenge everyone here tonight when you're having a cocktail, talk to whoever you're talking to about uncertainty, see if you can even agree on what it means. But it's a great conversation to have over beers. And the more you drink, the more you start agreeing. So.
Yeah, well, okay. Well, I will not respond to this comment because actually nobody agrees what uncertainty is. How to use it. I think we have a major bottleneck as a community here. It's not Chris is right. This is not uncertainty we should talk about. I think we should talk about events of interest. We should go back to looking at, basics probability books and and go back to the first principle, say, what are we interested in? And what likelihood can we associate with it? I think that would be a starting point. We have been having a false debate for decades about that. And I think we need go.
Vasco, stop them, stop them.
Start this discussion, but the thing is, can we shift our attention to uncertainties for what the impact is or what the sector that's going to use this product is? And this is easily done now because I'm giving you not pixel-weight uncertainty, I'm giving you ensembles. You can run over your basin and create uncertainty in your stream flows. You can run over a city and see what is the possibility of this area flooding, etc. So we pass to a different level. It's not pixel-wise, it's not correlated uncertainties, I give you ensemble. Realizations equally probable.
Let me disagree with that slightly, but say that that's what we're going to do tonight when we're drinking.
Yes.
Okay, so we're going to continue with our next session. So this first speaker, the next session.
It's Ethan from tomorrow.io.
Good afternoon. Sorry, I've been flying for 40 hours, so I'm a little not here, but we'll go through this anyways. My name is Ethan. I am with Tomorrow.io. Quite a few names up there, but really this is a big group effort. I'm going to be talking about our small-sat constellation, some of the products that we're developing, and just kind of our, I think, vision and philosophy for going forward. Now, Tomorrow.io, way before space, we had a big enterprise offering, and I mean, we still do, but this was kind of our bread and butter. So talking about uncertainties and users and risk, we're really interested in finding sectors, looking at their pain points, what costs money, what weather events cost them money, and how can we mitigate that using probabilistic information. Now we've advanced to proprietary satellite data, trying to create global high revisit satellite coverage, and then that powers other things downstream, AI-powered modeling, and what we're calling agentic AI business intelligence, which is what I said without the buzzwords. So if you're not familiar, we have kind of two different offerings that we've been exploring. So the first was really our radars there on the left. Two Pathfinder satellites launched in 2023. These were Ka-band, single footprint radar satellites, and had some ups and downs with bus and different payload anomalies, but we got a pretty good data record. 5-kilometer footprint. If you care, there's some more statistics. Really the main thing, 50% duty cycle, so we couldn't sample everywhere all the time. And then kind of what we're working on right now is the microwave sounder constellation. So we have 11 microwave sounders launched. These have a heritage in the tropics mission. You can see the various orbits there. We're doing both SSO with various LTANs as well as inclined orbits. 12 channels, weighting functions there in the bottom left. Let's see. Okay, yeah, so pretty picture. I took this just from April, showing revisit. This is every 10 minutes, and I think the fade is about an hour. So really good coverage that we like, which is fun. Now talking about the products, we've got two different types of neural networks. We're really leaning into machine learning, AI. So just kind of a 1D neural network where you put in a vector and you get out a vector, and then kind of a 3D neural network where you're doing more of a convolutional structure. So we have two different strategies for these retrievals. And so the first one that I'm going to talk about is model-based retrievals. And so what we do, this is just a static image, sorry the video was way too big, but we took the GEOS Diamond nature run. So Diamond is really interested in seeing how convection is represented in global high-resolution models between different centers. We took the NASA one, obviously. And what we did is we took that 3-kilometer atmospheric simulation, and we simulated an SSO and an inclined orbit from that on the native grid. And then we basically take our specific instruments, so 11 sounders right now. We take all the characteristics about the antenna, bias pattern, spectral response functions, and we basically try our best to represent what radiation that satellite would see, but through the model. And we get all of the model fields out of that: temperature, water vapor profiles, and so on, surface precip. Some validation, this is really just some plots. You're not going to take much away from it, but we do a pretty good job compared to tropics as a good start. There's also some iterations of these figures that I've made more recently where we're getting close to ATMS performance. So that's on the left side. On the right side, looking at precip since IPC, the top right shows just kind of the coloring of sample size. I'll talk about a unique characteristic of that in a second, and then the bottom right shows a scatter plot with a 1-to-1 sample line. I didn't put an R-squared on there right now because this is just our kind of interim microwave product. Now you'll notice though, if you play with our data at any point, we might have kind of gaps, or you wonder why is it much, I guess, bluer over the southeast US. Right now with our current generation, we actually can't receive data, so when we're transmitting to a downlink site, we don't get good data because there's some interference. So that can often cause holes over great MRMS coverage. All right, the second type is really observation-based retrievals. And so what we're doing is taking gold standard instruments like GPM and trying to extract information out of that, throw it into a neural network like Chris was saying, and see what comes out. So for our Pathfinder L2 product, we took 1 year of the combined KUKA GMI precip rate, and then we basically, again, brought in simulations of what our Pathfinder would be, and then we threw that in the neural network. And then in the operational standpoint, we just feed it in the actual Pathfinder data, and we get out a lot of nice GPM product-derived data. And so one kind of interesting tidbit, when we did the training, we held out some data, and then if you look, so there's a lot of data here, but if you focus on this plot, the x-axis is, you guys, oh, you can't actually see that. Okay, so the left column shows on the x-axis just the Ka only product, and then on the, I guess the top row shows the DPR estimate only, and then the bottom one shows the DPR GMI. So if you compare the Ka versus the DPR GMI, we got an R-squared of 0.28. But then when you look on the right, where the x-axis is now actually our neural network algorithm compared to the DPR GMI product, we get an R-squared of 0.7. So just kind of rehashing, with that really gold standard combined data product as our training for like what the precipitation estimate is, when we feed it in just Ka only data, we actually do a pretty good job from our satellites. And then talking about climate, wow, this is very, I guess, fortuitous. So I just threw together all the precip rate estimates, and I did a gridding here. I think this is 1 degree, over the full data record. So the bottom left shows the sample size of the various points. And then if you look in the right-hand side, and if you squint, you can actually see a lot of commonalities between GPCP and our product. And keep in mind, there's not that much data. We have like 2 years of single footprint data. So it's great, and even a limited, and I'm not saying this will be used for climate data, but in even such a small sample size, we can continue to reproduce these trends that we see in government missions. And then finally, the new product that we're really working on right now, this is our sounder. We're calling it high resolution precipitation product. And this is, again, another product that we're training based on GPM data. So we take, for this plot here, since this was done last week, we took a full month of combined the GPM CMB product, co-located with TMS, and we basically did a convolutional neural network for chunks of those data overpasses. And so then when we have that training done, we can basically feed it in just our microwave sounder, brightness, temperatures, and some other information like land fraction and elevation, and we get a lot of nice outputs from the combined product. So just some eye candy on this slide. Hey, it's a typhoon, it matches, that's great. And then just some skill scores. So again, this is like 1 month of data, just a stab in the dark, but actually not doing too bad. So we're very hopeful that we can really, well, one, train on more data as we're compiling those archives, but then two, try and make this a more high resolution product. I didn't mention, I'll go back, that's the jet lag. So right now, I was taking a 3x3 grid that surrounds our pixels on those overpasses, but eventually we want to actually do kind of a super resolution retrieval where we're doing in between our microwave sounder footprints. And then finally, again, these animations were too huge, so I just took a static image. But we're playing around with real-time nowcasting from our microwave sounder constellation is kind of the first pass, and then also adding in geostationary, that's obviously the next step. And just this kind of plot here in the middle bottom, whatever right you want to call it, the retrieval when we include geostationary versus MRMS for a given snapshot. Again, blur your eyes right now, they look okay. Lots of improvements. So going to the title of the talk, Improved Global Precipitation Understanding. What we're really about is trying to improve global revisit rate and improve data latency. Kind of our lifetime is 5 years for satellite instruments. And so we're really still leaning on these government missions, the big dollar, like gold standard missions to help us calibrate and validate these instruments across both the different instrument characteristics as well as just the kind of different launch times. We've noticed, and I don't have it in here, but our radiometric behavior has actually been pretty impressive over 2 years as we kind of look at our calibration data over and over again. And so just the final bullet point, we see ourselves as a synergy with government operational missions and definitely not like some sort of replacement. And then talk about low versus high frequency. Well, we're actually running some internal trade studies right now. What is that 50 to 60? If you didn't look at the weighting functions, we don't have, or in my slide, we don't actually have those on TMS, but what kind of information does that provide versus just that 12-channel neural network? We're playing around with that, and I'm just going to kind of jump through here. So with that, I'll take any questions. Thanks. Oh, and I guess these QR codes, if you don't know, I mean, we have a lot of our data that the government has purchased. So the whole Pathfinder, I don't know that it's all up yet, but the whole archive for the Pathfinder radars, that's through the CSDAP on the left, and then on the right side, there's been a NOAA data pilot, and they have, I think, 6 months of data.
Yep. And I think that full radar thing is up now.
Yeah.
Great, thank you so much, Ethan. Questions for Ethan?
Sorry, that was a flurry of information.
You never mentioned what kind of neural network model you're using. So what's the type of model you're using, hyperparameters, features? What are you using right now?
So for, yeah, I left a lot of that out. So for the 1D, we have quite a few hidden layers in there. And it's a back propagation neural network. So as we continue to train it, the neurons talk to each other.
Is it just an artificial neural network?
Yes.
Okay.
Yep. And then this 3D is a convolutional neural network. I don't know the full mechanics of that, but basically taking like a 128 by 128 chunk, feeding that in, then it downscales and then upscales.
Okay, thanks.
Yeah.
I have time for maybe one more quick question for Ethan. Ali?
I'll leave it on the climate slide, Ali, in case you have a question about that. I don't know where that was.
Thank you for the talk. So KA is the information plus microwave sounder. So KA may have issues with extreme precipitation because probably doesn't see the core of convective very much. I don't know how the analysis of microwave sounder is with respect to extremes, and what's the performance of your product with the very extreme cases that was very important?
That's a good question. Yeah, obviously K saturates. For the microwave sounders, well, our first pass didn't do so well. That just in full disclosure. We noticed that there were a lot of issues with heavy convection, especially with tropical cyclones. So what we've been doing is actually augmenting this diamond data set with the halves model. So NOAA runs this halves model on tropical cyclones. And so we're basically trying to replicate the same framework for generating synthetic observations. So I'll keep you posted, maybe at AMS. But we're expecting improvements where we do better simulate that, high intensity precipitation. All right, thanks, Sarah.
All right, thank you so much. Exciting stuff going on there. Now we're going to move on to Daniel. Okay, I thought I had the PowerPoint. So what do I have to click? There we go. There we go. That's this one. Okay. There we go. All right. Okay, go ahead, Daniel.
Hi, I'm Daniel Waters. I'm going to talk to you today about a high-resolution global convective stratiform precipitation type product from geostationary infrared observations. I'd like to acknowledge my co-authors as well, just before starting with the talk. Okay, to simplify the title down, because that's a lot of words, what's the research gap here? At the minute, there is no high-resolution precipitation type product that exists for global monitoring. What do I mean by that? Well, essentially, we have the iMerge product, GSMAP product that provides us with long records of high-resolution precipitation rate data, but we don't have precipitation type products, convective or stratiform, currently available. So in other words, no iMerge product for precipitation types. You might be asking, okay, well, we've got precipitation rates. Why do we need precipitation types as well? And there's several reasons for it. The first one, you can use precipitation types, convective or stratiform, to calibrate satellites. You can use it for monitoring extreme events, classifying storm types, but maybe the most important of all is that convective and stratiform precipitation types are an insight into latent heating. And where we have latent heating, and in particular differences in latent heating in different parts of the world, that's where we get things like the Hadley cells, so different circulations, winds across the globe. So it's important information to note. For a global monitoring type product, what we have at the minute is not monitoring capabilities, but we have a reference for case study analyses. We have the GPM dual frequency precipitation radar. It's orbiting around the Earth every 90 minutes, which means that we can't use it for monitoring. It only has a 245-kilometer swath, but what it does provide is invaluable data as a reference for training. And in particular, the vertical information, the 3D information that you get from a radar, the profiling information, is critical for understanding precipitation types. So, an overview. The goal of this presentation is to showcase a high-resolution global convective stratiform product from IR brightness temperatures at 0.05 degrees every half an hour for the past 30 years. The rationale behind this, we want to synergize the geostationary IR high-resolution cloud top height record by utilizing the GPM DPR's precipitation type sensitivity as a training reference. What you see here is just a table that just highlights the synergy between the two. You've got the IR provides quasi-global coverage at high resolution all the way back to 1998. And the DPR is providing the precipitation type information that we want to use to generate information across the globe. And then we also have a product like iMerge. It provides precipitation rates everywhere, which allows us to delineate between rain and no rain. Okay, so for the precipitation type product, we've named it Grommet, and we've actually produced two different types of models. So in both cases, on the left-hand side, you can see the core predictor of the models is the IR brightness temperatures at 0.05 degrees every 30 minutes. And on the right-hand side, you can see the target information, which is the DPR precipitation type at the same spatial temporal resolution. Okay, why two models? This is where things get interesting. Okay, so we provide two different sets of convective precipitation probability outputs, one from a heuristic type model and one from a machine learning type model. The reason for this is that if we utilize all of the information that we can get from kind of heuristic approach, we're able to see what the gains of machine learning are compared to what the best possible capabilities are from the data we already have. And that's something interesting to be able to know is really, are we actually advancing things, and by quantitatively how much with machine learning? Okay, so the first one. I'm going to flick through these two slides. They're both pretty similar, but we have version 1, which is called the heuristic model. It is essentially just a lookup table. So on the left-hand side, you can see the predictor in blue is the IR brightness temperatures across the globe. We get the precipitation, rain or no rain information from iMerge. And then that feeds into the green lookup table box. It's a 5D histogram purely from DPR and IR matchups for 3 years. It ingests information on latitude, longitude, time of day, brightness temperature, and precipitation type. The target is the DPR precipitation type, and it outputs global convective probability information at the same resolution. On to model 2 then, so version 2. This is the AI/ML model. We've chosen a model, a quite simplistic machine learning model called random undersample boosted trees. The reason for this is because it's targeted to the problem that we're dealing with. 80% of all precipitation on Earth is stratiform and 20% is convective. It's what's classed as an undersampled problem. And in particular, getting the convective accuracy is really important. RUS boosted trees is tailored towards this sort of problem. For our training, we use a segment of days at the start of the month across a 3-year period. For the testing data, we use a separate segment later in the month. We ensure that there's no correlation between the two data sets. And interestingly, the only predictors that we use for this model are brightness, temperature, and latitude. Why only 2 predictors? Well, we utilized a range of different predictors for this model, and we essentially tested both forwards. We did what was called like forward modeling and backward modeling to identify what were the key predictors for estimating precipitation types in this machine learning model. So what you can see in the diagram on the right-hand side, in terms of accuracy scores, we've got in green both convective and stratiform, in blue stratiform only, and in red convective. And on the left-hand side, before the dotted line, you can see all of the predictors together give us a convective stratiform accuracy of about 84%. All predictors includes everything we can throw at the machine learning model. So that is latitude, longitude, brightness, temperature, precipitation rate, elevation, water fraction, time of day. If you look then at the right-hand side of the plot, you can see that with latitude and brightness temperature alone, we are able to replicate the score compared to putting every predictor in. So it means that we only need two variables for this particular type of model. That does not mean that it's the only thing that's needed for any type of model. In terms of accuracy, you can see on the left-hand side compared to the right that the machine learning model outperforms the lookup table. And for an independent year of data, you can see that the stratiform score goes up by about 1%, but interestingly, the convective score goes up from 51% to 58%. That's a rise of 7%, which is pretty good. And to go beyond that, we don't want to just look at bulk metrics. We're also looking at different ways to test the model. Zonal accuracy is one that we've been kind of investigating. So in blue, you can see the lookup table model. In red, you can see the machine learning model. And in white, you can see the reference DPR data. And you can see that the two models are doing an okay job at replicating kind of zonal trends, but not perfect, and they have their differences. Okay, to conclude, we have generated 2 different types of models for predicting precipitation types across the globe. The lookup table model has an accuracy of 82.6%. The machine learning model increases that by 2.1% to 84.7%. The machine learning approach is able to boost our heuristic capabilities by 2% in terms of overall accuracy, 7% in terms of convective accuracy, and to increase the Heidke skill score, the ability to delineate between convective and stratiform precipitation types, by 0.1 nearly. And just to highlight, this work is part of a larger measures project with a wider team. There are concurrent passive microwave and alternative IR algorithm work currently being conducted by Velshko, Marco, and Jackson Tan, respectively. Thank you for listening.
Yeah, it's interesting that only 2 features seem to do pretty well, or at least, you know, the other features didn't seem to be as important. Have you looked into any other features you can include in your model in version 2 that might give you some better accuracy? And have you thought about doing feature importance as well?
Sorry, can you just repeat the last part?
Yeah, feature importance, like ablation studies at all? Like randomly perturbing some features to see what features are more important than others?
Oh, sorry. Okay, thank you. I appreciate that. Thank you for the question and the comments. The first one, in terms of the predictor selection, we tried to go exhaustive with as minimal information as possible. So what I mean by that is that we're trying to use as much kind of geospatial information, but we really want the core predictor of the model to be infrared brightness temperatures. If we have to start bringing in auxiliary data, it makes the model more complicated. So there is the potential to do that in future, but as a kind of you know, starting point, we do want to start with the basic variables to see really what's, you know, most important before we try and boost the score even further. In terms of using 2 predictors, I think something that I just want to highlight in particular on this is this does not mean that latitude and brightness temperature alone tell you a lot about precipitation type. This means that for this particular machine learning model we've picked, which is tailored to this type of problem, it only needs these 2 predictors. That doesn't mean that with other models that would be the case, and that is part of the kind of choice of what kind of machine learning model that you use. The benefit of the model that we have used here is that it is an ensemble tree-based approach. It's essentially explainable AI. We can look into the tree and see why it's done what it's done and where maybe some of the simplicities are. So that can explain some elements of why there may only be kind of 2 predictors. Did I cover everything in your question? Okay, thank you.
Hey, Daniel, good talk. I just had a question, and maybe it was my misunderstanding. So when you did the basically binary precip and no precip, you didn't use a threshold. You just said if it's more than 0, is that correct? Or did you use some type of threshold to determine that precipitation versus no precipitation? I don't know if that helps, or if that...
Yes, no, I understand your question. Thank you for the comment, first off. In terms of the precip or no precip, we just purely use iMerge for that. So essentially, it is a case of, is it more than 0? It's actually if it's more than 0.03 millimeters per hour, which is the iMerge precipitation threshold. So yeah, it's just done in that sense. And part of the reason for that, and not kind of integrating it too much into the model, something I should stress actually is the model does not predict if precipitation is there. It purely predicts whether it's more convective or stratiform. With the ability for using iMerge, it means that if things improve in future, we can replace iMerge with, you know, that thing that improves it, whether that's an improved version of iMerge, whether somebody wants to use a different type of precipitation rate retrieval.
Thank you.
Thank you.
All right, we are about 20 minutes behind now, so we're going to go ahead and move on. Our next talk is going to be remote from Jackson Tan back in Maryland, who is going to talk to us about iMerge. Are you there, Jackson? Oh, we see you.
Can you please try to say something just to see if we can hear you? Okay, I think we can hear you now.
Can you see my slides?
Yes.
Yep.
Okay, perfect. So I'm going to get started. So thanks for the opportunity for me to present on iMerge version 8. Sorry I couldn't be there with you in person. Now, I'm the one giving the presentation, but this is an effort by a lot of people. You can see the iMerge core algorithm team there. But I've also added contributions from GPM family, and that's because iMerge is the tip of the iceberg, and we are supported by a huge team across the GPM family, and they have made contributions that you'll see in my presentation shortly. Okay, so now a quick introduction to iMerge. So what is iMerge? It's a gridded global precipitation product from GPM, 0.1 degree, half hour, fully global, going back from 98 with 3 different runs to cater to different latency requirements. So in the full iMerge algorithm, we take the passive microwave precipitation retrievals from the GPM constellation, we grid them, we calibrate them to the combined radar radiometer product, or CORA, and then we perform forward and backward morphing to get complete coverage of the passive microwave retrievals, and then merge them with the infrared precipitation in a Kalman filter framework before finally applying a gauge adjustment overland to the GPCC gauge analysis product. So this is the full iMerge algorithm. Near real-time runs will drop different components to reduce its latency. So the entire GPM family product are in the process of upgrading to version 8. DPR and gprof are already in production with full record being generated right now. CORA and iMerge are still in development in terms of its code. So this presentation will showcase a selection of algorithm changes in iMerge version 8 and their impact on the scale of iMerge. So first of all, gprof. In iMerge version 8, we'll be using gprof version 8, and gprof version 8 adopts a new machine learning approach. It is a convolutional neural network architecture, and it is leading to more consistent retrievals across sensors and better scale. So if you look at the figure over there, on the left is gprof version 7, top is GMI, bottom is one of the SSMIS sensors. So you can see that while the two sensors are broadly similar, there are some differences in terms of the area and in terms of the high intensities. But if you look at the right, that's version 8. SSMIS is much more consistent with GMI. And that's one snapshot. And if we were to conduct an evaluation over one season, this is what we get. Version 7 on the left, version 8 on the right for GMI. Now, if I blow up the stats, you can see that there is a remarkable improvement in the scores in all these metrics that I'm looking at. So this is indeed much better. So version 8 is indeed much better than version 7, and this will filter down to iMerge version 8 as well. So this is the passive microwave inputs. In iMerge version 8, we'll also be switching the IR precipitation algorithm to the gprof IR, which is an algorithm that leverages the gprof neural network designed for passive microwave retrievals. And if you look at the evaluation right there, again, just like the passive microwave, we're looking at very much improved retrievals for IR. If you look at the numbers, it's a very impressive improvement. And in fact, this is a very striking result because it is forcing us to reconsider our philosophy of handling input. So for the longest time in merged products, the conventional wisdom is that, oh, it's passive microwave is the best and IR is not so good, so we'll use IR as the baseline to fall back on. But if gprof IR can be so good, this means that we may need to rethink how we approach these various inputs. Okay, oops, sorry. Okay, so one issue is that we realized with version 7 is that okay, no, wrong slide, sorry. So another change here is that we're splitting the passive microwave fields in iMerge. And what I mean by this is if you were to take one of the half-hourly version 7 files and if you look at a variable called MW precipitation, you'll see something like this, the plot over there. This is the available passive microwave retrievals in that half-hour window with everything merged into a single field. But in version 8, we are going to split it into 4 different views. So there's GMI and TMI, the reference sensor for each era. And then we're going to have images, we're going to have cross-track sounders, and we're going to have others. And for others, it is a layer intended for small sets. And the idea is that by keeping small sets separate from the standard satellites, this allows us to better handle the expected difference in quality, so we can avoid a situation such as, a small set overriding one of our big standard satellites that we have. And the fact that we have them in 4 different layers also gives us the advantage that we can actually compute the Kalman filter stats of these instantaneous retrievals. So in version 7, which is on the left, all the layers are all in one layer. All the passive microwave are all in one layer. So we cannot co-locate them with GMI and TMI. So when it comes to the Kalman stats, where we merge them together by their relative performance, we have to reconstruct the stats from the climatology. And so that's not ideal. So in version 8, the fact that we split them into different layers allows us to compute the co-located and therefore the instantaneous stats when we merge them. And so it is more representative. And then on top of that, if you look at that 2 plots over there, you can see on the right, it is much more finer resolution. And that's because we are reducing the computation of the Kalman stats to every 1 degree over a large area separately over land and ocean. So we can get something that is, the stats are more regionally representative. Okay, and then if we were to evaluate the changes to the Kalman filter, there is some modest improvement. Not a lot, but quite a bit. And this is just the same, the change in scale when we use the same inputs. So this is with version 7 gprof input going in and doing the propagation. The change in stats is a measure of the changes in the Kalman filters alone. So if we were to include version 8, gprof version 8, we can expect a much bigger improvement. Okay, so now, even though iMerge version 8 is still in development, there are still pieces to be done. We can put all the pieces that are already ready together, assemble them, and do an end-to-end run and perform an evaluation. So what you're seeing here is an evaluation for 1 month showing various metrics. So this is for version 6, iMerge version 6, and we can throw in version 7. You see there's a bit of improvement across many of the metrics. We're looking at correlation, Heiker scale score at 2 different thresholds here. General improvement, but at the Heiker scale score at 10 millimeter per hour on the right, there's a slight decline in scale in the detection of intense precipitation for this 1 month at least. Now, if we were to throw in version 8, this is what we get. This is the jump in the scale that we can be expecting, a massive leap compared to version 7. And this is across the board in all these metrics that we're looking at. Okay, so in summary, iMerge version 8 addresses issues identified in version 7, and we continue to improve the estimates. And we have also made changes to better position iMerge to handle small sets. And what I've described are just a small selection of the many other changes that we're implementing in version 8. Other changes include a more consistent record between the trim and GPM era, so we can have a distribution that is more consistent. And also, I will point out that we have some sample files available upon request. So for you to test out the file format, data structure, metadata. So if you need to get started in terms of preparing your workflow, you can email me. But I will say that the changes in terms of the file structure are relatively minimal this time round. And if you were to evaluate iMerge version 8 test products, we can expect a massive improvement. And I will give a shout out to the gprof team at Colorado State University. They are responsible for most of this increase. Like you look at the massive jump in version 8, that's mostly them. And so, when will iMerge version 8 be available? Now, this is a timeline we put together a few months ago, but it's more or less still valid. So we are there today, we're here today. Sometime in summer of 2026, we will begin retrospective processing of version 8 final, and retrospective processing is the processing of the 20 plus years of the record going back to 98. Now, I know we're already in summer, so it's starting to get close, but summer goes all the way to August, so we still have a bit of time. And once we get this going and it's done and we're happy with the result, then the next step is to go to the near real-time products and we do the retrospective processing. And that's because the near real-time retrospective processing of the 20 plus year record uses the intermediate files from final. So then that gives us a full 20+ year record for the near real-time users to study the changes before the actual near real-time switches over to version 8, which is expected to occur no earlier than fall of 2026. Now, obviously, this timeline is a projection, so there may be some delays, and indeed, we're still waiting for some upstream products to be finalized. So this timeline may yet slip. But I'm sort of confident that we will have something out there by this year, by the end of this year. So if there's any feedback or questions, or if you want sample files, my email is there, and there's also a link to the slides. Thank you.
Any questions?
Thank you. Very exciting work. You've showed some evaluation for the USA region. Have you done any evaluation for the other areas, tropics, Europe, Southern Hemisphere, etc.? It'd be nice to have an idea.
No, unfortunately not yet. But so our focus is with the US because that's where we have data. But okay, sorry. I realize I can't turn on the live stream. Yeah, so not yet, but we are certainly keeping in mind, especially once we start rolling out to actual test product. I think we can start looking at other regions as well.
Thank you, Jackson. In the interest of time, we'll move on to the next presentation. Thank you so much.
Thanks.
All right, next I'd like to introduce me. I'm going to be talking about land surface emissivity in the microwave. To be very clear, this is work that Fraser King did. I was the idea man behind this project, but Fraser King did the bulk of this work when he was doing a postdoc with me at NASA Goddard. He's now a professor at University of Wisconsin-Madison. But I'd like to tell you a little bit about his amazing work. And I had to share, this was his title slide for the project. I love it because he gave our project the acronym GRAIL, like with the idea that the surface emissivity was the holy grail for physical precipitation retrievals in the microwave. So this is a precipitation conference. Why am I talking to you about land surface emissivity? And the reason for that, as most of you probably know, is that in these window regions that we like to use for precipitation retrieval, a large part of the radiation you're seeing at the top of the atmosphere is coming from the surface. So a better understanding of how the complex land surface emits in these frequencies is key to really understanding how the retrievals work. It's a large and highly variable contribution to that signal. And it's sensitive to frequency, polarization, all of the dielectric and roughness properties of the soil and the vegetation, and whatever's on the surface, the buildings, the roads, whatever. Standing water or snow cause very large changes. It's very challenging to model, right? So the physical models require, assumptions about what direction the leaves are pointing and how many of them there are. And that's obviously something that we are just not ever going to know on a global scale. But it has the beauty of being a bottom-up type of retrieval or of model, so that in precipitation where we're not seeing as much of the surface, we can still get a good value if we use these models. Retrievals, on the other hand, are top-down, and again, they don't work very well in regions of precipitation, but in cloud-free areas, they're very accurate. So the models and the retrievals have different strengths, and their strengths vary by frequency. The plot on the right, this is kind of where this all started. This was a paper that Ralph Ferraro and a bunch of us put together back in 2012. And so those plots are showing emissivity times temperature. So this is a much smoother function than just the emissivity itself. And the only thing you really need to see here is that the orange line is the models. And you can see that as the frequencies increase across the top, we've got 10, 37, and then 19 and 89 on the bottom. And especially if you look at the 89, the model values are just way out of the ballpark compared to any of the different retrievals. So this started with some work that I did back in my graduate school days. I used 5 years of emissivity retrievals from very strictly cloud-cleared pixels from AMSR-E over the Southern Great Plains in the US. And we noticed that the emissivities tended to be pretty strong functions of the leaf area index at the higher frequencies and the soil moisture at the lower frequencies. So we developed what we called a semi-empirical model, where we would model the emissivity at 10 gigahertz, which, if you recall from Ralph's plots, is where the models perform the best. And then we would use those, use the relationships between the 10 and all of the other frequencies as a function of leaf area index and soil moisture. And if you look at the plots on the right, that sort of tells you that this should work. These are for one bin of a particular leaf area index and a particular soil moisture, and it's comparing the 10H, which is the one we would model, to other frequencies, and you can see that they line up pretty closely. When I did this, I just used very simple, like linear covariances. And so Fraser is a machine learning expert, and so he looked at doing this in, a more complex way. So the idea was that you would get the 10H in some way, either from a model or a retrieval, and then map with an empirical model using machine learning to all of the other frequencies. And we hope that this will have multiple applications, improving data assimilation, forecasting, et cetera, et cetera. As input to this, we used the GPM combined retrievals, and in particular, the emissivity retrievals that were done by Munchak et al. 2020. These are sort of really good gold standard emissivity retrievals. And for the surface information, we use the SMAP level 4 product. So really high temporal resolution, surface soil moisture, LAI, all of that good stuff. I'm not going to go through all of these, but we've got all of the channels of the ORE retrievals. We have information about the character of the soil. That's also necessary for understanding that emissivity. And again, the SMAP products. He explored a series of models, so we could sort of look at the difference in performance based on how complex the model was. Everything from simple channel covariances, linear regression, moving up to feature tokenizer transformer, the FTT, which was his most complex model. So these are plots of the RMSE on the top and the R squared on the bottom. For each of the frequencies of GMI, which you see along the bottom axis there, and the colors get cooler as the model becomes more complex. So you see we get decreased error and increased correlation for the models as they get more complex. And you also see that we get more error generally as we move up in frequency, which was the case before with the simpler models as well. Looking at that skill spatiotemporally, the maps here are for the 18.7 gigahertz channels in the red plots and the 89V channels in the blue plots. And then on the bottom, we're looking at it as a function of time. So the time plot RMSE on the left there, and then seasonal averages on the right. So looking at these maps, you can see again that as we move to more complex models, we get better performance, smaller errors. And then looking at the seasonal changes, you can see that the linear, more simple methods struggle to capture some of the seasonal differences. And on the map, you see that that's also a function of geography. Emissivity is obviously very hard to validate because this isn't something that we have global observations of. So in general, how we do this is we take cloud-free conditions, use the retrieved emissivity, put an atmosphere in, compute a top of the atmosphere brightness temperature, and compare that to observations. So here you see that validation technique for the 18.7 gigahertz from GMI. And so the OE panel on the left is basically our truth here. Any errors are coming from what we're assuming about the atmosphere. So that's the best we can get. And you can see that the really simple models don't tend to do as well, particularly over deserts. But as we get to the FTT, we see very good agreement actually with the OE retrieved emissivities. And looking at the time series plot on the bottom, we see lower seasonal variability compared to the covariance. We also wanted to see if we could generalize this. Like I said, the idea was that you would get the 10H from whatever method you chose. Here we were using retrieved 10H emissivities, but we thought, what if someone wanted to use a model? Or in this case, we tested it using the TELSEM2 climatology. So this is something that comes in the RT-TOF. And obviously is a very highly utilized data set. So we wanted to look at what the retrievals would look like if we used that as our input for the 10H. And you can see it performs pretty well. This is again for the 18.7 gigahertz TB on GMI. And in the top, you see the default using our retrieved values, and in the bottom, the TELSEM2. So, obviously we have some differences, it looks like, with definitions of coast, but if you look at the scatter plotter, considering there's no dynamic variability and it's a climatology, that's actually not too bad. And then this is just a pretty picture to show you what our retrieved emissivities look like across the globe for all 13 GMI frequencies. Well, I guess that's not all 13, but. All of this code is accessible if you would like to play with it. Fraser did this all in Python, so there's a Google Colab you can use to play around with, and also he has a GitHub with everything that you would need to train the model yourself and use it as a fun little sandbox to play with. These emissivity calculations are really important for understanding how these retrievals work over land surfaces, and in particular for data assimilation. For a long time, everything over land was thrown out in the passive microwave, but now that we're starting to get this better understanding, they can start to utilize that information, which gives more to the models. We leveraged here a 5-year global data set from GPM and SMAP, and like I said, it just takes in the 10H emissivity as its input, and then it maps out to all of your other frequencies using machine learning. We end up with R-squared values of 0.8, and above 0.88 for the lower frequency channels when compared to GMI. Using the TELSEM2 data also provides good overall skill, as I just said. And then I didn't have time to show this a lot in this presentation, but if you read Fraser's paper, he used explainable AI techniques to show that the model is really picking up on important soil moisture and vegetation features in the data. So we can get some sort of physical interpretation from this type of model as well. And that's it. I'm happy to take one quick question, or you can just talk to me at the coffee break. Any question?
Yeah, I was wondering about the configurations of each of the models. So you say that the transformer worked the best, but it wasn't obvious to me whether it worked the best because the architecture was better, or whether it had more complexity in how it was configured compared to the other versions of the models.
That is an excellent question for Fraser. I can take a look back at the paper and get back to you on that one. I'm not quite sure about the differences between those. All right, let's move on. I think, is Lisa next? Okay, that's right. Coming up here. All right.
All right, I'm back, and I'm going to talk about what people don't want to talk about. They always ignore the snowfall part of precipitation. So here we are. You can't go home without hearing about that. I want to acknowledge my co-author, Veljko Petkovic. He is the one who implemented the machine learning models here. And we are going to talk today about methodology to partition snowfall regimes into shallow convective ones and deep stratiform ones. And the motivation for which we started this project is linked to the passive microwave that are actually widely used for precipitation. They have good temporal and spatial resolution compared to radars that are narrow, and we only had so far 2 in space. And And compared to rainfall, snowfall retrievals are still a work in progress. There are several factors that influence the retrieval process, such as surface type, like Sarah just talked about, the emissivity and whatever can influence our observations of the atmosphere portion of the observation from the sensor, the coverage of snow, the crystal shape, orientation, density, water vapor, temperature, and so on. And whether our algorithms are based on machine learning or other methods, like the Bayesian methods we had so far for GPROF, the passive microwave usually need an a priori or a training database. And we all know that if the information is not in the database for the model, it doesn't exist. So we need enough and a good variety of examples to put in these data sets. Previous works showed that it is very important to determine the snowfall regime to help the algorithm recognizing the precipitation event that it is looking at. And here is an example. On the left top side, we have the MRMS, ground observations. This is the Great Lakes region in the US, and we have those very nice snow band lake effect snow. And on the right, we have the passive microwave product, GPROF version, I believe this was still version 5. It didn't improve that much with version 7, with this kind of things. That doesn't actually recognize the snow bands. But if we tell the algorithm to look into a specific a priori data set, in this case it's all snow cases, then it can do something better. So here came the idea of of building a specific a priori data set that contains the cases we want to recognize. And how we do that, we borrowed the Cooley et al. 2016 methodology that used a cloud set to partition snowfall regimes using reflectivity profiles, snowfall rate retrievals, and cloud classification. So every time we have a stratocumulus or cumulus, we classify it as shallow convective, and every time we have a nimbus stratus cloud, we classify it as deep stratiform. And then we take the combined data set of CloudSat and GPM. We use the 13 channels, brightness, temperatures, and the reference, as I just explained. CloudSat reference. The data set is pretty small. We use about 60,000 collocated pixels of CloudSat and GMI. The coincidence is among 15 minutes. And we use the 2014-2019 period, leaving out the 2016 for validation purposes. We use the brightness temperatures, difference of brightness temperatures, temperature, and humidity. And on the plot, we show the distribution of our classes that actually matches pretty well the distribution that Cooley et al. Found in their paper. About 17% is shallow, 80% is deep, and 3% is other than shallow and deep. So this is, it seems like a good data set, if it is, even if it is not so big. And we use the extreme gradient boost decision tree as a model, XGBoost. We put together four models to see which one could actually do better for our needs. And so the first one is a 4-class model. We do everything with it. We partition deep, shallow, other, and also no snow. So there's a detection component in there. Then we have a 2-class detection, so only snow and no snow classification. A 3-class that is applied only to snow pixels, and it tells when it's deep, shallow, or other, and a 2-class as well applied only to snow pixel and says when it's deep or shallow. And the pixel accuracy in classifying the classes goes between 75 and 85%, so it's pretty good, and also in volume, we go between 77 and 91%. And here is an example, a case study over the Southern Ocean. The bottom is Antarctica, and on the left side is our model, the result from our model. Red is shallow, green is deep, and blue is other. And then the line is CloudSat that matches this profile that I provided here. And you can see that the deep part is well recognized in green also for CloudSat. There's an overlap there in colors. I hope you can see it. And then the shallow part in red is also recognized by the model. On the right side, I put an independent data set. This case is 2016, so it's independent from the training data set. On the right side is an independent, independent modeled reanalysis from ERA 5. The partitioning is slightly different in concept. We have, in red, we have the convective snowfall. In green, we have the large scale snowfall. So I coupled it with shallow and deep, and overlapping is the CloudSat. And of course, the models don't put things in the right position all the time, so we have that big shallow that doesn't have a matching with the CloudSat. But overall, it looks very similar to what we predicted. And this is the global analysis. I ran the global model for 2014-19 on the whole GMI data set. So it includes a data set that we use for training, but has much, much more data in it. And on the top right panel is the CloudSat shallow cumuliform global map of the full operational period of CloudSat 2006-2010 that was published in the Cooley paper. So there is a little bit of overestimation in the detection of the class. This is the percentage of shallow convective snowfall. But overall, the patterns are very similar to the CloudSat one. And I think the two classes, not only on the bottom left, that uses the two class as a detection. So we detect with the two class model, and then we apply the two class deep versus shallow, does the best job. And then I did also for the deep stratiform, again, CloudSat on the top right. And in this case, the 4 class, the one that does everything, including detection, seems to capture all the nuances that are around, that are seen for a CloudSat. So concluding, we put together this snowfall type retrieval developed using a machine learning approach, and we use coupled observation of CloudSat and GPM GMI sensors. We use 5 years of observations. They offer only a limited training data set, but XGBoost seems to be able to provide good accuracy anyways. The best models achieve a weighted accuracy of about 80% for the 4 and 3 class problem, and between 75 and 79 for the 2 class tasks. They correctly classify snowfall amounts among the 3 regimes exceed 90% globally, demonstrating the potential of this machine learning model to extract information from very ambiguous passive microwave signals. And now future work include the improvement of the detection, understanding why the shallow is a little bit higher than what we expect. We think that it could be capturing also the diurnal cycle of precipitation. The clouds cannot capture, but we need to do further analysis for that. And also regional analysis in some areas where shallow convective snowfall is most likely to happen. And finally, we have the paper almost out. It's in review. We just submitted the second round review, so we expect to see it very soon. Thank you.
Yeah, just a clarification that when you say about when you separate snow from the rain, is based on the cloud set algorithm? How do you separate the rain from the snow in this? You are only looking at the snow, but what's your criteria to, is it that pixel snow or rain?
Right, CloudSet has a choosy snow product, so we are just training with snow products. And GMI most likely gets the information from the temperature, the 2-meter temperature.
Oh, is it like the wet bulb temperature?
No, the 2-meter temperature.
Air temperature.
It's as an input of the model, so it must capture it that way.
Okay, and when you say about shallow versus deep, is it 3 kilometer or what's the definition of shallow and deep?
The definition is based on the cloud classification of CloudSet, which is stratocumulus, cumulus, stratocumulus versus nimbus stratus. Most likely is around 3 kilometers, but there's a big overlap between the two. I didn't show that, that plot, but there's an overlap. So it could be smaller or shorter or taller than 3 kilometers, but yeah, more or less.
Okay,
but it's based on cloud classification, not simple altitude.
Okay, thank you.
All right, our final talk of the session will be from Ali, who's going to talk to us about high latitude and oceanic precipitation.
All right, so probably you see some bold fonts, and some of them are pale, kind of, because I figured out in 10 minutes probably I cannot cover everything, so I dropped some of the things in the title. So focus more on the high latitude precipitation assessment discussion. So these are some of the facts I try to just mention. So high latitude precip, specifically snowfall, remains a long-standing challenge, as Lisa also mentioned. Challenges are related to sensors, capability, retrieval methods, training data sets, and evaluation difficulties. Significant progress has been made, but not yet enough progress. We need more. The lack of robust observations, observational reference exists. We have gauges that are called rain gauges. They are not called snow gauges because of a reason, because they're really good for rain, not necessarily for snowfall. And then we have reanalysis products that are used for algorithm development, for training satellite data, and also for assessment. And Aero 5, we should admit that usually, and also regional models are doing fairly good job in high latitude and snowfall regimes. So we should acknowledge that, in fact, but we need to evaluate them as well. So snow quantification is important across multiple disciplines. This is not only precipitation community problem. It's a lot of people they care about the snowfall because the signature of the snowfall is the snow accumulation in SUI, and cryospheric scientists, hydrologists, everybody care about it. So I'm trying to kind of go a little bit out of the precipitation community and connect to the other communities that they care about it and see how we can use the convergence of everything we learn from different communities to help precipitation communities. So back and forth a little bit. So SUI and snow depths largely reflect accumulation of snowfall and are closely linked to snowfall, although factors such as melt, sublimation, and snow density are kind of complications and needs to be understood. Although snowfall and SUI snow depths differ due to the post-depositional process, their combined analysis provides valuable insight, specifically for snowfall quantification. Large increases in SUI often indicate significant snowfall events. Probably you agree on that. And both event scale and long-term assessment are useful. Each brings unique strengths and limitations. Now, I wrote an article in GVAX News, what's called quarterly news from GVAX, basically suggesting that we should look at it from different angles. It's not just precipitation community problem. This is like something that everybody probably can help because we have limited reference snowfall data in many regions. So let's look at everything together and see if we can learn from each other. And basically, we're talking about a complementary, a suite of tools that are available. I'm not trying to undermine the value of the gauges. I'm not trying to undermine even any point measurements that we have, but I'm trying to see, okay, we have collection of different things and different communities that can be used for our purpose. So I give you some of the examples through the work that I've been doing in the last couple of years. The first one is using GRACE and GRACE follow-on, which is basically monitoring the changes in the mass. So if you're talking about a region that we have limited melt or no melt, like very cold regions, then the change of a mass is mainly snowfall accumulation change. So, it's coarse scale. So we use that kind of, we look at the regions that are very cold throughout the season and calculated the mass change from GRACE and then link it to the snowfall accumulation and use that as a way to look at the rain gauge measurement of snowfall. So again, rain gauge is rain that is used for snowfall as well as a reference. Now, it's not a reference really. Rain gauges are not reference for snowfall, but is used. Now, there are multiplied, whatever measured at gauges are multiplied by a factor of 2, 1, from 1 to 3, because the undercatch correction of a snowfall is significant. You have to apply something. And we use GRACE to suggest some methods are better than the others, and that's the first time probably that satellite can comment on the ground truth observation in a way to help us understand the biases. We also look at the high mountain Asia using the closed basin where we don't have runoff, we don't have stream flow, so we can look at the mass within the basin and did some work. So a couple of papers on that published. And also we did stream flow based mass budget over the Arctic basins to look at how precipitation fits into the mass balance analysis and calculated back the precipitation and compare it to satellite and have some comments on that. Also, we did some analysis over Antarctic, which we also almost absolutely have no gauges there, and the only thing that we have from observation could come from, from GRACE or something like that, which is because the satellite used to have a lot of problems getting snowfall over Antarctic. So CloudSat gave us the first indication. I have a couple of papers on CloudSat. But then CloudSat has problem of sampling to some extent. So we use mass budget at each basin using combination of GRACE for the mass change, like a snow accumulation, and also radar and Landsat images to give us discharge, because these are basins, but we don't have a stream flow like the way that we have in hydrology. These are ice flow. We almost have no stream flow. So we reach out to people who are expert in these and calculate the ice discharge and then try to close the budget and calculate precipitation on each of these. Now, this is the solution. I don't know if I have a pointer or something, but the cursor doesn't work. So the one in the box is the precipitation rate calculated from the water budget using ISAT, using a combination of radar and Landsat, and GRACE and ISAT, which is a completely different topic, but that's what we think is observational based. And then the bottom part is GPROF version 7, which you can see the significant underestimation. And the middle row is the GPROF version 8, which now becomes something that is comparable. I mean, this is one area that we can learn a little bit from what other observations, because I remember Chris was talking about version 7, we are underestimating. But what's the reference? I mean, that could be something that we can get some insight, and the version 8 already uses the insight to improve over whatever used to be. And the other one is the sea ice. I mean, this is a region that we have nothing, right? So, however, ISAT, CryoSat give us snow depths, and they have some sort of uncertainty about it, but they're fairly good these days because they need it for ice thickness calculations. So we use that kind of a snow depths and using some sort of models that cryospheric scientists use, in this case NESOZIM, which is a Goddard-based product, and then calculate it. I mean, that you have to track sea ice to accumulate it because it's moving, it's not fixed location. So that model is really tracking as well as accumulating at the same time. And then you can compare with satellite products, and we have papers published on that, how we can use these products to assess satellite product. This is out of that, and we haven't done the version 8 yet, but version 7 showed a lot of problems with respect to pattern. I mean, the bias was much better in the version 7 compared to version 6 of iMerge, for example, but the pattern got worse in version 7 compared to version 6. You may probably link it to the issues we had with the combined product used for calibration of some of the microwave products. But anyways, the bottom line is these are a way that we can assess the convergence of different methods and at least help us to better understand if we are converging or not. If we are converging, that's good. If we are not converging, then we have to think about if we are doing things right or not. I mean, that's the kind of alarm or warning sign. And lastly, another one within the limited time I have is the kind of using airborne observation over glaciers. That's the reason that we have terrible situation, right? I mean, it's very difficult to measure snowfall over glaciers, but we have airborne observation previously under the OIB mission of NASA flight. And then we did some analysis because they have radar to measure this snow depths and then convert it to SUI and then compare it with satellite. So we did some work on that. But the good thing is when I was doing that, I hang out with glaciers experts and cryospheric scientists, and we came up with idea. We proposed it under EVS4, the Snow for Flow mission, which is basically trying to look at the glacier mass budget, and snowfall is part of it. And that proposal that we wrote together funded, and now EVS4 is a mission for studying the mass budget of glacier, including snowfall, and that's very new, and flight is going to happen next year. So this is how we can learn from each other in the community. I'm trying to advocate for that type of thing. So a lot of things in this can come together in this image to help us better understand the earth science using multiple missions. That's the idea. Thank you.
All right, I'm going to suggest finding Ali during the coffee break. We are done now until please be back at 4 o'clock. And to close out the PMM session, I just want to say it's so fantastic seeing all the work that all of you are doing with GPM and the other PMM mission components. And, you know, we're fighting every day to keep GPM and precipitation science going at NASA. So please send us your highlights. Please email me as you're publishing and doing all of your cool science. And we use those highlights to show headquarters and move up the chain to hopefully keep all this great work going. So thank you all very much.
See if mine will actually run and with the
The posters are right outside the coffee break area.
yeah, they are
the
small,
hallway.
but they are hanging on the wall, by the side of the.
So the entrance to the coffee break area, if you look right over that area, they're on the wall.
I'm glad I, put the voice in there because my eyes are not that great.
Yeah, and this is a bit small.
Yeah, I need new glasses. Okay, great. I use this.
Yes.
I don't hear anything.
You have to.
No, it's not connected. So that's why we probably need. No, it should start automatically. The problem. The problem is that if I can hear it now here, but not there.
This is on or off?
Because
presentation is about the Open SSP portal grand reopening as a milestone towards the much more ambitious NASA PassDB.
I'm not sure if it's. I don't think it's gonna.
Maybe the sound system is actually off.
Oh,
we're
because.
on a coffee break. Could be.
You're right.
Hey, yeah, but even this is it's not on. Yeah, it's not on.
Tutu. 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 Tutu.
Okay, yeah, it works. Well, welcome back to the second session of the afternoon. Title is Bridging Models and Observation for Advancing Precipitation Science. We are going to start with Daniel Waters. Ground validation of the Tomorrow I/O Pathfinder radars over the continuous U.S. I hope people outside can hear me so they come in.
There we go. Can you hear me now? Okay, I'm going to talk to you about ground validation of the Tomorrow.io Pathfinder radars over the contiguous US. And again, I'd like to acknowledge my co-authors. Okay, so an overview of this talk. The idea here really is to quantify the performance of these commercial satellite radars, which are the first commercial radars in space, and I think only the 6th and 7th cloud/precipitation radars ever to be launched into space. And in particular, we're looking at their surface precipitation retrievals. The motivation for this analysis is in terms of novelty. As said, it's the first 2 commercial satellites to be launched with precipitation radars. There's a real complementarity factor here. So the reason why we want to look at the performance of the Tomorrow.io radars, a bit like Ethan alluded to earlier, is that there is the potential that they can complement the NASA JAXA Global Precipitation Measurement Mission, but also what comes next. And then at the minute, there's unknown quality. So outside of Tomorrow.io, there's not been an assessment of the Tomorrow.io radars. So there's some novelty in that. In terms of the radars themselves, there's 2 Pathfinder radars. Both were launched in 2023. The first radar, known as R1, deorbited in late 2025. Radar 2 is still up in orbit. Both are Ka-band radars. They both have 5-kilometer footprints, just like the DPR. On board the GPM Core Observatory, apologies. But the altitude is higher, and in particular, they have sun-synchronous orbits. In terms of ground reference, we use GV-MRMS, MRMS just being a mosaic of ground-based radars across the US, mixed with the gauges and model information. And the GV component of that is that MRMS is tailored towards spaceborne validation activities via quality and quantity control procedures. In terms of the framework itself, the validation framework, it's really an intercomparison between the spaceborne radars from Tomorrow.io and the ground-based GV-MRMS product. The analysis period is short. So so I should preclude this by saying that this work forms part of a quality assessment requested by NASA to evaluate how the Tomorrow.io Pathfinder radars were performing. NASA only had access to a short amount of data from tomorrow.io. So in particular, Radar 1 had data from October 1st to November 30th, 2023. That's approximately 61 days. And Radar 2 had an even shorter period of only 21 days in October 2023. There we go. Okay, so into the results. The first one, so what do the radar samples look like? With a shorter amount of data, it's interesting to look at what the maps are like. Is there any biases in where the kind of radar is sampling? And there was. So you can see that on the right-hand side of both maps, you might see that there is kind of regular resampling over the Boston, Massachusetts area, which is one of the areas where tomorrow.io has an area for calibration. And you can see that in terms of the sampling itself, R1 has 60 days, 61 days of data. There was about 500,000 precipitation sampling data points within that time period. And for tomorrow R2, you know, about half the data sample, so about half the amount of precipitation cases. Okay, so we split our results into detection and quantification. So the first question we asked is, do the radars have the capability to detect precipitation? So we're really looking at the ability to delineate between rain and no rain. If you look at the contingency tables, R1 on the left and R2 on the right, you'll see that the radars both exhibit skill in detecting precipitation. They detect both precipitation and no precipitation correctly about 82% of the time. We're seeing that in terms of differences between the two radars. Radar 1 slightly outperforms Radar 2. It had an enhanced ability to detect instances of no rain. That's the correct rejection you'll see in the bottom left-hand panel on both of the contingency tables. And what comes with that is that Tomorrow R1 had a much higher Heidke skill score. So a Heidke skill score is of about 0.3 is considered to be very good for a delineation of rain and no rain. We saw that with Tomorrow R1, because of that ability to correctly identify no rain better than R2, that it was getting a Heidke skill score of about 0.38 compared to about 0.27 for R2. In terms of quantification then, we started by breaking down the analysis into the probability distributions for rain rates from both radars. So we did this both by occurrence, which is denoted by the letter C in the plots, and also by volume of rainfall, which is denoted by the letter V. And what you can see is for Tomorrow R1, particularly looking at the volume here, you can see that on the higher end of the precipitation spectrum, so approximately above about 7 millimeters per hour, that the R1 radar, the black solid line, compares pretty well to GVM RMS, which is the gray line in the background. But you can see that on the lighter end of the rain rates, the rainfall volume, it's not doing so good in capturing that part of the spectrum. You then flip that with R2. R2 did a better job with the light and intermediate rainfall below 5 millimeters per hour, but didn't do such a good job with capturing the extremes. Onto the density scatter plots here. This is where we got kind of information on kind of mean absolute bias and other kind of core bulk metrics that we could extract. So you can see here that the Tomorrow.io radars had a tendency to underestimate precipitation, both of them. On average, the Tomorrow Radar 1 would underestimate by 22%, and Tomorrow Radar 2 would underestimate by 6%. So there was a bit of a discrepancy there in terms of the mean absolute bias. But if you look at every other metric in the bottom right-hand corner of both plots, you'll see that Tomorrow R2 had substantially better systematic error, random error, and correlation coefficient metrics. In particular, you'll see that the correlation coefficient for tomorrow R1 was 0.73, and for R2 it was 0.93, which was a big jump between the two radars. We also tested R1, so we didn't know if it was a sampling thing, so we subsampled tomorrow radar 1 to October 10th to 30th, like radar 2, but that didn't change the results. So there seemed to be some discrepancy there between the two radars. We then also looked at the kind of typical GPM performance plot. So what I mean by this is that in the early days of GPM, one of the ways in which it was evaluated at the higher NASA levels was by its ability to get systematic errors or mean absolute bias within a certain range, and the same with random errors. So that's what we've done here. If you focus on the green triangle, you'll see that these are the NASA requirements, GPM mission science requirements at about 50 kilometer scale that were required for GPM back in the early days. We were evaluating Tomorrow.io radars at their native resolution of 5 kilometers. And you can see that at much finer resolution, they're actually doing a really good job of satisfying those mission requirements from NASA, with the mean absolute bias being satisfied for both radars. You can see Tomorrow Radar 1 in blue and Tomorrow Radar 2 in red. And you can see that it's with random error that's where they were just outside of the mission requirements at certain rain rates between 1 and 10 millimeters per hour. However, note that the scale is much finer. So if you were to go to 50 kilometers, I think we could safely assume that it'd be within those mission requirements. Okay, so to conclude the talk, I've just kind of highlighted in green here the key parts. The precipitation detection performance of both radars is good, the same with the quantification. Both radars have a tendency, on average, I should stress, to overestimate light and underestimate heavier precipitation rates. And the Tomorrow Radar 2 outperforms Radar 1 overall, with Tomorrow Radar 2 typically having a lower bias overall and smaller random errors. And in terms of mission science requirements, they're satisfied for systematic errors at the 5 kilometer scale. And just to note here, there is a QR code. This analysis has been put into NASA's Tomorrow.io radar quality assessment report, and you can find it at the QR code, and it's currently being advanced into a paper with an evaluation relative to GPM as well. Thank you for listening.
Thank you, Daniel. Are there questions? I see 3. We start from the top. Sorry, Chris.
Yeah, I was wondering about how you do the matching between MRMS and the Pathfinder.
So the matchup was performed kind of using typical kind of spatial temporal matchup techniques. The GVM RMS is provided every 2 minutes, so we would take the 2-minute interval where there was an overpass by Tomorrow.io radar, in particular making sure that each footprint was temporally matched correctly to GVM RMS. And then it was the typical kind of spatial matchup that we used the Gaussian weighting pattern that's typical of a kind of spaceborne radar when we were averaging the GVM RMS at 1 kilometer up to 5 kilometers.
All right, thanks.
Thank you.
Ali?
A couple of things. Can you interpret a little bit why R2 overperforms R1 for a heavy and vice versa for R1? I mean, what's one of your conclusions there? You know, radar number 1 is in the better lighter, and the R2 is the better in the heavier radar. Why is behind? What's the reason behind that?
That's a good question. We didn't have enough data to kind of get into the intricacies of that. And for the NASA evaluation, it was, the key thing was to get kind of certain analyses done. So we didn't dive further into that, but that will be something we'll look further into going into the paper.
And you say that you did your study over the Boston area in Massachusetts?
No, sorry, I should stress the whole analysis was performed over the US. What I was showing here was everywhere where tomorrow.io radars passed over the US.
Okay, every place. Yeah.
Yes.
Okay.
It was just to highlight that there may be a little bias towards that. There may be a little bias towards that part of the US, but for the most part, it was well sampled within the kind of one.
And did you take only RQI is equal to 1? Only that database from the MRMS perspective?
Yes, we did, yeah.
Okay, thank you.
Right, last quick, Chris? No. Yes? No? I already answered. Okay. Thank you, Daniel.
Cheers, thank you.
Next speaker is Ana Nunes, reviewing past strategies and examining new approaches on the development of hybrid observational modeling datasets.
Thank you. I give a PDF talk because I was not sure about how it looks like. And I have a lot of the slides. I'm sorry about that. Oh, no. It's good. How do I change this? The same. Okay, this one. Okay. Thank you for having me here. Good afternoon. My name is Ana Nunes. Something happened. I don't know what it is. Okay. Oops. Okay. To talk about a little bit, it's quite a shift of subject in this talk, but it's more like using satellite-based products inside the model through a simulation of precipitation. So I'll talk a little bit about the beginning of this. Explain that this beginning with a technique developed by Krishnamurti in the 80s. And I used this FSU, Florida State nested regional spectrum model at Florida State when I was there. And I kind of took this idea and changed something to improve not only short-term predictions, but also do a kind of a project of mine that will be a South American reconstruction, hydroclimate reconstruction in South America. I'll talk a little bit about this. So this is the Krishnamurti approach, and they use, in fact, physical nudging is actually precipitation assimilation. And this is the model running from day -1 to D0, and you have a physical initial conditions initialized using a combination of precipitation assimilation and Newtonian relaxation at the time. He didn't use the term of physical nudge. I did. It's not actually, it's a reverse of Cool scheme that was very popular at the time. Sorry. And we use this for improve the initial conditions using a threshold for 10 millimeters per day, using at the time SSMI, OLR estimates. They are daily at the time. So this is more or less like you look using the global model at the top and a regional model at the bottom. These are for 10 cases we analyze at the time. Steve Cocker was the person who actually developed the regional spectrum model at FSU, and I use his model, and also the global model. So we have a pretty good correlation with the assimilation with the satellite-based estimates at the time during the assimilation period, improve a little bit the equitable trade score, and you have improved also the predictions. So in the bottom, you have the predictions, 24 hours prediction. You don't use the initialization, precipitation time in the predictions, okay? This is just predictions. This is interesting. This is actually initialization or not. It is, because if you look at precipitation surface pressure at time step of the model during the assimilation period and afterwards, you can see there is a dump of high frequency in the model if you can get that if you don't do anything. So most people who use model, they think they run 24 hours or less, or 6 hours, and they'll have a good dumping of the fast waves, high frequency waves, but that's not what happened. So you have to do something, data simulation, initialization more formally, or you can have the short-term prediction contaminated by this kind of waves. This is a case using CIPTEC, a global model. This model was developed at the time in Brazil. It's actually a color model from US they used at the time. And we did some sort of a simulation using the technique developed by Krishnamurti at the time. And this actually, the SSMI estimates they are daily. That was the problem at the time. And this, you have the physical nudging only. This is a low-level jet. You have dynamic nudging, what's Newtonian relaxation. That's don't make the precipitation near close to the SSMI-OLR. You have the reanalysis just to look at the low-level jet. And then you have the physical initialization, which have physical nudge plus dynamic nudging. You have the jet, but you don't get the mesoscale convective complex you have in this particular area in here. This is because the scheme was good in tropical areas, but not so good in subtropical areas. So this is looking at the high levels. It's still you have the subtropical jet, but you don't have the MCC at that place. Well, okay, so we go back to Brazil afterwards, and then after a time at Scripps as well. And, well, we use a different model, a regional spectral model from NSAP at the time, using CMORPH now as the satellite-based precipitation, combined with something different from Newtonian relaxation, this spectral nudging. This is selective scale dumping towards in this case, towards the reanalysis. So the results, okay, you redo the same case, now reduce the threshold, you have a different model, different boundary conditions, and you also have a different scheme. Now it's really a physical nudging. Before it was kind of reverse parameterization. This one is actually nudging. And we got from CMORPH, it's quite similar to the SSMI-OLR actually, and you got with physical initialization or precipitation simulation plus spectral nudge, you got the complex, the MCC in the area, apparently should be. And we don't have we don't have this with only nudging, and the control doesn't get anything near close. So it's not the spectral nudging that's doing a good job alone, is actually the assimilation of precipitation, what is important. This is the upper level jet showing that MCC should be in this area. Is kind of dynamic theory, ideostrophic circulation plays this kind of phenomena at that particular area. Okay, so, okay, we kind of got somewhere and get a little bit encouraged and go to a stream event using that particular scheme I just showed you, but with a different threshold, 5 millimeters threshold. There's a CMORPH in here, and this is the model. Okay, there is a simulation, continuous assimilation. This time is not for weather prediction, it's more for a continuous assimilation, like sort of low-cost regional reanalysis. So you have the phenomenon from CMORPH, you have the mean sea level pressure from the model, and the rain and the precipitation simulated by the model. Sky very, very close to the CMORPH, what's being is put inside the model to correct the moisture profiles. And that's it. It's from a paper, actually. This is the climate forecast system analysis. This is the Catarina event, was a sort of first registered storm-like hurricane in South Atlantic, Western Basin. So we can see that This is humidity, it's relative humidity, and this is the winds. They're very similar, very kind of convincing in terms of hurricane structure. Okay, so this is using the assimilation. Note that initial condition is several years before the phenomenon. So it's really assimilate precipitation and keep the model going, okay? So that's another application. Former student at the Department of Meteorology from my university is trying to figure out, we submit a paper about this green vegetation fraction, and he used NOAA LSM, and it's a land surface model. We call classic NOAA, but it's not the MP NOAA, for this station points from LBA, and use this product, continuous assimilation, atmospheric forcing for this kind of simulation, for 6 years simulation he did using NOAA LSM. Okay, now you're looking this same particular product for the Amazon drought to 2015, 2016. And these are the products that we use as kind of reference for comparison. Okay, so we have for soil moisture glean, area 5 for precipitation, ships you use for actually the old version of ships. Now they have a version 3. And the satellite enhanced regional downscape for applied studies. That's the product I was showing you before. And this is kind of some points in this particular drought. This is a SPI, standardized, standardized precipitation index for 6 months. And what you see, this negative values means that you have a kind of precipitation. It's based on precipitation only. You have a deficit on precipitation. This is really extreme drought. But it's very curious because you come from something that's humid, wet actually, and go straight to drought conditions and go back. So this on the top was the CHIPS 2 version. Anomalies from, I think it's what, December, January, February, I think so. And the mid panels have R5 for the anomalies, and in the lower panels you have the satellite enhanced regional downscale for applied studies anomaly, and somewhere actually in the right you have the correlations with CHIPS. And then you have for soil moisture glean and the satellite enhanced regional downscale on the bottom. Show also for the anomalies, soil moisture anomalies for the first layer, 10 centimeter layers below ground. You compare. There's a comparison, and it's not bad. It's a Pearson correlation coefficient. The key takeaways. This is a prototype. I'm going back to this. I'm changing the model. I'm going to put different boundary conditions and try to revise the physical nudging using many types of satellite bases probably than I can have in my hands to use. But the idea is that you use Newtonian relaxation or spectral nudging, and you can do the precipitation simulation to improve initial conditions for short-term predictions. In tropical areas, it does pretty good. Continuous assimilation could actually reconstruct a hydroclimate in some areas in the world or even globally. I recommend tropical and subtropical areas. You have a simulation of satellite precipitation estimates could enhance simulation of extreme hydrometeorological events, and you can use as well for improve initial conditions to seasonal to subseasonal predictions. That's all. Thank you so much. Oh my.
We'll keep going with the last speaker of this session, which is Ho-Sheng Guo.
Oh, this is.
He's going to talk about OpenSSP portal grant reopening, a milestone towards NASA PAS.
You use the left, right, or up and down to advance?
Left, right.
Left, right.
Yeah.
Okay.
I think it is.
You think it'll work? Well, let's see if this works. To better control the times, I pre-recorded the audio. So. Doesn't seem to work.
I think you have to press here.
No, I have it set to. I'm known to be a troublemaker.
Sorry.
This reopening as a milestone towards the much more ambitious NASA PAS-DB.
Okay.
This presentation is about the. Here's the outline of this talk. I will briefly introduce OpenSSP and the rationale behind it. Next, I will summarize what has stayed the same and what has changed. Then, I will envision what can be expected as it evolves towards NASA PAS-DB. Finally, we will conclude. So, what is OpenSSP? Why do we need it? OpenSSP stands for Open Single Scattering Properties. It represents two things. It is a database of numerically generated realistic solid hydromedias and their single scattering properties, SSPs. It also refers to a web interface, a portal, for interested researchers to access and obtain particle structures and their corresponding SSPs from the database. This is an example gallery of solid hydromedias offered by OpenSSP. The animation on the left shows the growth of a pristine crystal or snowflake. To its right, we have pristine crystals at the top. Below them are examples of aggregates formed from snowflakes of different sizes, but the same habit. You may find more details in the references listed at the bottom of the slide. These are photorealistic eye candy animations of two aggregates rendered with ray tracing. Why do we need OpenSSP? This slide explains the need for realistic irregular hydromedias in physical precipitation retrievals. This is figure 6 from Olson et al. 2016. The observed microwave radiometer brightness temperatures at 89 and 165.5 gigahertz are shown with thick dashed lines resembling railroad tracks on maps. The thin lines represent simulated brightness temperatures derived from radar retrievals. The left pane compares brightness temperatures obtained from fluffy spheres with 3 different densities. They cannot match the observed, especially for the 165.5 gigahertz. The difference can be as large as 40 Kelvin. When the realistic particles of OpenSSP are used, on the right, the agreement between the observed and the simulated improves drastically. Another driver for having OpenSSP is resource economy and sustainability. Both the generation of realistic hydromedias and the solution of their electromagnetic scattering are computationally intensive. These processes also generate large volumes of data. Resource demand increases further with advancements in instrument technology, such as expanded spectral coverage. Most researchers cannot afford the resource expenditure. Compounded by dwindling research support, the outlook is dim. Therefore, it is more economical and sustainable to have a place that can receive community contributions. OpenSSP is the beginning of such a place. At this OpenSSP grand reopening, what remains the same as before and what has changed? The underlying particle structure and the scattering property data have not changed. The interface remains mostly the same, except for the login page and the login process, which we will describe in the next slide. It still has the same tabs for getting different subsets of data. Pristine, aggregate, modeled PSD, scattering data package, particle structure, and MD and PSD tab, which may be the most useful. Users can use it to sample the database for particles according to a given particle size distribution, PSD, constrained by a mass dimensional relation, MD. After submitting the query, a plot of the PSD will appear. One can also examine the individual particle properties selected for the mass dimensional relation. What is different? The URL has changed. It is now at particlescattering.org. Logging into the portal still does not require a password. A user only needs to provide a valid email address to receive a one-time passcode. Enter the one-time passcode to log into the portal. The more consequential change is invisible to the users. We have replaced the backend HDF file with an enterprise-level database management system, PostgreSQL, to improve performance and versatility. What can we expect as we evolve towards NASA PassDB? Under the NASA PassDB initiative, we can expect more diverse hydromedia structures and scattering properties. We plan to implement a mechanism for the community to upload and ingest their particle and the scattering data into the database. The PostgreSQL DBMS will enable more flexible queries, allowing users to get exactly what they need. Microwave single scattering properties of irregularly shaped hydromedias are the initial focus of NASA PassDB. Next to include will be the melting hydromedias. We plan to expand eventually to a wider spectral range beyond microwave and to different species of particles with different compositions. Now we summarize. OpenSSP is back in operation at a different but more memorable URL. OpenSSP's web interface remains largely the same, except for the logging process. The most significant change is replacing the HDF file with a database management system. A mechanism to accept community contributions is planned as OpenSSP evolves into NASA PassDB. We aspire to significantly advanced atmospheric particulate remote sensing with NASA PassDB. That's all. Thank you for your attention.
Thank you, Kuo. Any question before we open the discussion session? No question? Okay, if you think a last minute one, Kuo will be around. Thank you all, and I invite Jessica and Chris for the discussion session. Thanks.
Okay, I hope you guys have some energy because we're going to discuss things, right? It's not just going to be us talking to you. We have provided a few slides to help prompt discussion. But just to start off, my name is Jessica Sutton. I'm a researcher at the University of Maryland, Baltimore County, and I'm also on the landslide team at NASA Goddard. And my role there is to look at precipitation and how we can use precipitation in landslide modeling. And so I've been asked to help lead this discussion. My part of this will be kind of leading it with AI in mind. It is not my expertise, but I hope that hopefully we can have some good discussion. We've already had some really good discussion started earlier, and we're going to kind of come back to that. And Chris, if you want to come introduce yourself.
Sure. Thanks, Jessica. Hi, everybody. My name is Chris Funk, and I'm the director of the Climate Hazard Center at the University of California, Santa Barbara. For many years, we've worked really closely with the Famine Early Warning Systems Network. I'm the lead developer for the Climate Hazards Infrared Precipitation with Stations database, and also both a big user of satellite data and a liaison between this community and a lot of people in the developing world who use satellite rainfall. Thanks.
Thank you. Okay, so I'm going to just kind of go through some of the discussion topics. If we can't make it through all of this, or we're really wanting to talk about something else, we'll kind of adjust. But from Chris and I talking, these are some of the things that we thought might be a good parts to bring up and discuss with the entire group. So the first is data accessibility, right? One of the things that we have seen in our community is data accessibility issues. And so that's something that we want to kind of bring to you. We all range in where we're at. Some people are algorithm developers. Some people are people that are actually using it for analysis, like me for landslides. So get that feedback. Barriers to accurate, effective, and authoritative applications. So thinking about what are current barriers and what might be in the future as we're moving forward, and how can we reduce those barriers now and in the future. And then really getting to this topic of AI and what are some current challenges, what are challenges that they can pose to our community in precipitation and the applications community kind of broader. And then how might we overcome some of these challenges, and really trying to hopefully not just stay on the negative, but like how can we improve applications in the future. With that, I'm going to hand it over to Chris.
Okay. Yeah, thanks. And the way we're thinking of structuring this is going to be in sort of 3 sections where we'll present a few slides to kind of prime the pump, have a few minutes of discussion and then move on to the next. So one kind of way of thinking about what we're doing here is this idea of transforming data into wise actions. So we might begin with infrared and microwave brightness temperatures, images, profiles, all the input data that has been talked about today. Then we can translate that kind of raw observation information or into information, right, where we might look at rainfall rates, wind motion vectors, snow versus rainfall, snow types, all kinds of different information, right? That's not necessarily directly usable. So then another important part of the value chain is to translate those values, that's information, into some type of usable impact information, right? So is the farmer going to have enough moisture to plant? Do we have to worry about flooding in a certain basin? And this is a really important part. And I think, Chris, this gets back to the questions of uncertainty, right? So it's uncertain for what? And it depends on whether you're talking to a farmer or, the Western US. And then finally, of course, there's a need to translate impact information about outcomes into recommendations and wise actions. And I very carefully, or very seldom, get to the far right of this image, but we're working hard to try to take data, transform it into information, knowledge, and then wise action. And I think there's ways that barriers can be reduced for this flow. So I don't know how much traction this topic has for this particular group. It's not something that I know about, but as a developer of the CHIRPS data set and as a provider of this information and other information resources, data accessibility is, I think, a big challenge. And as the resolution of precipitation data increases, spatially and temporally, the volume of data grows. So, it used to be monthly data was okay, right? Now we're down to like sub-hourly data for the globe at 2 kilometers. And so that's going to scale, and that creates a lot more problems. Many data providers are serving data via FTP or some kind of traditional sort of data storage and dissemination, and that includes the Climate Hazard Center. We've got hundreds of terabytes of data out there that people have to download in very onerous ways. And many users want data over time for a specific location or a spatial subset, and I think in general, we're pretty far behind what could be done in terms of these technologies. So I thought it would be an interesting 5-minute discussion for this community is what new technologies are emerging that can help address these challenges. So maybe we want to open up the floor to anybody who wants to comment on that.
And I'll just run around the room like this.
I developed a technology called Spatial Temporal Adaptive Resolution Encoding under NASA Advanced Information System Technology Program. So that technology, I think it will be very useful in addressing the issues, the challenges that we encounter. Say, for example, right now, if you want to fuse or merge, combine different data sets, and they are of different spatial resolution and so on. And the first thing is that most people do right now is that you reproject it to a common resolution, a common projection, and then you do the merging after that, right? So, but in this process, when you are reprojecting, then you are basically resampling or interpolating the data to a common projection or grid or resolution. So this is the first thing, and that is a lot of pre-processing you have to do. And then there's this intermediate data that you reprojected, but that is only for your use. And so you are creating more data, which essentially has the same information, as the original data you use to do the reprojection. So you kind of aggregate the data volume problem and the data variety problem. So we call it STAIR, spatial temporal adaptive resolution encoding. That allows you to actually merge data in their native resolution. You don't have to, it doesn't preclude you from reprojecting. And sometimes that's what you have to do. But then, but you could do a lot of stuff before you do the reprojection. And also, because this helps the process, streamline the process, right? You don't need to save the intermediate data. You don't need to save your reprojected data. So this is a typical, classical, storage versus computation speed problem, right? So if you have enough computation speed, and you don't need to save data and waste storage. But if you want to gain computation speed, then you probably store. A typical example is like our lookup model in a lookup table in retrievals and whatnot in the remote sensing. So the reason is that it's very time-consuming to generate the table on the fly. So we generate it first, and then we use that for lookup. I mean, it's similar to that. But nowadays, I think most of the agencies are moving their data into the cloud, which is, it solves part of the problem. So you go onto the cloud to do your processing. You no longer have to download the data. But the next stage of the problem, next level of the problem is that how do you actually effectively, efficiently merge the data together to do integrative analysis? And that's where STAIR can help.
Thank you.
Sarah? So accessibility sort of depends on the users, right? So I've been thinking about this a lot because I have some very young interns working with me this summer, and I wanted them to have the ability to look at precipitation in a certain place at a certain time, and they can't necessarily write a Python code to open up a netcdf file. So I think we're getting better with things like apps, Earth data, Giovanni, ways to visualize things. I do think we're moving to making that more accessible. My bigger question is, as excited as I am about working with our new commercial partners, when you talk about farmers being able to access this data, we're getting told sometimes from the top, do we really need to keep doing this now? Because the commercial companies are doing this. But we provide the data for free and make it accessible to everyone. That is not the case for the commercial companies. And so I'm concerned about them being locked out on accessibility if we don't continue to work together and make things accessible to all of those types of users. That's my 2 cents.
So I'm wondering if we're even asking the right question, right? I think it was Ethan who said, you look for a problem that someone's willing to pay for, and then we'll go solve it, right? I've talked to people that wanted precip data that, in the farm community that said, oh, just give me, green, yellow, and red, my people will get lost if you give them any more than that, right? They need very clear instructions. And then you tell the next farmer that, yeah, we're just going to give you green, yellow, and red. He says, I can download the Python and write my script, right? So I'm not an idiot, right? So every community has all kinds of needs, right? And so sometimes I think that we try to overguess, right, what the community needs. The private sector is pretty clean. Who's willing to pay me for what? And I will make that if the money's enough, right? That's how it works. So by not having that, sometimes I think we just, are struggling trying to figure out who the customer is, and maybe we need to just really define who the customer is and what they want, and not try to guess what it is they want.
We will take one more comment and then I'll push out because I want to leave Jessica time too.
Yeah, I think to your last point, specifically about new technologies, like we found kind of internally with respect to like validation, we have two, and you pointed out there basically two problems. You either want data over one point for a long time series, or you want some sort of spatial subset on a short time period. And for me, the like revolutionary thing has been cloud optimized data sets like ZAR, because under the hood, it can figure out the exact byte. Like, you're not downloading 400 megabyte CMB files to get like 2 scan lines. It knows exactly the byte range based on the metadata that it downloads from the cloud or even from your own computer. So I know, like, on the commercial side, we're really trying to embrace this. I know there are other like Earth Mover like companies that are trying to partner with the government, but I think we need to move beyond just like NetCDF and HDF5 to have more abstracted and more approachable data sets for people who are non-meteorological experts, because those are ultimately our end users.
Okay, good.
That sounds great. And I guess I just might ask whether, cloud optimized ZARs could be combined with stairs and those kinds of approaches. That would be pretty cool. There you go. Okay, so thanks for those great comments. And I think in order to save time, we'll just go on to the next one. Data accessibilities challenges. Discussion 2 topic. Barriers to accurate, effective, and authoritative applications. And we might ask, what are current barriers and how might they change in the future? And how can we reduce barriers now and in the future? And I'm just going to indulge in a few slides as we go. So, there are emerging technologies like model context protocol, different ways to have our data sets exposed to AI. I mean, we've also been in our group working with different development companies like JotAware that are using AI actions to process data, like go out and grab these 3 different data sets and put them on a common grid and do a lot of things that we might do manually by hand. This is just an example of one of the ways in our group that we're playing around with using AI, not to transform data into information, not to estimate precipitation, but instead to take information products and translate them into analyses, and so kind of down the value chain. And so we have developed for Ethiopia maps and time series of rainfall, and we want to transform those into textual descriptions of how the season is progressing. So my friend Diego Pedreros has taken just the raw maps, not the data, not the time series data, but like maps of the time, and put it into an AI. And so basically the inputs are like those on the left, and what came out the other end with a lot of crafting of the prompt, is this. I'm not going to read this, but it is in good English, which, having worked for years with Diego from Colombia and Deriba from Ethiopia, trying to craft, grammatically correct English descriptions of this stuff, just having things written well can be important when you're trying to work in the developing world. So anyway, it's a pretty neat example of how you can take sort of raw information products and translate them into analyses that could be relevant. But on the other hand, many important applications of precipitation data require homogeneous and deep historical records. So if your widget is going to tell you that it rained 100 millimeters in Omaha, that's not, from my perspective, really much information, right? You want to be able to put things in a deep historical context. You want to have that information be authoritative so that you can have a drought declaration, or when Cyclone Freddy comes in and drops, a huge amount of precipitation on Malawi, the African risk capacity can trigger, a big payout for the insurance for the countries. And I worry about opaque products leading to a lot of confusion. Ironically, the difficulty associated with transforming satellite data into precipitation estimates has helped enforce reliability and supported authoritative products. So a lot of us are here because we started in the early days when it was really difficult to do this. What happens when it gets really easy and everybody can play? what happens when the authority disappears. So we can imagine the future where Claude says, you say, hey, Claude, use all the GOES 16 imagery on earthmover.io to estimate rainfall in Guatemala, then develop a rainfall-based index insurance scheme for drought, and a flash flood alert system. Oh, and start sending out alerts via SMS, right? This is something I think that's going to be coming soon, and I do think it poses a risk. So I open the floor to discussion.
Sorry to be such a show-off, but anyway, we recently developed an agentic AI for actually geodata analysis reproduction. So basically, it reads a paper and then reproduce the study, reproduce the analysis, reproduce the figures in the paper. Okay, so we use a study that was published in 2013 using 12 years of TEMPA data, the iMerge predecessor data. And then our purpose at the beginning was to evaluate reproduction of the reproducibility of a research. But then we found out that, while we were doing that, the paper used TEMPA version 6, but TEMPA version 6 is no longer available, so the latest version is version 7. And that speaks of what the challenges you have in the reliability and so on and so forth, because these data products, they are advanced and they are improving, and then we don't usually keep the older versions. So some of so in this example we have we are publishing we're submitting a paper to the ACM 6 Spatial actually this weekend. We could reproduce the data almost exactly using the version 7 data, but there are some differences.
Thank you. Others? Oh.
I don't know if a comment I make is relevant or not, but I'm trying to make it relevant. So one of the challenges that I think that we're going to face in near future is multiple products from multiple groups using multiple methods. In the past, nobody could download all the data and run products and things like that. It took like a lot of time, so only a few groups were basically doing that. Now, if it's on cloud, all the data is on cloud, machine learning techniques are easy to use. Now you're gonna have a lot of products coming in, they are different. Then the challenge is which one to use. It's like, you can go like, okay, I'm gonna go with NASA flagship type of products, but a lot of people may trust other people's product, and that could be a challenge, how to find the best product out of multiple products coming up.
Okay, I'm thinking in my head, hopefully this comes out the way I want it to. Going back to your AI comment, I think one thing is even kind of building on what you said, Ali, is just communication. For the AI side, you might have the people that are not really familiar with how to actually generate the alerts. How does those methods actually go, with the exception of using AI? But I think it's the communication of saying, you still need the people that really know those processes to really validate and communicate the essential and the important. So when things disappear, let's say, I think we need to really show that we have a community of experts that are there to support and build those, and I think to check those AI. And this even goes to maybe even the side where data products are coming out and we can type into, give us a product that works, is even relaying what is your, the fitness for purpose, and communication, I think is gonna be a big role in how we play across communities going forward.
Great. Last question, I think, because then I want to pass over to Jessica.
Well, a question and a comment. I think one of the problems I see when working with users is that they don't really want to use new platforms or new software. So if they're using ArcGIS, that's what they want to keep on using because it takes a lot of effort, a lot of money to train their staff. And also, quite often we see this decoupling between the decision makers in the organizations and maybe the GIS team or the geospatial team that's actually using the data. And so I think one of the barriers is probably, are we talking to the right people to make sure that those organizational transformations are happening and coming from the people that have the actual power to introduce those changes. And finally, a lot of applications require data that's very different, not just precipitation. They'll probably need land cover. They'll need temperature. They'll need a bunch of things that come from different places. So how can we do a better job putting everything together in a way that's easier for the user, especially users, which I think is like probably 90% of the users, don't have more than 1 or 2 guys who can actually work on it. So that's.
Yeah, great comments. Yeah, Jessica, is it okay if you take over the?
Absolutely.
I don't want to cut you off without
Good.
time.
You're totally fine. Thank you. I'll give you this. You can run around the room. Okay, so we've already kind of hinted on this, and we want to spend a little bit of time talking about how AI is going to transform this. And we've already heard talks. We had great discussions kind of leading up to this. Machine learning, AI, it is here. It's going to be here unless there's a huge data crash and we all, but it's going to be around. And so some of the things that we're thinking about, right, is what are some current challenges? And this is not just for the precipitation community, but challenges in general for AI. And what kinds of problems that they are going to be posing, and how do we overcome them, and really thinking about improving that over time. So we already know, I think, all of the stuff that I'm going to show here, right? But one of the big problems is computational resources. Maybe it's not for us, right? I can use the supercomputer at NASA Goddard. People can use their GPUs on X, Y, or Z, but in a lot of places they don't have those resources, so they're going to depend on other people to provide those things. And then that is going to lead to other issues, right? So thinking about for computational resources, these are going to become probably better as we go in with time, but it is something that we have to think of other people that don't have those available, and that's a problem. Training data is limited, right? So if we look at some of the AI models, this is an example of HENS, which is an NVIDIA product that they basically take in a whole bunch of Era 5 data, and then they're able to produce these models over just minutes, right? Now, but with that said, it's limited to the data that's going into it. Era 5 is good. We know that Era 5 is good, but it has biases, it has issues within it that we can't track necessarily. And we throw that into a model, we have to think about what the repercussions mean. And so this is kind of an interesting showing how quickly this information can be used. Models are limited by the scale of microphysics, specifically for precipitation, right? That's something that we all know there's a problem with, especially for me. I look at landslides in the mountains. Mountains have issues. We have to do a better job at understanding what kind of precipitation, what's happening on a smaller scale, and really putting that into the models. But how do we do that, right? That's a limitation. A lot of that is looking at hybrid models and taking that physical component and merging it with others, which some have already talked about today. Extreme events are not well represented. And granted, they're becoming more, right? And so they're getting more represented, but being able to model, especially when we think about any kind of forecasting, it's hard to forecast something that's never happened on the scale at which we're seeing them, right? If it's happened in the region, that makes it easier. But how do we deal with that? And moving forward, right, we have to think about how well they're represented. And obviously the black box problem. You throw it in, what comes out, it looks good, but how do we explain it? These are all things that we've discussed and know about. And then the last one, again, we've already talked about this today, but the lack of trust. As we move forward, we are the people, this community and experts, are the people that are giving that trust to those products, but what happens when that is not available? And that's something that Chris also talked about. So for this next little portion, we're going to think about, and you can add to these things that I've added on here, is current challenges, and then thinking about how they can pose the precipitation and applications community. If there's things that you specifically want to talk about, things that I missed. So yeah, open it up. Yeah, Effie.
One problem that we discussed is how to use data at their native resolution without having to regrid everything, extrapolate or interpolate. The AI methodology for that exists. It's called infinite dimension diffusion models. So it works not in Euclidean space, it works in Hilbert space. So I do it on functions. It's difficult. We've implemented with another group like halfway through that, in the sense that I will use explicitly very sparse rain gauges, which are, here, there, et cetera, but I will use an average of these rain gauges as, say, 5 by 5 kilometers, and there will be a sparse representation. So I will have rain gauges on a sparse grid, and the other data full on that grid. And that has worked. We try to go further in the infinite dimensional space. But I think this will be something that it will help. Because, if we have 10 by 10 kilometer precipitation and we downscale, I mean, we regrid ERA 5 data from, 0.25 down to that, it's interpolation, it's not real data. So we create information that's not there. So that's one thing that I see. The other was, well, I'll come back to that after some.
At least from a forecasting perspective, I would say that data is a huge issue, and also variability in the accuracy in the data. For example, in the Northern Hemisphere, we have good data sets, but when you look, for example, in the accuracy that we have in the tropics, it's quite a difference there. We know, the precipitation in the tropics is quite challenging. So, yeah, I would say from a forecasting point of view, data accuracy, and also the internal complexities of predicting precipitation. So we have more and more approaches that appear in the literature, such as downscaling, etc. But you may use diffusion models and get very beautiful rainfall predictions at 5 days, and you might get spectra that look exactly as the reference, but you still won't have scale in those small scales. So it's actually quite challenging as as an application, right? Predicting precipitation is just difficult.
I think really the heart of the problem is the microphysics. We don't understand enough, the details enough anyway, and we don't have enough observations. Most of our observations are from in situ on the ground, or flight on an airplane, which I don't really trust what it's measuring, because the airplane fly over, you disturb the environment. And then we have almost nothing in between for the whole column. So for precipitation, I think the microphysics process is really the key. But right now, we don't have enough observation. And also for the observation we have, we don't even know the uncertainty. Let's say, for example, in the microphysics parameterization, especially for ice particles, you need a mass dimensional relation. And in our retrieval forward calculations, we also need a mass dimensional relation. But if you look at how the mass dimensional relations are derived, we don't have the uncertainty for for both actually, for both the maximum dimension or the mass in our observation. So, we're basically guessing in a sense. Oops, sorry.
Yeah, I think you have already listed, right? You were looking at the 3 discussion points that you put listed here. It seemed like discussion point 2 and 3 kind of belongs to scientists' questions, like microphysics, uncertainty, or AI. It kind of comes to do our job in the science. The first one is a little bit more not in our hands, the data availability. That is not, you have to get the data from someplace to start with. That's your starting point, has to be. And in that sense, so if you look at the precipitation field, in US at least, we are pretty good open source data availability a lot of times. But there are exceptions. Number one is we learned that Mesonet data, which has a large number of gauges, not open source. And like anytime we have the state Mesonet networks, people says, come and talk to me. What does it mean? I will not gonna give you right away. So there is one issue that. Obviously, from the satellite perspective, the data is pretty much open. Now, internationally, it's not the case. There is, at least we know, another GPM is already been launched by another country, but we have 0 data from that. There is another GPM course satellite available, but we don't know anything about it. This is the fact. Thank you.
Yeah. Okay, one more and then we'll move on. Does that sound good, Kathy?
Sure, yeah, absolutely. This ties right into the next part, so it's totally fine.
I just wanted, my only comment is, I think I talked about it, Effie talked about it. I think we need to impose some metrics on this. Right?
Yeah, agreed.
If we don't have metrics and everybody's free to define their own metrics, everybody's product is going to be the best. Or they're really bad at setting metrics. But I think as a community, if we don't do that, and it may be a large number of them, that users get to decide which ones they care about. But I think we have to do that.
And NVIDIA and Google had to do that too. Because, I know the NVIDIA guy that heads all these papers that we see out there, Mike Pritchard, and he was asking me, what metrics do you use? But they could not implement all these things, so they ended up using mean square error. So they have to learn too.
Mm-hmm. Absolutely.
And that shows up in the forecasting world too, right? Where these AI models minimize RMS error. In a lot of places, you just predict 0, and that's your best.
Yeah, absolutely. And these have pretty much already been kind of discussed and talked about, right? This idea that decisions are going to be hopefully not made, but already are kind of being made off of maybe not complete results or incorrect results or bad science, things that we can't necessarily follow where the information is coming from. It's a real issue, and it's something that we need to, as our community, evaluate and think about metrics and do better. These are some of the ones that are kind of in a fear kind of set, but funding for traditional science might decrease or disappear. That's already happening. That's something that we have to think of, right? As AI is becoming more and more widespread and companies are doing it, not to say that's necessarily a bad thing, but as far as scientists in the community, that's something that's going to reflect and influence us, right? As Andrea said, the trust, like we need the experts to be able to say the what's right and what's wrong. Is that going to continue? Hopefully, right? It's up to us to do it. Jobs. We see this in other areas. Luckily, I don't think jobs have been necessarily lost in the precipitation community, but as it advances, it's a real potential. We've already discussed the open and free data might be lost or replaced or produced and competed for. And then models might be accurate, but without physical meeting, right? And that's a big thing that we already see, and that's something that having those metrics available, being able to trace that is an important part of it. And so when we're thinking about this AI, I try to talk about a lot of the negative aspects, and some of you have already talked about a lot of the positive aspects. You already know these things. But maybe when you think about it as you were talking about, Chris, as saying, okay, maybe we're not going to necessarily just use it for estimating precipitation, because we know we can't really do that accurately because we don't have the microphysics that's actually a part of these models. But maybe we can make it easier to use AI in a different way, right? Able to use it more effectively, maybe to analyze, maybe to actually think about that end user and who's going to be utilizing that on the other side, right? So kind of try to push it in that direction so that we're not necessarily losing out on our precipitation community, but we're also kind of moving into it and allowing it to be an improvement. Helping identify events more effectively, increase users of precipitation applications. This is something that we're, I think, constantly wanting to do. We want more people to use the data. We want more people to understand the data. We want to be able to say that it's being used in good ways. And improving communication, right? AI is already doing that, as you showed. Improving communication, improving disaster planning. How can we kind of lean into that? And so these are some ideas of thinking about how it's going to potentially improve. And I want to open it up to ideas or thoughts on this. So it's not just from the precipitation, estimation, but also like how we can use it in other ways, if that makes sense.
I'm going to stand on this side of it.
Absolutely, yeah, absolutely.
We haven't heard from the people on the right.
They're all tired. It's been a long day. Any thoughts? Yeah, Andrea?
I think going back to a few folks that talked about time and resources, that's a huge barrier, right? And so where AI can help is actually reducing the time to actually understand. So novice users, while it's really, actually to many of us still, is super overwhelming. It gives you a start, whether it's the right data set for you or not, it gives you a start into, let's say, the NASA Earth data tool. To give you just like, here's one, this is how it goes, this is how you can go if you're like visualization tool. It's great ways to streamline. I mean, there's so many folks, even in the forecasting side, it's operated by like 2 or 3 people in certain countries. And this might be a good way to effectively start planning and understanding what data sets are out there, not necessarily using it operationally, but with the time and resources they have. So I think that's one is.
I mean, I agree, but I also want to remind people that I Googled, I used AI to find the weather radar in Kampala.
That's
a
very good
no
point.
problems giving me that.
Absolutely, and that's part of the issue, right? Like, how do we fix that? Can we fix it? Is it something that we can actually tackle?
No, in line with the same comments, actually, you are talking about trust, but these communities, precipitation community from space is quite large, but with respect to AI community, probably, I don't know, 1%, even much less. So the problem is that, as Chris mentioned in the slides, weather radar over Uganda and AI tell you yes, and our normal life is like this. We have to Google everything, and we trust them. So basically, and we are at the very beginning. Probably in a couple of years, we will trust more on AI with respect to on data. And so the challenge here, you say, okay, AI can help to, attract a new user, to improve communication, but it is very likely that before or later it will be more AI than data. And this is, to me, the major challenge that we have. Because even in the science community, if you tell me which product for precipitation to use, I am in trouble. Consider that you have, I'm a meteorologist, I don't need only precipitation, it's monsoon, evaporation. I see also in the slide, the people continue to use modeling data as data. They are not data. SMAP level 4 is a model, it's not a data. But still in science we are using. So basically that's why the challenge will only increase, because now everybody is developing data sets. Downscaling with some machine learning, put together in situ modeling, and that's it. Numerical weather prediction now is basically more focusing on AI. If you talk with the numerical weather prediction people 5 years ago and they say, okay, you can use AI, they say, haha. So that's I don't know how to improve the trust on data, because we are scientists and we believe that data are the holy true or whatever. But probably it's in this kind of changing world, it will be more and more difficult. I don't know how to address this.
The agentic AI system that we're building, I spoke of earlier, we use it to reproduce published studies. So then we have something that we know that we can compare to, and that we have a benchmark. But more importantly, that is to help scientists to improve research productivity. Say, for example, the study we reproduced that used Tempa data, 12 years of Tempa data. So we reused the workflow on 12 years of iMerge data, and it's not reproducing anymore, it's replicated the study using the iMerge data. And we were able to do that in 2 days, including downloading the data and apply the analysis. But that doesn't, you mentioned something that is very important, that's the computational resources. That still depends on your computational resource. You gotta have enough hard disk to store the data, and then you have to have a big enough machine to process the data. But that problem, I think, can be addressed by cloud. But then, the researchers have to find money, basically, to pay for using that resources. I suppose that will be part of our proposal then. Proposal budget.
Well, it's interesting because if you have something like that that can go back and replicate different papers and different projects, you could do that with lots of different products and to compare them. And same methods, you can actually see which one is better in some regard, right, with good metrics.
So the system that we're building has the usability in mind when we were designing it. So basically, the researcher just upload a PDF of the publication. Then the scientist is in the loop, so you have to validate the artifact that it produced, like the reproduced figures or tables. But scientist is in the loop, but most of the work is done by the AI, including writing the Python code for doing it. We don't have access to the code of the original study. So it was produced by the AI using Python, but it's not limited to Python. If you want, you can ask AI to reproduce it using MATLAB, say, for example.
Very interesting. Yeah, Chris.
Yeah, I just want to point out that I just saw the end of my career looming, where if we write papers about how to generate, precipitation data sets like iMerge or GPCP or CHIRPS, the AI is going to steal our methods and recreate those data sets.
That is
Watch
very
out.
true. That is absolutely very true. It's already kind of doing that, right, though? So if it's out there and available to people, it can use that information. So do you have a question or thought? No? Okay. All right, well, I think I don't want to keep you guys. It's 5:40, Vasca. Is this when we should stop, or do you guys want to discuss a little bit more? Or yeah, go ahead.
Just a quick comment on AI. So AI is great, and most of us were trained before AI was around. So we learned about the basics, we had to study, read the textbooks, all that. What about the new generation of students who, instead of reading those textbooks, are actually just going to Gemini or Claude or something like that? What will be the impact of that in the future of precipitation? I think that's probably something we should also discuss and take into consideration.
Yeah, I think that's a great point. Do any of you guys have, I'm sure you guys have children, but my children, I have a 10-year-old and a 6-year-old, and they're growing up with already these things at their fingertips, right? They can easily use a phone in the computer already and just imagine what it's going to be in 10 years or in 20 years. So yeah, I think that's a really good point. I think it's interesting, and if you guys want to discuss it, I would love to hear about it. Yeah, absolutely.
Just a quick one to, to bootstrap off of what Vasco said. I am not a scientist. I am a lawyer. I'm a parasite here soaking up all of your knowledge. But to allay your concerns, possibly, one of the big conversations in the AI community, or the AI world of legal research and representation, is people who are above a certain age. We're trained the old way with actual books and with actual exercises. And in some ways, it's making lawyers and law professors over, say, age 40 or 45 much more effective users of AI and legal research than the ones who are going through law school right now. And there may be a special premium on scientists of your generation because you were classically trained, but you also know how to use the newest instruments. And there may be a particularly valuable social and professional capital there that you are not good at recognizing because science is very humility-inducing. Okay, and so I would just urge you to think about that possibly.
Thank you. I think we are afraid that we will end up with people who don't have critical thinking about the products from AI. AI doesn't think, doesn't have critical thinking, and I don't think that that will go away. So. A trust is something that will need to be defined according to sets with rigor, transparency, and a set of criteria that are met by the needs defined by the users. People will generate precipitation products blindly. Yeah, sure. Are they useful? No. So we'll need to find a framework to convey what the users are expecting. And trust will be one of them. And how we define it, that will be our new way to define it. As far as this capital, yeah, I totally agree. Somebody who is just putting some prompt to ChatGPT and generate a precipitation product like shirts is not a scientist. So let's not forget we are scientists, yeah, and what it means exactly.
We have a question or a comment in the back. Yeah.
Hi, so I'm currently in college, so AI became a thing when I was in high school, my last years of high school, and it's interesting hearing about your perspective, because for me, what you're saying, people don't have critical thinking. This is true. There are people in my age range that they use AI for everything, and they can't write emails and anything anymore. But I think, especially in the science, STEM, I'm studying STEM, right, science, and so especially in science, people are very critical about what AI pumps out, because what you said, AI doesn't think. So for example, I use AI when I'm doing homework and things because I want to check my answers, but it's just another tool. I'm Googling something, and it's very easy to see sometimes when it messes up because it doesn't make sense, especially ChatGPT and the ones that are more low level. And so I think that it's not a concern in the sense it's not gonna you still have to think about the results, and so yeah, so. If you're just producing data, yeah, it's not, or it's analyzing the data, but it's not thinking about what that implies, and that's, I think, the bigger job that scientists have.
Thank you very much. Yeah, we're gonna have maybe a couple more, and then we'll call
fully
it.
agree that AI doesn't think, because first thing is that when we say AI, I think most of the time we mean the large language model. But AI is more than a large language model. And sometimes we also use AI to mean machine learning, which is not the same thing either. And also machine learning is not just neural networks. There are other machine learning methods too. So just get that out of the way. But the large language model, they operate on text. So that's what Pierre was saying, basically. It doesn't think. It just learned from all the text, from the context of the text. So that, when we use AI, I'm old enough, but I'm also kind of aware or knowledgeable in some sense of AI, is that you have to use it with caution. And also, there are only certain things that you can kind of trust AI, not fully. Say, for example, AI now, large language model, is very good now in writing code. Probably better than some of the starting software engineers. And that's the thing that I found very useful to scientists, because we scientists in our classical training, we have to write code, but we are not really that great programmers. So the LLMs that helped us writing the code, that frees us to do actually more reasoning and the rational things, the more deeper things. I think that's the plus. But like the other people have mentioned, we have to take it with caution, use it with caution.
Okay, I'm a professor at the Federal University of Rio de Janeiro in Brazil. So I work with students, okay, and they are not coding anymore, they are not thinking. And my concern is not checking the results, but getting the results, meaning you have to learn how to think first, not against artificial intelligence at all, but you need to learn how to think, how to get there, how go out of the box to make your point, to evolve, actually, in terms of human beings and even improve artificial intelligence. They need us to get improved. So that's what I have to say.
Thanks, Anna.
Oh, okay, Pierre, and then Daniel, you're going to be the last one. Does that sound good? Awesome.
Okay, Daniel, you want to talk? Yeah, no, I think I think we are in agreement, everybody here. I really like this, I don't know your name, sorry, but your comments was great because don't have to code anymore, great. I never was a great coder. And there were bugs in my codes and some hidden stuff that I never discovered. AI may code, fine, there will be some issues with it, as long as I can check it. I have some tools to check it, fine. As long as I can apply the critical thinking that we will need to apply AI, where is it coming from? It's not coming from a computer. We are going to need to train in order to be able to check AI. And we'll go back to the books, or we'll go back to learning those principles or those very physical principles that define precipitation. So that is not going away. We'll look at the problems in different ways. Probably we will enrich the way we are doing it. So I think right now we are a bit scared because we don't know where our strengths are. And we need to figure that out. Okay, I will shut up now.
We have Daniel. We could probably talk about this forever. So let's have Daniel. And
No pressure. Okay, it feels really weird saying this from like an early career perspective, but like a bigger picture outlook on it is what can we give and what can we gain from the next generation of scientists? So something for us at the minute is that I think pretty much none of us in the room, none of us were really trained in AI, but we need to utilize it for precipitation science going forward. For the next generation of scientists, there's going to be more of an emphasis on AI and in terms of being trained on it, but our role is going to be to pass along the knowledge on precipitation science, but also that, you know, ability to be able to use AI, you know, efficiently, effectively, and to still utilize what we've learned and pass that along. So I feel like we're at a weird point where it's like, you know, we'll gain from the next generation because we will maybe not have the skill set that they have, but they need stuff from us as well. And I'll also just say, I feel like, you know, maybe it's not been as revolutionary before, but we've had to go through the age of computers, where I'm sure like our old professors and further down the line have had to, you know, learn to use computers, and it's been easy for us, and maybe we're kind of in a similar age, just with a different tool.
Yeah, great points. And I know this. I know we have another comment. You guys want to hear one last? I said that was the last one, but we haven't heard from him. One? Okay. Yep. All right. Go ahead. And then we're done. Right. I promise.
Okay. So to confirm and conclude all the discussions that we have. So I'm following all the conversation. I really like. I believe that AI is only a tool. So when we talk about producing data or simulating model with AI, my hand is shaking. You know, and I believe Vasco's question. So as a scientist and researcher, we have to somehow teach other people how to use AI. To be a little bit funny, I just asked ChatGPT. You know, my car is dirty and I want to wash it. I'm almost near the car wash, and it's about 100-meter distance. Is it okay to go by walk, or shall I go by car? You know, it's completely clear. My car is dirty. The answer is, if the car wash is only about 100 meters away, it's generally fine to walk. You know, and then so it makes some conditions. If the route is safe for pedestrian, if you do not need to move the car into the queue immediately. You see, so we have to have some other backgrounds, and then so to the trust points that Luca pointed out. So we have to really take care and consider this point as well.
Okay, well, thank you very much. This has been really interesting. Vasco, I don't know if you want to say anything before the end, but I appreciate all you guys discussing and hearing a lot of different voices, and I'm excited to see you guys tomorrow. I talk tomorrow, so yay. But anyway, I think we're having a cocktail networking?
Yes, so
okay.
we're having an icebreaker exactly in the same spot where we had lunch. You're all, of course, invited, and then we have so for people who actually booked the shuttle back to the hotels, we have the first one at 6. Sorry, just a second. 6:45, and the second one at 7:15. These ones are not. They're not booked by the same order as the morning ones. So it's first come, first serve for those who actually booked the shuttle. Sorry? They are. Unfortunately, at this point, they're fully booked. But if you want to try, maybe someone gives up or goes somewhere else. Not. Yes, you can. Yeah. If there are empty seats, you can take the place and go to Don Inês, Hotel Don Inês. Okay. Oh, another thing, before you go. Sorry. So there is the possibility Thursday, so it's after the conference is over, so Thursday, there is a chance to book a tour guide to the old campus of the university. If you want to be part of it, reach out to me. But before tomorrow's lunch. So either today or tomorrow morning, reach out to me if you're interested. You, your families, okay?
So I just did this tour yesterday, and it's totally worth it. You get to see the Baroque library, you get to see the palace. It's incredible, and they have really good people that are actually giving the tours as well. So do it. You should totally do it. There's also some on Wednesday afternoon as well.